Our lands go from the Werri River, south of Melbourne, out the Dandenong Ranges, out to Druin, Warrigal, takes into Wilson's Prom, French Island, Phillip Island, comes around the Point Nepean, around to Port Phillip Bay. So that's all Bunurong country. But we are a part of a Kulin nation because our tribes are our neighbouring tribes. To the west is Wathaurong. Then we've got to the north, we've got the Rundri, Tanarong, and Jarjarung. So we are, so there's all these clans as a part of a Kulin nation because we all used to come together for corroboree, trade, initiation, marriage. And the MCG, where the MCG is today, that used to be a corroboree ground. So we all come together and do the celebrations. And so we was all connected. But we are standing on sacred land. And I just want to acknowledge CSIRO for the work that you're doing and then within the symposium. I think it's great work that you do. But we've got Monash and everybody else that's involved. Because what we do today, yeah, this is important because this here is what sustains us. So do the hard work today to make it better for tomorrow. Better living. And so also Woomajinka Audio y'all want along Bunurong. And let's welcome all our friends to our lands of the Bunurong. Let's walk together and learn together. Because we want to be on the journey, but the journey has got to be inclusive of all. And let's walk side by side. But tread lightly while on country. Because we are connected to place. And underneath our feet, our history sleeps. So I wish you well and stay safe. Thank you.
Good morning, everyone. My name is Dan Yang Yin. I'm the chair for this symposium. It's my great honor and pleasure to welcome you to this International Symposium on Food and Feed Extrusion, co-hosted by CSIRO and Australian Food Engineering Association, and here at CSIRO Innovation Center. Welcome. Our goal is to create a safe and a pre-competitive platform where knowledge can be shared and the new ideas can be sparked together to shape the future of extrusion. This symposium was initiated from a conversation in our extrusion community of practice. This is a global network connecting industry professionals and the research committed to advance extrusion technology. If you are not one of that, you are welcome to join this community. As we discuss within this community, and it became very clear that there are a significant gap, more than 2 decades since the last this kind of event dedicated to food and feed extrusion. The last one is in 2003 in Bangkok. And then previous 3 sessions workshop is hosted by CSIRO in 1990s in Sydney. So CSIRO is, we are proud to support innovations through Smart Extrusion program, which is led by Jay Silaheva, who is attending online today. And we support custom formulations, prototype development, sustainable processing solutions, and industry collaborations. And so we are delighted to host this long overdue International Symposium on Food and Feed Extrusion. It's time to reconnect and reignite. So this year's program brings together 7 keynote speakers from Canada, the States, Europe, Australia, and New Zealand, and over 35 session technical presenters spanning from globe, and diverse of online and inline, or on-site and online participants from cross-continent. This symposium is not just about sharing technical insights. It's about collaboration, it's about inspiration and transformation. Over the next 2 days, we will explore how extrusion is evolving from a simple shaping tool to a powerful platform for delivering nutrient-dense foods, functional ingredients, and sustainable feed solutions. We will hear from global experts on topics including smart, energy-efficient systems shaping the next generation of extrusion, AI, digital twin, and protective control transforming process precision, advanced modeling and optimization, unlocking new level of efficiency, novel feedstock circular solutions driving sustainability in practice, and precision nutrition for pets, fish, and livestock, innovations in texture, flavor, nutrition, rendering product quality. I encourage everyone to actively engage, ask questions, share your experience, and connect across the sectors. Innovation thrives when we collaborate. Please take a minute to scan the QR code here or of the walls to share your expectations for this event. I would like to acknowledge our speakers, sponsors, and organizing committee for making this event possible. In particular, I'd like to acknowledge our gold sponsor, CSIRO, a global leader in extrusion technologies. CSIRO empowers industry to transform new materials to high-value products through innovative and efficient solutions. And a bronze sponsor, Colin Lab Pilot Solutions, a premium supplier with 50 years experience in modular lab and pilot scale systems for material testing, extrusion, and production scale up. And also our industry's booth sponsors, Australian Food Engineering Association, Anton Parr Australian, Food and Beverage Accelerator, Thermo Fisher Scientific, and Rheology Solutions Australia. Your support has been invaluable. And last, we have some housekeeping reminders. Toilet is over the corridor at end, and emergency assembly point is outside the field of reception. And inside, there's no smoking. And please don't leave your valuables in your car. And the gate access after hours, use the swipe card hanging on the beside the gate. Please do not remove. And if you want to charge your laptop and a cell phone, the charging station is at the back. And all session will be recorded. If you have any concerns, please come to see us. And presentation time, that's the session presentation time is 12 to 15 minutes. You will get a reminder in 10 minutes and secondary reminder 12 minutes. And please leave your lanyard and before you leave tomorrow. And we also have a Best Presentation Award sponsored by the Cholesterol. This will be announced at the closing session. And we'll take a group photos at 3 p.m. this afternoon before the afternoon tea. That's outside the reception area. And also at 5:30 here, and please vacate this part for the dinner setup. And also, if you want to connect to the online, please turn off your microphone and the speaker in your laptop. And now it's my pleasure to introduce our first keynote speaker, Dennis Forte, a highly respected chemical engineer with over 30 years experience in food processing, including senior roles in Mars and Uncle Toby's. As an independent consultant and author of 4 textbooks on food extrusion, Dennis has played a pivotal role in advanced extrusion technology across the globe. Please join me in welcoming Dennis Forte for his keynote address on the evolution of extrusion technology. Thank you.
Thank you, Dan. Introduction. Welcome, everybody. Thanks to everybody for being here and for the opportunity to talk to you all. I've been lucky enough, or unlucky enough, as evidenced by the lack of hair, to be working with extrusion for the last 40 years. And the important thing is I'm still learning. So I do spend a lot of time trying to share what I have learned, but I'm learning every day. There's always something new to be had in extrusion. So it is an emerging technology and it's still growing and it's still evolving. So what is extrusion? Dictionary definition says it's a process in which a material is forced to flow through a restricting orifice or die. And that die can take all kinds of forms or shapes. This also means that the material that we're forming within the screws is a fluid. So understanding extrusion requires understanding rheology and fluid dynamics. And if you don't want to work in those 2 areas, don't work in extrusion, okay? Because if you don't understand these basic fundamentals, you will never understand extrusion, okay? Words of warning. Extrusion is used for many applications, a lot of non-food applications, and that's where the technology originally evolved from. It was subsequently transferred to the use in food processing. Now, in normal non-food applications, the raw materials are basically fed into the machine, transformed into alternative shapes or forms, but remain essentially unchanged. In the case of food extrusion, however, the raw materials that we use, this is a bit wrong way around, it's interesting. In food extrusion, however, the formulations are far more complex typically. It's not uncommon to have 10, 20, 30 ingredients in a food recipe. Food technologists cannot help themselves, they just keep throwing things in there. And it's our job as food extrusion engineers to transform that material into some kind of product. And that transformation involves irreversible physical and chemical changes. We call that cooking. most importantly, anyone's ever been to any of my training courses, this cooking process is not gelatinization. It is not denaturation, because those two processes require excess water and a long time. Extrusion does neither. Extrusion involves short time, elevated temperatures and pressures, and the presence of shear, such that the process occurs in seconds instead of minutes and hours. So the products that are produced are cooked, they are transformed, but they are not gelatinized. They are not cooked. So I encourage all of you in the future, stop using those words. Because if you keep using those words, you're missing the key point. Extrusion is different. It does not produce normal products. It produces extrusion cooked products. And these are different. Why is extrusion so popular? And the answer is, it can do all these things. In my time, in my career, I've used extrusion technology to not only produce foods, but I've made everything from boiled lollies to explosives using extrusion technology. That's the broad spectrum of stuff that this technology can do. It's up to us to extend it even further. Okay? And extrusion didn't just happen. It has evolved and continues to evolve. And that evolution has involved both manufacturers, product developers, formulators, all working in unison. And there's a lot of cross-fertilization of ideas from one industry and one technology to another. And so this evolution continues. It started as simple as a shaping technology, making ceramic beads and things of this nature, simple things. The Romans used it to make pipes. Okay? So the technology's been around for a while. We then started processing foods, making noodles in batch-wise presses. So we've seen the beginnings of extrusion. Back in the late 1700s, a guy called Joseph Bramah developed an extruder for producing seamless lead pipes. These are all piston-type extruders. And then that technology was switched over to making clay pipes. We revisited what the Romans were doing. Right? So sometimes it goes round in circles and we go back. This happens. And maybe second, third time round, third iteration, the technology gets a bit better, gets refined, gets improved. That's how we do things. You don't always get it right first time. It takes time. And so the technology continues to grow. In 1873, the first patent was issued for a twin screw extruder. The growth and continuation of the piston-type extruders continued, and people started understanding that changing, don't just have a hole in a plate, change the shape of the hole, put the right angle on refine the geometry of the die, and we can refine the product, and better tolerances, better control, improved functionality in the products as we improve the way we do the extrusion itself. Engineers got involved and started trying to understand what was going on. And so we start writing down some mathematics and trying to explain how this extrusion thing works. And it continues to grow. In 1914, Di Franceschi and Sons developed the first twin piston press, for pasta production. So the pasta was being made, the pasta dough was being prepared continuously and manually transferred into batches, into a dual piston press to get semi-continuous extrusion of pasta. In 1929, in Germany, the Phoenix Gummiwork Company transformed the single screw for making rubber. And this is the beginning of continuous screw extrusion at a semi-commercial level. Our friends from Bühler in Switzerland developed the first single screw pasta press for the continuous manufacture of pasta. And so we're starting to see food coming into extrusion. Colombo and Pasquetti developed modified the twin screw that was developed by the guys back in the 1800s and improved it for the transformation of plastics. Colombo, by the way, the C, that's part of the BC name, Klextrol. He was one of the original design engineers that designed the first Klextrol extruder. He was involved. You're going to hear lots of names that will sound familiar. They've been around for a long time. It's a bit of an incestuous industry too, because people change camps every now and again. Okay. General Mills and Kellogg came across this thing called extrusion and started using it to make some of their breakfast cereal products. The first large-scale commercial breakfast cereal, and it's still around today, Special K from Kellogg's. Okay. It's still being made the same way. Okay. Same way. Dunham files the first patent in the UK for the single screw extruder in about 1938. Over on the other side of the Atlantic, Mr. Wenger, Levan Wenger, decides good idea to attach a screw to the back of his PTO tractor. Okay, and that's how the first Wenger extruder was operated, from the power takeoff of a tractor in the back paddock of Mr. Wenger's farm. Went so well, his friends saw what he was doing, and he thought, we'll have one too. And the Wenger Mixer and Company was established. He got out of farming and started building extruders instead, because there was more money in extruders than farming. Wenger's still going today. No longer family owned. Now it's owned by an investment consortium, but that's another story. But the name's still out there, and the extruders are still out there. But this is where they began. Similar times frame, another company was making rabbit food. By the way, we're in the middle of the Great Depression now, so rabbits were good food. Rabbits need to eat, so if we're going to farm rabbits, they need to be fed. So somebody decided they could take corn and other grains, put it through a machine and use it to flake and make flaked rabbit food. That machine ultimately became the friction disc extruder that makes twisties. That technology is still around today, still making twisties. Okay? The twisty product was developed by accident because one of the operators decided to throw some corn into the machine to clean the machine out. But he forgot to add the right amount of water. And instead of just cleaning the product came out and exploded and became an expanded snack. After many iterations, that company, that group of people, became Frito-Lay, PepsiCo, brands we still know today, still using the same technology in some places. Okay? So these products, these technologies have long histories. Another spin-off from that was the collet extruder that is now used for making direct expanded snacks. The original technology used for making Cheetos, Cheezels, so more of the brands that we may be familiar with. Okay? And so the technology continues to evolve. In 1940s, the single screw expeller was developed. We'll put holes in the barrel wall and let the oil come out as we squeeze the seed. And so oil extraction became much more commercially viable, again, courtesy of an extrusion screw. In the mid-40s, Gaines homogenised meal was released. It was the first commercial dog food. And that grew to become the pedigree business, or Mars Pet Care. Again, these things have long histories. In the 50s, a company called Sprout Waldron developed a pressurised preconditioner to pre-cook the material before it goes into the extruder. And these machines became quite popular in the 60s and 70s. However, the problem with that is every time they blocked, you had to disassemble a pressure vessel, so they became not very commercially popular, okay, even though they worked very well. As polymers and fine chemical industries grew, the technology started to develop. And so the technology became more and more refined. Certain companies were involved in that refinement. One of those companies was Chrysler that ultimately became Clickstrel. This is one of their machines, installed vertically. Extruders don't have to be installed horizontally. Gravity doesn't matter in extrusion. The forces involved of such high magnitude that gravity doesn't count until the product gets out of the die. Then gravity takes over again, right? But inside the extruder, it's a whole new world. Gravity counts for naught. The Ralston Purina Company, now Nestle, part of the Nestle group, they launched the Purina dog chow product. Okay. Joseph Wenger, son of Levan Wenger, who built the first extruder, takes out a patent for a twin zone or twin chamber preconditioner with claims that it improves palatability and digestibility of the food that they can make with their extruder. These preconditioners are still around, and the claim is still valid because palatability and digestibility do improve with preconditioning. Okay? This is why people still buy them. This is why they are there. And so this technology keeps growing. Another group of people got together and they ultimately became the Instapro company. And those extruders are still around. In the 60s, again, as the polymer industry kept improving, the venting process was established for removing volatiles, residual volatiles, out of the polymer system. That technology is now used to optimise expansion behaviour in food extrusion for aquafeeds and other products. So there's a lot of cross-fertilisation of ideas and technologies from one industry to another as the technology evolves. And in the 60s, in the late 60s, early 70s, Chrysler, now Clickstrel, Baker Perkins, and Werner and Fleiderer, now known as Caperian, all became important players in promoting and developing the application of twin screw extrusion for foods and really started to push this technology into the industry. These guys are still involved and one of our gold sponsors. The concept of reactive extrusion started being talked about. And really, what is cooking? It's reaction extrusion. That's what we're doing. Optimising our conditions to get the right cook, the right flavours, the right textures, the right colour development. That is what we're doing when we're doing food extrusion. My apologies. I have to learn to stand still. The advent of the modular extruder became more and more common. What's the benefit of modular extrusion? We can fine-tune the screw profiles to really get control of our processes. Equipment suppliers started offering new elements, reversing element, cut flight screws, all these sorts of things that progressively took our processes further. In the 90s, some of the equipment suppliers started offering higher speed screws, resulting in different types of cooking processes and higher outputs of the machinery, because everybody's looking for more economic ways of doing things. Through the 80s and 90s and continuing today, more and more books are being written about food extrusion. So, and some of the people involved in writing some of these books are in the room. Okay? So there's more and more information being made available. In the 90s as well, other things start, again, cross-fertilisation. So by this stage, the conical twin screw was relatively common in the polymer industry, but these were counter-rotating conical twins. So Wenger launched the co-rotating conical twin. And these machines are around and available now. Also, the aquafeed industry was growing and developing and still evolving, and accurate control of bulk density became very important, accurate control of cooking, and so many versions of barrel valves began to be offered by the various suppliers to allow accurate control of the cooking and the expansion process as well. And so we continue to evolve. The Andritz company, or at the time it wasn't Andritz, it was, I can't remember their name now, but they developed the positive pressure control. So you're actually controlling the pressure within the cutter hood to get absolute control of the expansion process of the product. And just to prove that engineers are completely mad, we keep inventing more and more complicated machines. And you can buy a triple screw extruder. It is commercially available. Okay? So it's out there. Is it necessary? That depends on who you talk to. And planetary extruders are also readily available. So what have we actually got? A wealth of different options in terms of screw designs. All kinds of shapes, sizes, brands, countries of manufacture, lots of different options. But don't forget, all of these options, all of these extruders are just doing the same unit operations. And it is these unit operations that are carrying out the transformation of your raw materials into your product. And so if, as a chemical engineer, we always think in terms of unit operations, because every unit operation can be understood, studied, controlled, optimized. And so too can your process. When it's not working the way you want it to be working, think about these unit operations. What is missing? Where are we going wrong? This is where the solution is. Optimize the screw, modify the die, improve the process. And understanding that involves understanding the fluid dynamic that happens within the screw. So we need to take the time to understand the rheology and the fluid dynamics. Because if we don't understand what's happening inside, we will never control what's coming out. And that's the key. We need to be able to be inside the machine. And the dominant force is always the rheology. We need to understand the rheology of our products, of our raw materials. You cannot just simply swap ingredients in and out of a recipe and expect nothing to change. We change the ingredients, you change the rheology, you change the process, you change the product. It might be the right density and it might be the right diameter, but it ain't the same. And flavour, texture, digestibility, feed conversion ratios, all these things that the industry measures itself by, changes. And right now, we still haven't got that, because there are many large global businesses who do exactly this every day and play with their recipes all the time, and then wonder why their factories don't work as efficiently as they should. It's a circular thing, and they keep chasing their tails. Right? So stop and think a bit before you do some of the things you do, because this rheology controls the fluid dynamics inside the extruder. The detail of the fluid dynamics is different depending on the geometry of the extruder. And those different fluid dynamics lead to different velocity profiles. This is what we call shear, that magic word we all mention when we talk extrusion. Most of us never really wrap our heads around what the hell is this thing called shear. But it's important because that's what the product sees. The product doesn't know that it's inside a French machine or a German machine or an American machine. It just knows it sees shear. And the shear does the transformation. And this is how you have to learn to think. Because every different machine has different capabilities. There is no perfect extruder. Every extruder is better at doing something and not so good at doing something else. So depending on the job you want to do, there might just be a better extruder out there for you. The one you have may not be the right one. So you need to be open to change. And where's extrusion going to go? The simple reality is, if you believe the numbers that have been talked about, by about 2050, there's going to be about 10 billion of us to be fed. Every human needs a finite amount of protein every day. That protein can't come the way it always has. We can't fish enough fish anymore. We can't grow enough cows anymore. We are all going to become semi-vegetarian. We have to. It's the only sustainable way to feed ourselves. And taking those vegetable proteins and turning them into acceptable foods, extrusion will have a role to play. We've had a go recently, all these meat analog products that hit the market. We failed because many of those products went out there with lots of encouragement, lots of excitement, but they all fell over. We overpromised, under-delivered. We have to try again, because there is no other way. And that's going to be your job. I'm about to get out of this business. You're going to continue. So this is your challenge. Make better products. Feed me and your grandchildren into the future. And extrusion will have a role to play. And on that note, goodbye. Okay. No questions, I assume? I'm out of here. Good.
Hey, Dennis, so you are encyclopedia of extrusion, I know, right? You know everything. My question is, like, we spend a couple of $1 million for this plant-based extrusion as well, but it's going down, right? You said that this is our responsibility, but what your suggestion is, what can we do? Are we lacking on the technology of texturization, or can we do some sort of like a more reactive extrusion to make more cross-links? You said we are delivering a false promise, but what can we do next?
Well, what I said was, can you hear this? Yes? What I said was that we over-promised and under-delivered. We promised that we were going to replace meat. We never were. Tofu doesn't promise to be meat. Tofu is just functional protein that can be consumed, and you do with it as you please. We produce some really good, well-textured products, which we call meat analogues. We should have just called it textured protein. Better than TVP, definitely, and more fibrous, almost meat-like, but not quite. But we should never have called it meat, because that was never going to be true. It never was, never will be. It's not meat. It's an alternative to meat, just like tofu. And ultimately, economics will make people eat this stuff. And it's our job to present good quality stuff that they will eat. Simple economics will do it. It's already starting. Meat is getting more and more expensive. And vegetarian diets are going to be the way of the future. There is no alternative. Either that or food wars. You pick, because that's the other option.
We have just one more.
Yeah, I just want to add to what the colleague said and what you answered. The biggest challenge for the alternative protein industry is that on one side, they have very motivated, educated people, but on the other side, they lack the basic knowledge of food processing and understanding of equipment and shear and flow and everything. So this is the biggest problem, and then over-promising investor pressure to put products on the market very fast, thinking like the computer industry, a product is 80% ready, we fix it on the fly. We cannot do that in food processing. And that needs to change. And the infrastructure, so the education for the next generation people needs to start at universities in combination, like a dual German apprenticeship system or something.
Wholeheartedly agree with everything you just said. Absolutely. Okay.
We have two questions online. First one, let Keith to ask your question. Keith?
Yeah, good morning. Can you hear me?
Yes.
Yes.
Yeah, I'm the other side of the planet at the moment, so I'm in my pajamas, so it's a good job you can't see me. My question for Dennis is, as you know, that I used to do a lot of work with Weetabix a long time ago, and having costed them tens of thousands of pounds in not understanding open area versus conductance. In your opinion or your view is, how do you see industry today, both the manufacturers and the machine manufacturers, getting to grips with really understanding, in terms of scale up, the importance of understanding conductance and get away from open area calculations for your die designs?
Okay. So you've used a whole bunch of words there, conductance versus open area, all these other principles. Again, what you're hitting on is understanding these fluid flow dynamics. That's what it's about, really applying true engineering principles to understanding what we're doing. To stop talking about, oh, geez, screw speed 300 makes my product. No, that is bullshit. What makes the product is the correct shear rate in that particular machine, and it happens to be happening at 300 revs per minute in your machine. That's what's actually going on. We need to get, and this is mathematics, is the way in. We need to get better at applying the engineering principles and the maths to the equipment to really understand what it's doing, to the raw materials, to the feeds, to create the products that we call the food. And where are we on that scale? Early days. There's a few people, few individuals in this room even, who have been working hard trying to get this information across. But we're screaming in the wind a lot of the time, because people look at it, they get excited because they see it can be done, but then they choose not to do it themselves once they get home. That's the problem. And until we can encourage enough people in industry to really apply the principles rigidly, robustly, consistently, then the industry will really improve and start to do the right things. Okay.
Next, we have another Jason Stokes. Your question?
Hi, Dennis. Sorry I can't be there to everyone. Well done, Jordan, and the team putting this together. It's always great listening to you, and you've mentioned shear rheology a lot. What about extensional rheology? How big a role does that play in creating lots of structure in terms of the lamellar sheets that you're trying to create with plant-based foods? As I see that there's a lot of extension in the process, especially, at the dye stage. What are your thoughts on extensional rheology?
It certainly does have a role to play. That's, as I touched on in my talk, changing the shape of the die changes the behavior of the melt. Change the pitch, the angle of the taper in a die, and you change the way the product expands, the shape that it forms. This is extensional rheology at work. That's what you're doing. We just don't understand it for what it is. We just know that a 33-degree taper is better than a 45. We don't know quite why, but it works, so just keep doing it. But actually what we're doing when we change the shape of a die, we are playing with the extensional rheology of the melt that we have formed within the screw. That's exactly what you're doing. So you're absolutely right, using lots of engineering words, lamellar flow and all these really good things, and that's great. That's how we should talk as engineers, because we're handling a fluid dynamic system. And until you get that right and understand it and recognize it for what it is, you won't really go the next step. You can't fly to the moon unless you understand some fluid dynamics and all the rest of it. We want to go to the moon. We want to feed ourselves into the future. We want to make all these great products. The pathway is the science. That's why we're here. That's how we have to learn to think and do. And we'll get there. And we have to. We don't have a choice. So, yes, good to see you thinking the right way. We'll have many more good conversations.
Any further questions? So, if not, we'll proceed to the next session.
I'd like to take the opportunity to welcome Gaetan Challery from our gold sponsor, Clickstraw, and he's also joined by his colleague, Louison Duclos, who's also in the room. Take the opportunity to accost these guys whenever you can, see if you can get a good deal out of them. That's what they're here for, okay? They're here to talk to us about shaping the future of snacking and with twin screw extrusion technology. And as you would have gleaned from my brief talk, these guys, or this company, has been involved in the technology for quite a while, so they might have something good to say.
Good morning, everyone. Thank you, Dennis, for the opportunity to talk. Thank you, all of you, also for attending today. It's great to see such an attendance, either on-site or online. It's a great pleasure to have the opportunity to talk to you about two presentations today, one about snacking and one on alternative proteins later today. I would like to take the opportunity also to thank the CSIRO for organizing and hosting this amazing event. Thank you very much. And it has also always been a pleasure to collaborate with you over the years. So a bit about ourselves. My name is Gaetan Challery. I work for Clickstraw as Pacific Sales Manager. I've been working for them for the last 3 years now, and I'm very pleased to be joined today by Louison Duclos, our Asia Pacific process expert, process engineer. He's usually based in Singapore, but we have the chance to have him today. So yeah, I will talk. If you allow me, I would like to introduce a bit more Klextrol. So who are we, what we do. So Klextrol, it's a French company. We are headquartered in Firminy. It's a French city not far from Lyon, about 1 hour for those who are familiar with the French geography. This is where we have our headquarters, our pilot plant. Yeah, the color is not very highlighted in. Okay. Perfect. I will go further into details. So yeah, the pilot plant, the headquarters, and our factory are in France. So in Firminy, it's yeah, one of the spot that you have, the pin that you have in the middle. It's a bit more than 300 employees worldwide. So we have developed and built a network of subsidiaries and offices around the world, business units in the America, business unit in Europe and Africa, and one in Asia Pacific, so where we work with Louison. Our engineering hub in Asia, to get as close as possible to our network here, is in Vietnam. We have automation, project management, electrical expertise over there. And I work in Melbourne with another guy who is in charge of the after-sales maintenance and everything that we can do on site here. So yeah, 12 locations, as I mentioned, 2 pilot plants, one in France at our headquarters and one in Tampa in the US. Both are full furnished with all the equipment to make R&D, to develop new product, new recipe, either in-house for our process knowledge, or also to advise, guide, and assist our network and contacts to develop their own product, basically. The process is something that we really focus on. It's a part of our supply. It's a part of our the services that we provide. And talking about the supply, what we do, maybe it's the first thing I should have talked about. We design, manufacture, and supply twin screw processing lines, processing solutions for food and feed and other applications, but today's topic is food and feed. Those lines integrate twin screw extruders, dryers, and other ancillaries that are required to operate the line. And we also, as I mentioned, provide services such as after sales, wear part supply, and also process assistance on site or remotely. In terms of turnover, last year we made 85 million euros, which is about 150 million of Australian dollars at the moment with the exchange rate, with 80% of it made abroad. So we are very proud of it. So through the network, subsidiary and offices network I mentioned earlier. Well, there is no map and okay. So in terms of application, as I mentioned, we are in the human food. So basically food applications such as plant-based protein, snacks, cereals, breakfast, ingredients, and so on. We also provide equipment for the animal feed section. So cat feed, pet food, cat, dog, fish, shrimps, anything which is related to feeding. In terms of application, we also provide equipment for the biomass. So it is a booming application today, which is not related with food at all. So in that we have biomass treatment into valuable products, treatment of wood chip, for instance, for hortifiber, treatment of cotton for security paper, such as banknotes, not here in Australia because it's plastic, but other part of the world it's made with us. Also for passport, it's also an application we do. And other industries such as the cosmetic, defense, plastic and recycling, chemistry, which is specific project that we are always happy to discuss about. So what is a twin screw extruder? Denise gave you a very deep preliminary explication, but for us, an extruder, it looks like that. So it is basically a frame with the power unit on the right, which is composed of the motor with one shaft, power shaft at the end. It is after coupled with the gearbox, which transformed the one shaft power into two shaft power, which made us the twin screw active part on the left hand side. So yeah, your left hand side. So it's basically two shafts with a screw profile mounted on it, enclosed within a barrel assembly. So as you can see, we have a few details here, and the feeding section on the top, yeah, to infeed the barrel assembly and the screw elements. It is also included with a water pump, so we inject water for the process into the barrel assembly directly. So it is a continuous process, meaning that everything that you infeed, it goes out at the end. The active part, as I mentioned, it's composed of the barrel modules. So it is a complete set to make the barrel assembly. And also the screw elements, which are mounted on the two shafts. So it is co-rotating shaft, intermeshing screws. It has the benefit of being self-cleaning and positive displacement pumps. So it means that everything that you infeed will be conveying within the barrel assembly with different characteristics being conveyed, being mixed, being shared throughout the process. It has a precise control of the energy input with mechanical energy. So through the sharing which is provided by the screw profile, it increases the energy, so it makes the raw materials heated. And the thermal energy through the heat transfer with barrel. I will explain a bit more that on one of the next slides. To focus on the active part, the screw elements, so it looks like that. As you can see, we have a spline shaft here with a mounted screw on it. So depending on what you require for your process, we have different kind of screw elements. So for conveying, sharing, mixing, and much more. So it is modular and continuous, meaning that we definitely can change the screw profile when it is relevant to enhance the process, to change recipes or whatever reason. So it is not fixed. You can always change it. We have a wide range of screw profiles designed for different kind of application on the raw materials and the melt. Some are more for thermochemical reason. Some are more for sharing reason, conveying reason, depending on what you require. So great mixing and sharing, which is this time depends of the geometry, the flight, the flap of the screws, and the various metallurgies. So this time it's depending of the process and the raw material you use to limit the wear, to limit all kind of wear. It's very useful to have sometime more hard screw profile. So the barrel temperature, our barrels are thermoregulated, meaning that we keep it cool or we can also heat them. So for keeping them cool, we have a cooling circuit, as it is representing on the left-hand side. So with high flow of cold water coming from -5 degrees with antifreeze, so it is the minimum that we accept. The pressure bar, 5 to 6 bar, and it is automatically controlled by solenoid valves. On the other side, when it comes to heating, we also have technology with resistance heaters. It looks like what you have on the right-hand side. It is a continuous temperature between 300 degrees to 500 degrees. Protection degrees IP55, so no leaks. Easy to install, as you can see. It's very easy to install and designed suitable for all type of barrels, so it's like a clamp. We provide drying technologies, so two kinds. The Evolum, which is our value options. It is dedicated for uncoated product because we cannot clean it with water. And we have the Evolum Plus, which is our latest technology. It is this time dedicated. It is extended to coating with sugar because it's cleaning with water. In terms of capacity, for this one we are about around 300 to nearly 4 tons per hour. It is modular design, meaning that we have modules, drying modules that we can add and remove to increase the length of the equipment. Coating unit, so it's one part of the ancillaries that we have. It is for coat the product with sugar or salty coating if you want cereals or snacks. This is a production line of snacking, so it looks like that, basically from 200 to a bit more than 1 ton 5 kg. High flexibility to run different kind of snacking, capable of producing different shapes and formats, adjustable processing to achieve diverse texture. So this is my colleague here who is in charge of developing new texture and new shapes. Easily customizable and suitable for both standard and innovation formulation. And if we focus on the market for snacking, this is what we research. So for the Australian market, we are in 2025 at the moment, and we expect it to increase by 1.4% until 230. Coming up to nearly 4 billion for global snack by 234. And for extruded snack, we expect in 2024, we expect, as I mentioned, 1.4% of augmentation until 230. I will leave the floor to my colleague to speak about process now and more about snacking. Thank you very much.
Good morning. I try to make it quick. Gaëtan likes to talk. So yeah, I'm Louison. I'm based in Singapore usually. So I'm the Clextrol APAC process engineer. So I will focus on the product here. So I will talk about the direct expanded snack. So as Dennis mentioned, those snacks are made directly at the end of the extruder. So we have the direct expansion. So just to focus, so here you can see the standard, like the regular shape. I don't want to spoil, but that's 80% of the machine we sell are made for those ones. So we try to innovate all the time. I will talk about that. But people really like those shapes because that's the standard that we see on our supermarkets. So if we have a look at those shapes, we have the balls, the curves, and the rings. That's the basics one. And if we have a look at the recipe, so most of the time we use the corn grits because we know that the corn grits is having really great expansion. And then we'll add some ingredients. So here you can see salt, fibers, and calcium carbonate. The aim of those ingredients is to limitate this expansion, to reduce the size of the bubbles inside our product, and also to bring like a good color, good taste, which is also really important for our customers. Okay, so here you can see also many shapes that we can make. So our catalog is really big, but as I said, I would say 80% is made of curves, rings, and balls, like the regular one. But it's also important to innovate and to show our customers that we can do like new stuff and also like industrial, like, I don't know, for Halloween, for example, they make like pumpkin face or stuff like that. So it's also important to match what the customer is expecting. So here is a small overview. So you can see the grids, the chipstick, the smiley, the fans. We also produce some co-extruded products. Our catalog is really big. So I will focus on the trends because when we want to innovate, it's good to innovate, but we have to be aware about what is my customer expecting from me. I don't want to like innovate just to innovate. So it's really important to match, of course, if we want to sell our product, to be sure what the customer is expecting. So if we have a look at the trends, so those ones are made for Australia, but in the developed countries, they are almost the same everywhere. So the first one would be the health conscious preferences, meaning like people want to eat more healthy. Premiumization, meaning like good packaging, like premium packaging, luxury packaging, black with gold, and so on. Convenient formats, formats to be able to share, and also the individual. We reduced, like in the past, in France, we reduced like people were buying less and less individual formats because of the sustainability, and now it's becoming more trendy again. So the format is also really important. The sustainability, trying to buy like new packaging made from new raw materials, recyclable packaging is really important. Digital channel, it can be like Deliveroo, Uber Eats, and so on, is becoming also really trendy. The click and collect also, for example, and also we focus on the taste all the time to make sure like the people will enjoy the snack we will provide them. So if we have a look at the healthy snack, so the extrusion is allowing us to use many different kind of raw materials to make healthy snack. So if you remember the slide, the previous slide, is the number one trend, like the healthy food. So that's why we try to innovate in this way. So if we focus on the healthy snack, the aim is to provide like good nutrition value inside the snack, protein, fibers, and so on. We can also create new shape, we give natural color, and also we can also work on the texture to try to have something more different. So if we have a look at the recipe here, so to make healthy snack, we usually use the legumes. It can be grits, it can be proteins, it can be flours, and usually we mix that with another kind of starch. It can be, usually it's rice, but it can also be corn, that we know that it's having like a great expansion, and then the legume will reduce a little bit this expansion. So we tried, over the past years, we tried to make some new kind of recipe. So we tried, as you can see on the screen, we tried the pea flours, the lentil flours, the blue corn, the sorghum. So we get really different results, and then we have also to change the parameters on the extrusion, meaning like changing the screw profile to get the right texture, changing the water flow also, changing the temperature and so on to get the right texture and to get the like what the customer is expecting, like something crunchy, something melting in mouth. So that's also really really important. And not all the starch or the raw materials are behaving the same on the extruder. So that's also really important. You cannot just put something in the extruder and say, okay, I will get something really nice. It's a long work to find the good parameters. So this is an example of what we can do matching the shape and the recipe for healthy snack. So this one is really trendy. We sell a lot of this one. So that's the pea pods. So the pea pods is made with green pea flour and rice flour. And then we gave this special shape that makes really appealing on the market. And usually it's also coated later on. We also have the multigrain wavy chips, which is also really trendy because it's high in fibers. I will not talk too much about this one, but it's really, really interesting as well. It's a product that we saw on the market for ages, and it's working really well again. Baby snacks also is really like becoming really trendy. We have more and more people asking us about this. So the aim is to have something really melting in mouth for the babies. And then it's also coated. It can be oil-based coating or sweet coating. So this is also a trend that we see those days. And sorry, I'm trying to make it fast to finish on time. So also, what is really important with the extrusion and the great advantages of using this technology is that we can improve our recipe. This is a great example. It was exactly the same in France. So now you have the L-star rating on the packaging, meaning that the industrial must put this label on the packaging to make people know like the impact of this product on the health. Meaning that for good nutritional value, for example fibers, your product will win points, and for bad nutritional stuff, it will lose points. For example, if you have high fibers in your product, you will have a great rate. If you have a lot of sugar, you will decrease the rates. And then here we have what we call the Choco Cups. So the version 1, it was the one on the market for ages, and then the health rating star was only 3 stars. And the industrial came to us to improve this. And thanks to extrusion, we were able to increase the fiber, decrease the sugar, a little bit, like divide by 2 actually, decrease also the salt to try to win some stars on this L-star rating system, which make also a really big importance on the marketing side. So by changing the parameters, we change the recipe, and by changing the parameters, we reach the same final product. And this is the last slide. So this one is the crisp. So this one is also becoming really, really trendy because with the extrusion, we can make those crisps, which are made usually with 80% of concentrate. So it can be soy, it can be pea. And then we mix it with starch to have a great expansion. And there's those small extruded snack are used in other applications. So this one is like cereal balls, but it can be also included in muesli, ready-to-eat muesli, for example. And this is also becoming more and more trendy, and industrial come to us to perform some trials like more often than in the past. So just to conclude on this, on the process side, we can see that extrusion allows us to work, like thanks to be able to move, to change all the parameters, we're able to work on many different recipes, many different shapes, that makes us the possibility to improve our recipe and to develop also new innovation, to be able to match what the customer is expecting in terms of trends. So here it was more focused on the L side. Okay, so I'm done. Thanks a lot for your attention. And if you have any question, I will be happy to answer it.
Thank you so much, Gaetan and Luzon. Thank you for a lovely presentation. Luckily, I didn't talk too much, so you had a bit of extra time. Are there any particular questions in the room? No? Okay, on that hand, then our friend Keith from the... Oh, sorry, we have got a question. My apologies. Osvaldo.
Yeah, hello. Yeah,
morning, how
good
are you?
presentation. I have a question because, you know, when you do the graph showing how it's going to be the market, why in 2028 you are seeing a reduction in the snacks?
I give the mic to Gaetan for this one.
I mean, who got that information? Because it's linking with Dennis was saying, you know, sometimes it's going down, but I would like to know who is predicting that.
Yes, so it's predicting by your marketing department. It's about cycling market. So maybe crises, maybe regulations also that could arrive in Australia. So it's just an expectation, a theory. Nothing is really set up at the moment. It just to expect everything. So
what we can do ourselves to, I mean, go against that decrease, you know, because we are trying to make better product, you know, you mentioned it.
Yeah, I totally understand. What we can do, I don't have the answer on my own, to be honest. So it will be, market evolutions, avoid transport, any transport issues, for instance, keep importations, things like that. We don't really have the answer.
Thank you.
Thank you.
Are there any other questions in the room? Yep, one more.
Good morning, everyone. My question is with regards to the co-rotating screw. Why do Klextrol offer that, and what are the advantages, if there are any, with the counter rotating screw?
So yeah, for the co-rotating screws, what we know, so we have many different applications, and we know that having the screw going in the same way allows us to have like a great shearing, also like a great, we have an application which is really relevant for this one, is like the flavor encapsulation, meaning that you will, if you open a tea bag, you will find some small sugar matrix that is encapsulating the flavor. So this process is also made on our machine, meaning that you put a sugar and then you will create an emulsion with like an all-base flavor. And the aim is to be able to have the same amount of flavor in each small bubbles of sugar. And then with the, like having the screw going in the same way, we have like a great shearing, but also great mixing. So we know that we have a really great dispersion inside the extruder, meaning that also, so for flavor encapsulation, it's really important, but also for snacks, it means that you will have the same, I would say, through your process, you will have exactly the same texture all along, and then you will create like a really great, like in the intermeshing zone, the mechanical energy bring into the machine will be different if you have like a co-rotating or contra-rotating screw. And we know that with the co-rotating screw for all of our application, it's the best. I mean, it's the best way to produce this one. Yeah. Maybe Dennis, you know more than me on this one.
So, the co-rotating twin is the common machine used in food processing, no doubt. As far as emulsification of oils and fats into melts, my experience is that the counter-rotating twin, if it's configured correctly, can do a better job, but it doesn't do as good a job at melting. So it's a case of understanding what is the product you're trying to make. So every different screw geometry, every different screw extruder option has positives and negatives, as I highlighted briefly in my slide. There's no such thing as a perfect extruder. Don't worry about the salesman. There is an extruder, and it can be, if it's configured appropriately, it can do a good job. Doesn't mean it's the perfect job. It will do an acceptable job. And we're here to feed people. We're not here to make perfection. All right? It's delivering products in good functional products in an acceptable format. That's our job. Doesn't mean perfection. Yeah. But they do build some decent machines. I'll give you that. I think there was one question from overseas. I believe Keith wants to ask a question again. This is your last one, Keith. You already had your share.
I do apologise. Thanks,
So you
Dennis.
should.
Thanks for that. Yeah, Lewis and Gaetan, thank you very much for a great presentation. Gaetan, I didn't recognise you with your new beard, so very, very fetching, very nice. My question is visiting clients' sites this year, troubleshooting on some of the problems. The majority of the issues have been around preconditioning. And I have to say, probably one of the best preconditioners was actually a Klextrol, which is a twin shaft top loaded, which allows you to do dead stops. I'm hoping everybody in the audience do dead stops when they're testing. My question is, I enjoyed your presentation, but there are many snacks which are 3G snacks. And I wanted to ask you, how important is preconditioning for both either 2G snacks or 3G snacks in your experience?
So usually at Klextrol we do only direct expanded snack. So we don't use the preconditioning for snacks. The only thing that we use, the only application I would say that we use the preconditioner for, like, is the flakes. So we have like also flakes. So it's a long machine, and you need to pre-cook your starch in the preconditioner to make sure you will not expand also at the end of the machine. So you need to cook your starch without expanding at the end, because you will, like, the aim of flakes is not to expand like a snack. So that's why we use the preconditioner. But mainly we use the preconditioning for fish feed and pet food to make sure, like, we will increase as much as possible the digestibility of the proteins and the starch for like the fish and also the pets. But yeah, for snacks we don't use that much, only for flakes.
Okay, thank you. That's great. Thanks, Dennis.
You're welcome, Keith. Thank you for the question. On that note, I'll say thank you.
Thank you very much,
both of you.
Thank you.
And I'd now like to introduce our next speaker. Now, I'm just wondering, I was going to read out your title, but doesn't have it. But anyway, Dr. Azad Emin, here he is.
Yeah,
it is the, yeah.
Can I use the last
Welcome.
30 minutes?
You can have it all.
Okay.
If they don't want to have any morning tea, you can have it. You can have that too. No problem.
Yes, good. So, good morning, everybody. How are you? I see some familiar faces. It's nice, and some to be. This is the one that's supposed to change the things, right?
The green button
Green button. Perfect. Actually, I'm going to just repeat what Dennis said. So I'm trying to just use different words so it's not getting boring because he already said many things about what I'm going to talk about. The session is about future food production. So the question is actually, what should we expect from future? I think that's one big question. What we definitely know today, I think you all will agree about that one, that food industry is facing a major challenge. In parentheses, an opportunity in shifting to sustainable food production, but I see that it's rather more challenge than opportunity, obviously. We have seen the last 3 years that it has been very challenging also for the industry on those new topics, new innovation topics. And when you talk about, or when we need to talk about sustainable food production, it's a big umbrella, and under that there are many topics actually. When it comes to production or food engineering related topics, there are 3 big topics that we can talk about. One of them is alternative proteins. I think there are many presentations also today about that one, so I don't need to mention anything about it. The second one is a whole food, no waste. I think there is one product in the bags that is related to that topic, about using side streams. And the third one is process intensification. So those 3 topics are going to probably keep us quite busy during the upcoming years. That's what we see right now, at least. And when you try to evaluate all the available technologies that we have access to, so to say, extrusion actually seems to be the key technology when it comes to that one. I don't see any other technology which is coming any closer to extrusion, and I am open for any challenge about that one and happy to discuss about that one. And I will try to give you a bit of examples. It's the things that you already know, but sometimes it's nice to put the things into context just to find, just to have the real good motivation and also the driving force for our research. I will start about process intensification. When it comes to process intensification, it's about actually producing the same product, but simply adapting the process in such that it becomes more efficient. So we need less resources, but products stay typically same, so to say. The best example when it comes to extrusion is the pasta production. I like this example always to give this example because this is one big success story about process intensification. If you check some historical photos on Google, you will see how the pasta was originally produced. There were like big presses. They were making a dough manually, putting into those presses, and people were just really pressing those things. Then afterwards, there were some machines, but not a continuous in a way. And extrusion made it happen, and in a great way. So they made the cost drastically reduced. So that was the goal, obviously. But then they standardized, or we standardized those products, and then increase the versatility of those products. So it seems like we can intensify the process with extrusion in a strong way, take something local, traditional, keep that essence of that product, and also diversify it and just launch it in the global level. And you can find pasta everywhere in the world, very accessible. So it's a great example, actually, how the things should be done when it comes to process intensification by extrusion. Another example is pet food. It's another success story, actually. The pet food as it is today is made through the process intensification by extrusion. Yeah, so that's the reason actually why it's such a big industry, such a successful industry. Here again, you see this nice AI photo, all those different dry products, but they're also like wet products. You can extrude almost anything actually for this purpose. You can also find almost any type of products on the market used by extrusion. Again, here it's all about process intensification, in producing those products in a cost-effective way. And extrusion has been proven to be very successful for this one. But I've been working in this field since about 20 years. We got a lot of projects also about process intensification, but you don't see those publications, obviously, because they are trade secrets. So companies doesn't want to talk about these things, but some of them were published. There is like ice cream production. I think this was done at the ETH Zurich. There's a mozzarella production by using extruder. One of the biggest extruders that I know is used for chocolate production. But we also had a project about cacao butter production. So it's a nice one because normally cacao nibs are actually transported to Europe, yeah, typically, and because you need the huge machines, right? Separate machines for alkalization, so you get that dark, nice cacao color. There's also like a milling, roasting, pressing, like big machines normally, yeah? What we did was we got the extruder, put a filter on the bottom of extruder, simple, almost like an oil expeller, but a bit more reduced one. So you get nicely, and you could also add alkali solution also during the extrusion. So you can change the color, you can also roast it, you can press the cacao out of it, and you don't even need to do it in Europe, right? So you can just put it next to the farmers. Yeah, so that shows the strength of the extrusion towards that process intensification. So it has been already proven to be very successful for that one, but that won't be a topic. When we go to the second one, whole food, no waste, this is going to be highly relevant. We all know that food industry is mainly driven by refined ingredients. This has been a good thing at the beginning because you get all those standardized ingredients, but all the goodies, all those typically like dietary fibers, proteins, a lot of bioactive materials actually are left behind, unused when you think about it. And when you think about all those commodity crises happening already in different parts of the world, but it can also happen very quickly next year, the year after also in this region, hope not, but we expect that. We need to use obviously those ingredients in a more efficient way, right? And another nice AI photo, but it shows actually what's possible with extruder. Anybody who is working with extruder knows that typically, not always, what you put inside is coming out. 90%, I would say, 95%, right? And depending on the applied thermal and mechanical stresses, we can change the structure of that material, always. Yeah? And at the end, we get some kind of texture as well. So, and you can get ingredients that you can functionalize in a way that we can have a certain techno-functional properties, better solubility maybe, better water absorption, gelling behavior, so this type of activities, but also we can give them a texture. And we know since from the 80s, beginning of 80s, there are many studies in this field actually using those side streams. I know like there's a brewer spent grain, so what's from beer production, for instance, or apple pomace from apple juice production, which is left behind. Typically it's even more valuable than actual apple juice itself, but left behind. Those things can be extruded. It's not necessarily extruded as it is. That's the strength of the extruder. We can always blend the materials, right? So we can mix the things and adjust the matrix, and at the end we can get a certain texture and certain functionality. This is very important information, because if you know how to deal with extruder, that means you can almost extrude any type of products actually that's necessary to be extruded, so to say. And of course, alternative proteins. I think this is a very popular topic. No need to tell a lot, but this shows nicely that these three topics are not necessarily separate. It can be also done together. Yeah. So, and the proteins are one of them actually. You can extrude almost any type of proteins. This is a fact, and you can get all the whole protein flours, like soy, for instance, and extrude it as well. And what we can do is we can use extruder as a reactor, so we can end up with producing some kind of like dry extrudate, which can be then used in like mixed products, like sausages or burgers, or of course those whole cut products. This is also a very important one, just to repeat it again. We all know this, but it's nice to just sometimes repeat it. It's a very complex texture which we create also with this process. So it shows actually what is possible. Yeah? So I think this is a very, very important part to think about it, that we can use extrusion to design very different products successfully, but still there is not enough research, in my opinion, that there's not strong progress in this field, that I am struggling to understand why it's like that. My opinion is probably it's 100 years old, and people assume that everything has been done already. Yeah? And that's a big wrong statement, yeah, or assumption, so to say. But it is yet still a black box. We know it. Yeah, we hear about it all the time, and it is the truth. And therefore, we have that slow and inefficient progress. What's meant with that one is you can get a small extruder if you have enough people, a bit of money, and raw materials. You will really end up with a good product. I promise. It's always like that. The challenge is when you try to scale it up, then typically we fail. Yeah? And when you go to 200, 300, 400 kg per hour, you cannot just experiment every day 10 times. Yeah? Just cleaning the machine is like taking a whole day typically. Yeah? So that means we need to know, we need to not use small-scale extruder just to experiment freely. It is good. We shouldn't stop that one. But I think we need to use that small-scale extruder simply to have a better understanding of the process so we can transfer into the large-scale extruder. Meaning that actually we need to have a better mechanistic understanding of extrusion if you want to progress this technology in a targeted way. And I like to ask these questions always. You also ask the same question in one slide I saw. It's good. It's good to ask it all the time, because there is no one answer for all. But it's good to discuss what extrusion is. What we definitely know is that we have some certain kind of structure that we have inside the extruder that is, you don't apply extrusion, then you have a structure, but you have rather a structure which is continuously changing in this process. Yeah? And this is happening obviously as a function of those processing conditions. This can be a thermal stress profile, mechanical stress profile, as well as mixing characteristics. Yeah? So if you want to have a control on the structure, we need to have clear information about what those stress profiles inside the extruder are, how that changes are happening. And there are quite some work in that field, processing conditions, but there are still quite some open spaces. And the main work actually is done in the polymer industry, not in the food industry. Yeah? And one big topic that I realize is almost completely missing is the material properties. And that's the part actually linking the process conditions to structure. And it is amplified strongly. So if you have a certain structure, it is not the result of the process only, but it is part of the process. What I mean with this one is if you have let's say a certain raw material, just little fluctuation in the raw material, it is going to have a big impact because that will change the processing conditions. Processing conditions will change the structure, so it's kind of like an amplified effect during extrusion. That's what makes it quite difficult to deal with. Yeah? And if you want to solve this, we also need to take a look at the material properties. With material properties, of course, it's a very long list. But what I mean, or at least the three big topics in my opinion, is rheology, as you mentioned as well, reaction properties. So do I have any type of reaction? What type of reactions? When do they start? How they evolve? Yeah. And the third one is the phase properties. This is also the one topic which is almost never discussed somehow, but extremely important. When it comes to food biopolymers, we always have a multi-phase system. It's never one phase system. And you know, if you have proteins, they're not just protein molecules, there are also other phases, and depending on those phases and the rheological properties, we always have a different reaction. So we need to actually discuss these properties also in relation to each other. So when you look at this, this thing, in my opinion, this sums up the main questions of extrusion, obviously depending on the application. If it's expanded products, if it's pasta production, what we said, cacao production, the structure will change, but we definitely need to focus on processing conditions as well as the process material properties to be able to study the mechanistic the mechanisms which are responsible for those structural changes. You can ask, or you may ask, why there are not many studies when it comes to properties. You know, when you think about like a extrusion, we have like proteins, for instance. It's a good topic. There are also many presentations today. We don't even know how those proteins are behaving during extrusion, right? So if there's reactions, how they start, how they evolve. The main difficulty is if you want to analyze the properties, we need to have a defined extrusion-like conditions. And this cannot be somehow done by using extruder itself. We need to have some kind of extrusion-like conditions, but in a defined way. We want to keep the temperature constant, we want to keep the shear constant, and we want to track the changes in the inline way. You don't want to analyze just final structure or final properties, but you want to see how the things are changing along. And luckily, polymer industry also gave us a nice device about that one. I think this has been developed at the beginning of '90s, and when I discovered it, or when I found it, so to say, I was very happy. This is a closed cavity rheometer. It is a two-cone, so to say. You can put the polymer inside or biopolymer inside, like in our case, and it can apply constant shear and constant temperature, and it's a rheometer. Yeah? So it means that actually you can apply shear, and you can measure the response. So if there's any structural changes, typically it is reflected to the rheological properties, meaning that we get two key information directly: how the rheological properties are changing as a function of extrusion-like conditions, as well as the structural changes. At least there's some hints about that one. I will give you one example about that one. It's a vital wheat gluten. What we did here was we get the gluten, mix it with the water in a Thermomix, put it in a rheometer, close it, and apply a increasing temperature. I think it was 5 Kelvin per minute. And normally the viscosity of the matrix should continuously decrease as a function of temperature because the molecules are getting more mobile, obviously, unless there is a reaction. If there is a reaction, if there is some kind of network build-up, then you will see an increase. Yeah? And this is definitely the case. It is not a new information, right? So it's already known from bread making, etc. But the thing is, when it is happening. So we can analyze when it's starting. And you can see nicely, for instance, it's about 80 degrees Celsius. At these typical conditions, then you can see when it's happening. Yeah. Then you can see, of course, analyze the water effect of water or different proteins or different conditions, etc., etc. Yeah, this is what I already told about. And of course, we can also use this same approach to get information about the dynamics, because we don't only want to know when the reactions are starting, at which temperature, but how they're also evolving. Yeah? And for this, we can, of course, keep the temperature constant, keep the shear constant in the rheometer. And then in this case, you can see, again, how the network build-up is happening. So it's getting actually a stronger gel, so to say. In this case, you can see very, very quickly how it is increasing. This is in a shearless conditions, 120 degrees Celsius. And then when we change the temperature, 140 degrees Celsius, if you would analyze the last bit, you would say at 140 degrees Celsius, it becomes even less viscous, maybe. Yeah? But actually, what we see is it is increasing quite faster at the beginning, as expected, higher temperature, higher reaction rates. But then all those higher temperatures is also leading to some kind of decomposition reactions as well. Yeah? And this is showing nicely, actually, that we need some kind of inline measurements to see how the evolution is, not analyzing what's coming out of the extruder, but what's happening inside the extruder. Yeah? Another topic, the shear. The effect of shear has been discussed all the time. Right? Typically, we are using a specific mechanical energy input for this description. It's the integral value. It is, in my opinion, definitely not sufficient when it comes to understanding the shear. Also during extruder, when you're talking about like screw speed, etc., it's never decoupled from temperature. Yeah, so you do have an increased shear, yes, but you also have an increased temperature. So you never know what's the reason when it comes to scientific explanation of that conditions, right? So, and assuming that it's because of shear is a bit of oversimplification of the situation. And here, of course, we can change the shear as well. The first one on the top, 120 degrees Celsius, and the last one at 120 degrees Celsius. When you see the difference is only because of additional shear, you can see a dramatic effect of shear in this case. We see that reactions are taking happening faster, so to say, taking place faster, but also there's also decomposition reactions in this case happening. This is a very valuable information through a very simple measurements, right? So the main message in this case is actually, if we are trying to find a solution for those properties, there are already many methods available. Yeah? So we don't need to really develop ourselves methods, we just need to look for it. There's already quite enough ones. Yeah? And we can get quite some information about that one. Tomorrow in my talk, I will give a bit more examples about that one, also about the phase properties. Of course, when you're working with a certain mixture, and if you want to design it by using extruder, then we need to also understand how the conditions during the extruder are. Yeah? So we need to adapt the extruder in a way to create those conditions that we want to achieve. Yeah? Meaning that the processing conditions. And this was probably one of the biggest surprises during my extrusion research, the temperature measurements. Yeah? So this is obviously the most simple and most important value when it comes to extrusion. It's a thermomechanical treatment, and we need to at least have a clear information about temperature. We all agree, I guess, yeah? And what we know, obviously, is that temperature inside the extruder is not constant. So it's, you put something in the room temperature, typically, you apply, you mix it with the water at the beginning. This is just a exemplary presentation. And there is increase in temperature drastically in 20-25 seconds, yeah? So one sensor is not enough. There are extruders with multiple sensors. This is good. But the problem is those are thermocouples, and thermocouples are great methods as long as they are immersed in the material. Yeah, I don't want to finger point, but maybe in some point I need to finger point, because I have been explaining this since 10 years. Publication is not here. Yeah, and I think the food extrusion companies should, extruder companies should work on that one, right? Here is the measurements that we have done. It's 10 years exactly. Yeah, so this was for publication. You see here's how the thermocouple, this is mounted at the end of the extruder. Yeah, the classical one. How it measures temperature. Barrel temperature is 80 degrees Celsius. With increasing screw speed, this was a wheat flour. Of course, the temperature is increasing, higher viscous dissipation, etc. We put there an infrared sensor, house developed, and we have measured the temperature. The infrared sensor is measuring what it sees and not what's around. Yeah? Thermocouples are getting what's the heat transfer is allowing it to go inside. Of course, they are not mounted into the material. The tip is a bit, yeah, just a bit in extruders. And I work with all type of extruders available on the market, right? And there's a huge difference about these ones. You know, I have a fellow PhD students or colleagues who have been working on modeling of the proteins or bioactives, etc. People were struggling, right? For 5 years. You want to have questions already? Yes, please.
So if I understand you correctly,
Yeah.
then the thermometer does not touch the dough.
It does, but not sufficiently.
Ah, okay.
Yeah.
So that's stupid because I come from the meat industry.
Yeah.
And our biggest concern is that the thermometer in a bowl cutter is always touching the dough, so we have always the constant readings.
Yes, yes, we do have as well, but there is a metal casing of the thermocouples, and that metal casing is in the barrel, and that barrel, just the tip of that metal casing is in the material, yeah? And we repeated these measurements also by simply putting thermocouples into the material, yeah? And we just also verified these results that we measured with the infrared sensor, and we have seen a drastic difference, definitely, yeah? So meaning that the measurements that you do with your extruder, I don't want to say 100%, but 90% it's false, yeah? And this is a big difference. And this can be, depending on extruder, up to 40 degrees Celsius, 50 degrees Celsius difference, huge differences. And think about actually when you're working with a small scale extruder, you design everything, and you want to transfer to a large scale extruder. This difference will be even bigger, you know, because the extruder channel is bigger, yeah? So you just struggle, yeah, because we cannot measure the temperature. Yeah, I don't want to go into too much detail about that one, but let's get a bit of deeper on that one. That's already a problem, but actually what we have here is we have screws, and screws are obviously applying a viscous dissipation. You mentioned that the shear is the main factor, but shear is not homogeneously distributed. At the tip of the screws, we have the hot spots, and those hot spots cannot be measured by using thermocouples. They're having typically 1 Hertz, so 1 measurement per second measurement time, so it gives you a temperature of the mixture actually. But what you will expect from screws rotating is like hotspots increasing and decreasing, something like a nice little one, yeah, some measurements. And when we use the infrared sensors, we have seen this effect indeed. Here you can see the 180 degrees RPM, not strong one, 300 a higher one, 500 even higher one. Of course, we have a higher viscous dissipation, and there is strong variation of, in this case, 12 degrees Celsius. This wasn't a 25 millimeter extruder. If you transfer it to like a 60, 63, it will be even more dramatic, yeah? And if you're thinking about working about the aroma encapsulation, cacao, yeah, some roasting, some proteins, this is something that we need to control. If there's a 20, 30 degrees difference in the tip of the screws, it is a problem if you don't control it, and if you just measure the mix, which is obviously also wrong, yeah, so we have a big struggle. Yeah? So what I'm trying to say is, yes, extruder is black box, but the solution is not that complicated in some cases. Yeah? We can make our lives significantly easier. And here, important thing is, again, we do have those hotspots, of course, but we don't know what is the amount of material that's going to experience those things, because you have a channel, materials going through these things, typically 20, 25 seconds in a large-scale extruder if you go to really high throughput, and some of that material is not going to experience those maxima, yeah? And you need to have an information about the distribution, yeah? And for distribution, only method that I know at least is the CFD, so computational fluid dynamic simulations, but 20 years ago it was a bit of like, oh wow, yeah, it's like fancy. Nowadays it's just standard. You can really get those codes. They are very well structured. You have instructions. You can get just anybody who doesn't even have an idea about the CFD and can start working on that one. The only thing that you need is a good material properties, rheological properties, to get a good results about the core. Of course, it has limitations, but here's the thing: you can keep the rheological properties constant. Then you can adjust the screw design. You can change the extruder design. So we don't need to actually just work with the process parameters, but we can also adapt the extruder itself depending on our needs, right? So this is not happening. You will always hear the same extruder, same things, just process parameters, but actually, in my opinion, tomorrow also I will talk about that one. We need to design extruders for our needs, in my opinion, yeah? And for this, we can use the CFD. It gives us a nice distribution. If we have good rheological properties, then we can track like massless, volumeless particles, like 10,000, 20,000. Then we can track what is the temperature that they are experiencing inside the extruder, and we can get a nice distribution of the stress along those particles. And these methods are standard. It is not like really fancy stuff. They're already there. You need to get the license, obviously, but universities typically already have those licenses. So back to this one. If we want to have a mechanistic understanding, about the structural changes, we need to have a better understanding on those processing conditions as well as those material properties. Yeah, and we need to not get one value. We need to have an information about those dynamics. And I think there are quite some methods already available on the market. We just need to go grab them, test them, and apply them. And I'm pretty sure, and I can just encourage you, that the effect is drastic. The control that we gain on the extruder by using those methods is really significant. Yeah, and it is not that black box, maybe dark gray box. Yeah, and these methods, those methods which are leading to mechanistic analysis, it's not something that we can use only to publish papers and make a nice academic research. My personal opinion, this is definitely necessary for innovation as well as for the production, for the operational excellence. So it is not like something that scientists should do, publish some papers or whatever. This is something really very, very central aspect of this process. If you want to bring those 3 topics forward, we established a company about 3 years ago, Nextnoa, that I've been working on. And this is mainly what we have been focusing on, adapting those methods, having a better accessibility to extrusion, and using it hopefully in a more targeted way for innovation and operational excellence. Yep. And with this one, I think I'm done. Thank you very much.
Thank you so much, Azad. That was an excellent talk. I'll summarise it all by saying something I say all the time in my training courses. The barrel temperature is not the product temperature. Okay? Get it in your heads. So, thank you. Are there any online questions? No online questions. Any questions in the room? Oh, take it back. Of course there is an online question.
Jason.
Okay.
Thanks for your talk. Just a question about the closed cavity rheometer, because you showed G prime, but you were referring to shear rate. I just wanted to clarify whether that was a pre-shear that you applied, or is that actually meant to be frequency? Are these linear viscoelastic measurements? I think I read cavities mainly for G prime data, so is it just linear, or can you do large amplitude dissolution shear? And can you do shear? And I was just a bit confused because you were referring to centrifugal seconds and different things. So can you clarify that?
Yeah, sure. You can do more or less all type of measurements actually that I know from a rheometer. So you can do, what we do is we take that closed cavity rheometer, we use it to simulate extrusion-like conditions, then perform rheological properties. Yeah, and there you can use actual oscillatory measurements. And now we have developed also in cooperation with the Padayachee from Germany. So if you want to get more information about that one, you can pass me an email, where we can also rotate it. Yeah, so we can get a shear viscosity, but we can also make a nonlinear rheology, large deformation, small deformation, any classical rheological measurements that you can imagine actually, and even more. So, and those guys that we're working with are also open for further improvements. So if you want to put a Raman spectroscopy or whatever inside, we can also do that.
And what about the bandaging condition on the edge? Because you don't have an air interface, but you've got a wall there now because it's closed. Does that change your rheological properties much?
Yeah,
Do you know
yeah.
how that affects?
Of course, everything changes the rheological properties. We did some simulations about the wall effects. It was very, very insignificant in comparison to the information that we get. Because think about it, we are working with the highly viscous matrices, right? So the effect of the walls is not that strong as in let's say, in the watery phases. Because in the watery phases, that affects the internal flow. But in our case, we're working with the very highly viscous matrices, and the wall effect is actually, I wouldn't say negligible, but it doesn't affect the outcome that we have.
Thanks.
Welcome.
I'd just like to make a comment. The whole objective of extrusion is to have a change in the rheological properties. We're all focused on trying to measure it. That's fine for the raw material, but what is actually happening in the extruder is an evolution of the rheological properties as dictated by the screw speed and the geometry of every individual element along the way. So it's not one viscosity, it's a million viscosities over time within the barrel volume. That's what we're trying to capture. So it's not going to be a simple evolution and a simple test. Don't look for single numbers. It's an evolving series of numbers. Yes.
Thank you very much, Azad. I like the idea of actually checking the actual temperature, because sometimes at the end of the extruder we get 95 degrees C, but we see expansion.
Yeah.
So that actually temperature obviously difference can explain why that's happening. My question is about the same sort of gap temperature between what we measure actually and what's the actual temperature in analytical techniques, like rheometers or the cavity rheometer that you showed in here. Do we have the same issues in our analytical techniques? And if so, do we need to actually do something about those as well?
A good question, yeah. We do, of course, yeah. It is always depending on the shear that we apply. If we go to a high shear, like a 500, 600, 700, then we will end up with a like extruder out of control with the heating. So there is always limitation. So you cannot simulate extrusion 100% because at the end you will end up with extruder, right? So, but yeah. So there's a cooling that we can use always to keep it. And you need to always figure out the range where you can keep the things constant, obviously. Yeah. But here's the thing, you can always keep the shear rate constant, you can keep the temperature constant, you can compare the different blends already. Yes, there is some heating, yes, there is some problems, but this is so much information that you can use already. I mean, like, we shouldn't get lost in the error analysis. It's important, but what we get at the end is already very, very valuable comparison of the materials that you cannot do by using extruder. Yeah.
Thank you. You mentioned using the leftover fiber and proteins from the extrusion for feed or food. My question was, like, in your experience, does the cost of increasing the palatability, acceptability, and the intake of that fiber, leftover fiber and protein, does it override the food sustainability benefits? Like, is it still cost effective like to increase the palatability of that feed? And is that cost much more than the sustainability benefit?
This is I cannot give it just an answer because it's, yeah, but what I can say is extrusion is very cheap production method. People always assume that it's a big machine and a high shear, but if you go to a high throughput, it's a very, very cheap machine. Yeah, so the production costs are very, very low, so to say. And depending, of course, the value that add into that production. When we work with the apple pomace, right? So we did the press cake from the apple production, apple juice production, we end up with at the end flour, apple pomace flour, let's say, which can lead to a gelling up to 1,000 times more than the original one. And of course, if you're going to use it for a specific application where it's not only for dietary fiber, but also for that functionality, then it is really, yeah, it's really worth it, so to say. Yeah, depends on what you want to achieve at the end. Yeah, there is no one answer, I think, to the question, I'm afraid.
Are there any other questions in the room? Oh, one more.
I'll just get Karsten to repeat his question for the online audience because they couldn't hear your question.
Okay.
It's a question about the thermometer. My question was, does the thermometer touch the dough all the time? Because, like I said, I come from the meat industry, and there you learn from day one in your apprenticeship, make sure the thermometers are working, and you have constant control of your thermometers when you make certain products.
Yeah, it touches the product. I mentioned it before. It just touches the tip of the metal casing. And think about like the housing, metal housing, and heat transfer is coming from everywhere, right? From the right and from left. What do I have right and left? I have the barrel, and there's a tip just looking out a bit. And also heat transfer there. So you just get the average. It is more the barrel temperature than the material temperature. And the solution is very simple. If you go there are companies in the polymer industry where they developed a nice sensor. So you just get it, and you can just screw it. So you just put the screws inside to the extruder, and you can just screw that thermocouple, and you just don't forget it at the end, and it's not that difficult, obviously, to just screw it back and get the screws out of it. So that's a very easy solution. Yeah.
And just in support of the work you just presented, some I've copied your work at the industrial level, and I have video of the oscillating temperature that really exists in a commercial extruder, a 15-tonne an hour extruder in Chile making aqua feed, and you can see the cyclic behaviour of the temperature. It's real. It's not just in the laboratory.
Yeah.
It happens in every extruder. It's what we call shear. Rub your hands together, they get hot. That's what happens locally with the rotation of the screw, locally at the wall for every bit of product. And so the product is a mixture of grossly overheated and slightly heated product all mixed together.
Yes.
It's not one product, it's a million products mixed into one. That is the reality of extrusion. Okay? So, thank you for the excellent presentation.
Thank you.
Sorry,
it's
last
time
question.
for everybody. Oh, we have one more question.
Sorry, I have a question. You mentioned about the importance of rheology model in the simulating the extrusion-like conditions, and you used the Bud-Carew model. What is your rationale and validation of choosing the correct rheological model in the simulation to make sure that it can reflect the real-life extrusion conditions?
Yeah, that needs another presentation probably to talk about because there's also, it is a difficult topic to choose that one. We need to discuss further what is flowing, what is not flowing, what is liquid-like, what is not liquid-like. The masses that we've been working on are viscoelastic systems, but the time that we have inside the extruder is very low. So we don't have any time for relaxation actually, so you typically can ignore. That's what I assume. You could typically ignore actual the viscoelastic properties and focus on the shear thinning behavior. And we didn't assume it, we just measure it. And those measurements were not with the CCR, they were with the inline rheometer actually. And you can see actually that the viscosity is decreasing with increasing shear. And by using a power law model, it was very easy to model it. I've used Bud-Carew because if you don't use it at the very low shear points, in simulation you always have them, it reaches infinity, right, in the power law model. So then you will have a trouble. And by using Bud-Carew, we just achieve some stability in the simulation. It doesn't affect the main flow, but just to achieve some stability by adding that plateau into the model synthetically, so to say.
Sorry, a follow-up question.
Yeah.
Like, is there any importance in considering the free flow or cavitation in the extruder, especially in the feeding section? Because the flow is the barrel is not completely full at all, and CFD they have a very challenges in handling that type of free flow surfaces. So how do you handle that type of situation?
Not with polyflow or ANSYS that we have been using, but they're already developing methods for that one. It is important part, especially when you want to get more information about the local residence time distribution. I didn't mention that one at all, but for that applications, to see actually how the use of different screw elements affect the residence time inside the extruder. So in which part, how long my material actually just stays for that applications, I think it is highly relevant, yes.
So thank you once again.
Yeah.
And a great way to polish off, and I guess we've all been saying the same thing. If you want to understand extrusion, you need to understand rheology and fluid dynamics. Otherwise, get a different job. Okay, it's really simple.
Before we go on the break, we're about to have morning tea now, so please enjoy some coffee and some snacks. But just for the next sessions, they're going to be back-to-back 15-minute time slots, and the presenters might take that full time period for their presentation. So if you have a question and we're out of time, there's a QR code on the front of your desk, so you can submit those questions to the presenters, and we'll email them and get a response from the presenters. And can the next set of presenters go see the audiovisual staff to load their presentations? Great. Everyone enjoy their morning tea. Thank you.
I'm probably the person in the room that knows the least about extrusion because I've just appeared in the food program at the start of July this year, and I have no background in food science. So don't ask me questions. But we're here today in the second session to talk about ingredient functionality and processing mechanisms for extruded products. And we have a slight change to the program in that the order has changed and Osvaldo will be speaking last. So this is not Osvaldo up here. And so I'd like to just introduce you to a good friend of mine. Sushil and I have worked on and off together over the years and crossed paths. And Sushil will be talking to you about structural changes of starch and protein at low and high temperature extrusion. Off you go, thanks.
Okay, so thank you, Crispin. So I hope everyone can listen me from the back as well, right? Good. So thank you, Daniel and Jordan, for this insightful Extrusion Symposium that I was looking for a long, long time. It happened. Hope we'll continue next year as well. Great. So today I'm going to talk about the structural change of starch and protein during low temperature and high temperature extrusion. I will not talk much about the starch at the high temperature because my colleague Oscar will be presenting that in the coming after me, but I will be much more focusing on the protein at the low and high temperature, right? We all talk about extrusion, and it has been discussed before by Dennis and other colleagues as well, that the mechanistic detail is very much missing on extrusion. Extrusion is looked as a black box, but you know, you can open the barrel, right? You can open the barrel and do some sort of testing as well. So I'll discuss about what the change of starch and protein at the low and high temperature over my 10-minute presentation. Okay, so this is the extruder. Everyone knows about it very well. If you feed the starch to the extruder, and then if you see here, there are different, now this is where this is going, you cannot see it, okay. So if you put the extruder and look at the different numbers over here, you can see number 20, number 1, number 2, number 3, number 4. There are different areas, and if you take the sample out from these areas and look on the starch properties at the high temperature, the temperature is shown on the barrel, and you can see that the starch molecular size has been changed, gradually changed from high to low. So what does it mean? It means the starch is sheared during extrusion. Okay, so this is a mazaca, means mazaca is a waxy starch. Waxy means starch that only has a higher amount of amylopectin, not the amylose. But if you look at the amylose are very less degraded during the extrusion, and the only portion that is degraded is the amylopectin. That is the one of the take-home message. The extrusion has much more effect on the branch molecule compared to the linear molecule, because the linear molecule can pass away the barrel shear, or the barrel temperature, or the pressure, and has a less effect on it, right? And I will show that in the graph as well. So you can basically see that the amylopectins are basically chopped at a different, but the helical amylose, they are much more resistance, probably due to formation of amylose lipid complex, or their flexible structures. So unflexible, or the blanch structures, are much shear-induced changes, or temperature and shear-induced changes compared to the linear molecule. That is the one take-home message. That's all for the starch now, and I'll leave the Oscar to talk much about it. Now let's go to the protein. So this is again the high temperature. I'm not talking about the low temperature now. Protein is you can say much more complex or much more simpler. Because why it is much more simpler is it doesn't have the hierarchical structures like the starch. Starch has a molecular, supramolecular, granular, and the different level of structures. The protein has primary, second, and tertiary, but it's not that complex like the starch. But another complexity of protein is it has a different amino acid. But if you look on the starch, it's only the polymer of glucose. It's much more easy on the starch to look at the molecular level, but the protein is much more complex. And here, what I have shown over here is two different types of the storage protein. The top one is what we call a leguminin protein, and the bottom one is called a vesicle protein, right? But when you talk about extrusion, you really need to understand what type of protein you have in the system. If you are talking about the mung bean is 100% vesicle protein. If you look at the pea or fava is a leguminin and vesicle-rich protein. Some has a higher leguminin percent, some has a higher vesicle percent. So without understanding what is leguminin, what is vesicle, what is the structures, the final product is a black box. So extrusion is not black box if you know the structures of your ingredients, right? Why it is important is the leguminin protein is a 6 hexamer, right? You can see the 6 molecule coming together, right? But the vesicle protein is a trimer. Is it 10 minutes? Yes. No. Oh my God, I was so scared. How 10 minutes fly so quickly? So vesicle is a trimer,
right? And the leguminin has a disulfide bond, and the vaseline have no disulfide bond. You know, disulfide bond are reactive bonds. They make a stronger network. But the gel hardness is not determined by the disulfide bond. Gel hardness is determined by the vaseline. So mung bean gel can be harder when you cool compared to the pea and fava bean gel, right? That's the mechanism, right? So what we did was we did the 3 extrusion from the mung bean pea and a commercial pea. We did a lot, but presented here. So the mung bean is a high vaseline, pea is a leguminin vaseline, and the commercial sample is unknown sample. You don't know what's the source of commercial sample. Right? And one of the way to understand whether your protein is native or not is do the DSC. But you cannot do the normal DSC for the protein. It's too complex. You have to do what you call a nano DSC in a solution state. And over here you can see that the middle one is a mung bean. Mung bean only has one peak. That's only the vaseline peak. But if you look on the lentil and the pea, you have a 2 peak. They are vaseline and leguminin peak. But when you look at the commercial sample over here, it doesn't have any peak. Means the commercial sample are probably a denatured one, or they have been chopped by the enzymes to increase the solubility. You don't know the source of commercial sample, right? So that is the one thing you really need to understand, that if you are extruding the denatured sample, your product will be already denatured. It will not have that much of reactive potential, right? You need to understand what's your native state of your sample first before you talk about the extrusion. And do not blame the extrusion. Blame your capability to analyze the sample, right? So, but once you do the high temperature extrusion, most of the samples are crystalline structures or secondary structures are denatured, okay? Now, there's another way to look at the structure as well. That's the CD spectroscopic, right? And these, I'm not going to go on much detail. That downfall at the 220 and this at the 190 are some sort of representative of secondary structures. But once you do the extrusion, these structures are damaged, means they lose their secondary structures. The take-home message, high temperature extrusion will basically damage all the secondary structures, and it will develop the unordered structures. And the unordered structures are more prone to aggregates compared to the native structures. And I'll show you what the aggregation means in the coming slide. Okay, so these are the raw materials before extrusion. And just want to highlight that, okay, this is a pea. I told you before, pea has a more leguminin and vaseline. Okay, leguminin are hexamer. They are around 300 kilodalton. So this is the leguminin peak. And this is the vaseline peak, right? If you look on the mung bean doesn't have the leguminin, and it has the vaseline peak over here, okay? Commercial samples, the peaks are very low, 38 kilodalton, means it is already like a chopped, because they want to increase the solubility, right? Now, we do the extrusion. So this is the extruded sample. Okay, so this is extruded of those samples. And look at here, the highest peak is around 90 or around 70 kilodalton. So what does it mean? The hexameric peak around 300 kilodalton, or the trimeric peak around 150 kilodalton, they all are degraded after extrusion. It doesn't have any secondary structures. But where the peaks are now is there's a small peak over 1200 kilodalton. Okay? Now, to make it clear, just compare between these two. This 90 kilodalton peak, which is the highest one, is here. This is neither any important peak for the raw materials. But you get an aggregation over here. That's 1200 kilodalton is the aggregated protein. So what does it mean? After extrusion, you really get the aggregated proteins, and these aggregated proteins doesn't have the secondary or helical structures. They are basically random order, right? So that's the take-home message. The extruded samples are basically aggregates. That's why they lose the solubility. That's why they have less functional property as well. And that's why they develop some sort of structures because of the aggregation as well. So varying the degree of aggregation, you can develop different types of structures, right? Now, the take-home message over here is the structures. Please read from this side, okay? From vaseline-like protein, for the vaseline-like protein, the proteins are degraded to smaller units. For leguminin-like a protein, they basically tend to re-aggregate to the
higher structures. Why vicillin degrades? Because they lack the disulfide bond. Why the leguminin aggregates? Because they have the disulfide bonds. That's a structure to the mechanism, right? So these are some of the work on that. So this will be recorded as well. So you can look at the papers, and if you want to do any of those analyses, just keep in touch with us. We are more than happy to provide you those services free of the cost for one sample. Okay, so the cold extrusion is a 5 minute left, right? Great. So now we are talking about the low temperature. So starch and protein at low temperature, so I don't need to give the background. So here, let's look at how the starch behave at the low temperature. Remember, at the high temperature, there was a gradual decrease of amylopectin. Low temperature means it has never been exposed above 50 degrees centigrade, which is 10 degree or 15 degree below the gelatinizing temperature of the starch, right? So the first is the extrusion damages the starch granule, and it's basically shear-induced damage. Second, you can again see the extrusion has a much more effect on the amylopectin molecule, not the amylose molecule, and these amylopectin are broken down and smaller fragments are coming over here. Okay, the same principle. Even at the 50 degrees centigrade, at the 150 RPM or 500 RPM, doesn't matter, the amylopectin are degraded, and it's a shear-induced degradation, not the temperature or pressure-induced degradation. Third, that degradation affects the cooking property that somehow increase the cooking loss as well. Okay, and that also affects the digestibility as well. So you can increase the digestibility of the starch or pasta just by increasing the shear rate. Okay, that sometimes can be beneficial as well. So we don't always need a low digestibility. You can have the more digestibility as well, right? Or alternatively, you can lower the glycemic response by decreasing the screw speed as well, more compactness. Okay, so this is a huge amount of work we are doing on that area, especially looking at the low temperature induced, but I'll basically focus on the protein and the gluten allergicity. So this is the protein on the pasta, it's basically gluten. So there's a lot of information over here. So what happened is there's a control pasta at 150 RPM and the control pasta at 150 RPM, right? Gluten added pasta at, finished, 2 minutes. Gluten pasta at 150 RPM and gluten pasta at 550 RPM. What basically happened is that you can see that once the screw speed is increased, right, your F1 peak is decreased. So F1 peak are glutenin peak. Okay, so just keep looking at this. What does it mean now is, increasing the screw speed, larger glutenin molecules are degraded, right? So what does it mean? Even in the low temperature extrusion in the pasta, you have change in the gluten structure or gliadin structures based on the screw speed. The important thing is, not only it changes the gluten and gliadin structures, but it can also affect the allergens. So if you look on this one, the allergens are decreased. And the number of peptides are also decreased. Okay? So one of the ways to lower the gluten allergicity in a pasta is increasing the speed, so that the shear-induced degradation of the protein can lower the allergicity. Okay, so I'll go to the conclusion. These are the summary, and this is my team. If you want to join Monas or do some of the collaboration with the Monas, please look at it. So I have a Labraj over here, Labraj is over here. Where is this one? One of my colleagues is there, he is me, sorry, I'll put your name as well. So we do a lot of work on the starch, fiber, protein, food structures, gut digestion, in vitro fermentation. So we provide one-stop solution for many research. Please be in touch. Thank you. I have one question time.
Yeah, thanks, Sushil. So we've got about a minute for questions, and if I start with the online, because the rest of you can catch Sushil over lunch or this evening. So are there any online questions, Danyang? No?
Great.
Anybody with a question for Sushil?
Yeah, Pastor, please.
Can you just wait for the microphone so the online people can hear?
Thank you. interesting presentation. So my question is about the allergenicity.
Yeah.
So allergenicity, we know these are coming from amino acid or a certain amino acid sequences,
Yeah.
not from large molecules. So do you know if extruder is able to break down that sequence that then it's low allergen?
Yeah. Extruder doesn't have preference over any molecule. Whatever comes on the searing position, they will be degraded.
Yeah.
Right? So allergens are maybe 15 amino acids or 25 amino acids, 30 amino acids. We found that they are degraded. Okay? That's why our research shows that higher speed, it will reduce the amount of allergen.
Have you tested that? Or
Yeah, that's what that the
No, I
result
mean, the sequence is smaller, but have you tested the product is considered as allergen or no?
No. So there is a protocol for allergy testing, so we follow that, and the number of allergens are decreased, and the size of the allergens are decreased.
Correct.
Okay, that was shown on my last slide.
Yeah, I saw it. Thank you.
And it's recorded, so you can visit that slide again.
Yeah, I know that.
Thanks, Sushil. I think we'll leave it there in the interest of time. So thank you very much, Sushil, and a small little memory from your talk at CSIRO.
Okay, thank you, everyone. Thank you very, very much.
You're now, Bo's next. So Sushil came from the other side of Melbourne to get here. Now, pleasure to introduce Dr. Bo Zhang, who's come from China today to be with us. And Bo will be talking about flow behaviour of aqueous dispersion systems of a soybean protein isolate. So, thank you, Bo.
Thank you, Crispin, and thank you, Dan Yang, to invitation. And visited CSIRO again. I have been here for 1 year, and I'm very too special. Thank you for Danny, because I'm want to share the topic of flow behavior of the SPI, SPI, but I'm warner. I just too difficult to start. Why? I needed to share these results. So the Danny is give me very, very good start. The logic, the rheology, and the flow dynamic is very important in my head. So I want to give some events and my feeling to you to support the rheology. Very important. When the protein is put in the extruder, and you can imagine the material went through the dyer. So if you have the low viscosity, should be like this. If you have a higher viscosity, maybe like this. So this is the two type of the products, and I think it's the you can imagine. And so how to characterize the flow behavior? We use this model, and that means the viscosity is equal to the consistence coefficient, and also with the flow behavior index. But today, I just share some results of how, what's the facts to influence the K and the N. We haven't the time to do some the work, how the K and N is related to the extruded products. So we're using 8 types of the SPI according to the particle size distribution. You can see one is the smaller, and the S8 is bigger. And also we measure the amorphous of the, with the length to the width ratio. That means when the particle through the equipment, the instruments, the most sites can be measured, and the very low sites will be measured. So this index, LBW, if bigger, that means it's less group. It's bigger, it's less group. It's equal to the 1, that means the group. So, and also we do some physical property. You can see the crude protein content is almost the same, because the commercial SPI standard require should be around to the 90%. And also we do this is the particle size, this is the LBW, this is the tapped density, and this is the soluble property, and this is the water holding capacity. But this is means the per gram insoluble fraction. So this one, the protein content and the solubility and the WHC represent the higher draw phobicity. And also we do the dicipher bond to means the social means the cross link, and also the zeta potential. And we do this reorimeter for this 60% to the 10%, the material can flow, so we're using the low rotation reorimeter. But if you similar like the extrusion, the temperature, the solid content TS is very higher. That cannot be flow, so we need to use the capillary reorimeter. So we have the very low TS, medial TS, and the very higher TS. And this is the K relationship between the TS. You can see with the TS increased, the K will be increased. But when we are very low TS, the scope is small. But when they are very higher TS, is very higher. That means they increased very fast. So we are doing the also the exponential model to simulate. So we can see we are do the correlation with the K with the physical property, like this one. We also construct the two parameters. For example, we are using the multiply the particle size and plus the multiply the LBW. So we are doing, and also we do the correlation. Yes, we select some top or the most significant correlation and to draw the figure. For example, this is the 6 to 7% TS, and you can see the R square is the for this parameters is very high, the most higher, and that means the K plus K divided by the TS. That means we are to cancel the TS, the effect. that means just only the structure or what the physical property. And also we do the media total solid content, 8% to the 10%, and the parameters is different. You can see here is the most higher. The parameters is the particle size multiply the LBW. But when we see when very, very low total solid percentage is the 100 subtracted to the NSI, that means how much the protein can solubility. And with the WHC, it means the total insoluble protein or fraction can hold the water. So it's the different. And also, if you go to the most, the highest, the total solid content, the parameters is also changed again. For example, you can see the tap density. So it's very interesting, which means if the total solid content changed, the mechanism maybe to affect the coefficient is different. So 5 minutes? Okay, this is the last slides. So what we are thinking is when very, very low the total solid content, that means the particle and just the interaction with the solvent, not with the particle to particle. When you are very higher total solid content, the particle is, the interaction will be particle to particle because they are very narrow. And in the media, that means between the station, the constant of that. So that's why the mechanism of the viscosity is the different. For example, if when you are very low, that means the most mechanism, the points is the particle with the solvent, like water. But if very higher, that should be like the solid rheometer, the particle interaction, the particle. And in the media, that's between them. That's the particle size and the morphology or the shape of the particle could be affected, the viscosity. That's all. Thank you very much.
Thank you, Bo. So, Dan Yang, are there online questions? So, open to the floor, and I'm sure there's lots.
Thank you for the presentations. I find that your graphs, those relationship between the K and the physical chemical properties, quite interesting because you got lots of correlations there. And you mentioned that you've got 8 samples in total, 8 commercial SPR samples. But in the data points, you actually have 16 points on it. So may I ask, do you measure like this, let's say for the water holding capacity of all those 8 commercial samples, and then you measure their rheology to get a K? So that will be one. So you got 8 samples, that means you got 8 data points. So how do you get 16 data points on those graphs?
Yeah, because we have the 2 or 3, the total solid concept, the percentage. Each 8, we needed to measure the rheometer by the 6% the total solid percentage and the 7 percentage. So you can get the 16.
All right, so you are saying those physical chemical properties is also a function of the total solid contents?
Yes, of course. And but we are when we are to see what's the structure, the effector, we will divide the total solid constant. You understand?
All right, I have to think about it. No worries. Thank you.
Okay.
Well, thanks.
The way I like to summarise all of what you've just presented is extrusion is typically a water-starved process. That's why you can't have true gelatinisation or true denaturation. And what you've highlighted is how important the moisture content is in dictating the cooking pathway that the raw material undergoes. This is why when you've got an extruder running at constant speed with the same dye, with the same recipe, simply adding 1% more water in changes the product. You're selecting a new cooking pathway through new rheology within the screw that dictates new flow dynamics within the same screw that leads to a new product. And that's what's going on. So again, it's always rheology and fluid dynamics interplaying within the extrusion system. It's a new way to think.
Thanks. And we've got
Thank
one
you.
question online, and then we'll wrap it up after that. We can't hear you, Regina.
Is that better?
Yes.
Yes, sorry. Just wanted to come back to your correlations, particularly with regards to the high solid system that you presented. So you correlated well with tapped density in that case. So I just wondered, what's your thought on the soluble protein content that you would have in that dispersion system at the time? What role would that play? Because that probably wouldn't play a role in tap density, but probably would play a role in a dispersion system.
I need help. I just understand the tap density. Oh, yeah. Okay, I will try. Because when the moisture is very low, the material, the flow behavior like the solid. So the tap density is the solid density. So that's why the tap density will be more, can predict with the very low moisture, the flow behavior. Thank you.
Thank you, Bo.
That's
it. A small gift for you.
Thank you.
Thank you. Askar? And so the third talk in this session is from Askar Faranaki from RMIT, again, just across Melbourne. We're bouncing around the world a bit. And he's going to talk about starch conversion processing in extrusion cooking. Over to you, Askar.
Thank you very much, Crispin, and thank you, Dan Young and Jordan, for giving the opportunity. It's a great pleasure to be here today. I'm from RMIT University, and we have a Food Research and Innovation Center there. We have interest in, of course, extrusion. That's why we are here. I will be talking about starch. Also, we have two other presentations this afternoon with our postdocs, Eva and Billy, that they will be talking about high moisture extrusion for texturized plant proteins. All right. This should, oh yeah, okay. RMIT, we've got different campuses. We're based obviously in Melbourne. Also, we've got campuses in other countries, including in Vietnam. Yeah, okay. We've got a Food Research and Innovation Center. We've got pilot plant facilities. And also, we have some extrusion capability. This is our twin screw extruder, which is set up for HME. I'll go to my presentation. I will be talking about starch. My colleague Sushil talked about HME, touched based on starch as well, but I will go deeper into starch to see what is happening to starch when we extrude it. Mostly this is relevant to breakfast cereals and also puffed snacks when we have low moisture levels and we have high SMEs. Yes, this is an extruder. Dennis talked about the basics, Azad, and just I want to highlight that inside the extruder we actually combine a number of unit operations that you can see on this slide, including mixing, shear, temperature, cooling, and we have a very effective way of mass and heat transfer all happening in perhaps matter of seconds. And Dennis highlighted this morning. It's very different to when we actually look into a starch, put it in water and mix it. It takes minutes, sometimes up to 10 minutes to gelatinize. But in here, we're talking about perhaps much, much shorter time. So extruder is a compact system that brings about many capabilities. Azad actually highlighted that this is a sort of a very resource-intensive process. It's cheap. It can actually produce products with high production rates. And also, we can play with dyes, with, let's say, ingredients, and come up with many varieties of food products. So it's a great tool for product development and also making, perhaps, ingredients. And we can play with our raw materials. We can play with our process parameters. And when we combine those two possibilities, it gives you many, many options to play with and make new products. On this slide, many products that the starch is playing a key role in their structure, but the starch in terms of its state is different in this product. So some are actually gelatinized, some are in native sort of form. So yes, in pasta it's native, but in the rest actually is more or less gelatinized. I know Dennis doesn't like the term of gelatinized when it comes to extruded products, but we can debate on that. Starch, starch of course, is actually playing a key role in many of these type of products that we talk about. It's a cheap structure forming ingredient. So it's actually a structure forming. It helps us to give a structure to our ingredients. It's a binding agent. It can actually help us to make porous texture. When it comes to semi-solid, semi-dry products, it can actually help with elasticity. It can melt much easier than protein. That's why it's easier to work with. And also in many cases, if we want to play with one starch, it's easier to find another replacement. When it comes to proteins, it's a bit more difficult. If we want to make a good product, we need a formulation, a balanced mixture of ingredients. We need the right extruder, and also we need the right process design. That's what Dennis was talking about, and when actually it comes to product development, we need to play with this to get the right product. Also, we can use extruder to make food ingredients. So we can actually use this extruder to make pre-gelatinized starch, for example. So it's not just food products, it's actually about ingredients too. When it comes to starch and starch-rich formulations, this is the system like any other extruders. We've got ingredients going into the extruder, we've got water, we are heating it, we apply mechanical stress, and that's gelatinizing or processing a starch as we go. So SME is very important in this process. SME is the mechanical energy that we apply per unit of weight or mass of our product, and that is very important. We can actually roughly measure it with the electrical current that is going into the extruder, not 100%, but it gives us a good rough estimation. Also, it's good to know that this mechanical energy that we put through the equipment, it actually mostly is converted into heat, and that heat, of course, is very important to process a starch and any other proteins that we have. Also, residence time is another parameter which is important. So that's the time that our materials actually spend inside the extruder. It could be 40 seconds or maybe a couple of minutes. but this depends on a number of factors like screw speed, flow rate, and also the screw design. Do we have reverse elements or we don't have those? So it's very important to know what's our residence time, and we can measure it. We can put a die and see when it's coming out, and we can actually measure it. When it comes to starch-rich products like breakfast cereals, extruder is at the heart of this system. So we've got raw ingredients, it goes to the extruder, and it's actually mixed with some water, not very high levels, maybe 5%. It's exposed to heat and also mechanical energy, and we transform starch from semi-crystalline structure to a system which is amorphous. We may call it gelatinized, but of course it's a different system. And after that, of course, it goes to a flaker, then a roaster, and a coater. But extruder is actually at the heart of this process, and we want to see what's happening to starch when it goes through such a process. Starch is in a form of starch granules, as we know. They come in the perhaps sizes of 5 to 20, 30 micrometer. If we put it in water and give it time, it actually precipitates. It's big. But let's see what's happening when we put it through the extruder. The starch first is mixed with water. It gets heated at the first perhaps couple of zones of the extruder. Then it gets cooked. It gets heated perhaps to 80, 100, 120. It's a sort of a enclosed system. And then it actually, mechanical energy helps to get it into a system that we call it a homogeneous melt. This homogeneous melt is a cohesive system that is going to come out of the die in a sort of a cohesive, free-flowing sort of a melt, and we can form it, we can shape it using our die and also the cutter. If I go to the next slide, this is our benchtop extruder that we're putting through some starch-rich flours, and we want to see what's happening in here. So this is our extruder, different zones with different temperatures. You can see the temperature at the top from 30 to 150 and then 120. That's the melt which is actually coming out of the die. So that process is happening just 60 seconds. So we're transforming our powder into this melt, this homogeneous melt is coming out, and we can actually form it, we can shape it. The cutter is not, of course, in there. We just want to see what's happening. So let's have a look and see what's happening during this 60 seconds. This is our wheat flour. We put it through. The particle size is perhaps about 200 to 500, as one of our first speakers actually showed it. In here, we've got perhaps 5, 10, 20 starch granules. We've got water, we've got heat, we've got mechanical energy, and in the next stage, what's happening is that starch granules get some water, they get heated. After that, starch granules are broken down, water is there, heat is there, and they tend to basically lose their structure. Granules are not perhaps present anymore when we go to the end of the extruder. And that melt that you saw coming out of the extruder is this shape. So we've got an amorphous sort of cooked system which is coming out. We can basically look into it, cut it, and perhaps puff it if we want. We can control our temperature of the die. If it's above 100 degrees C, we can have puffed system because water is evaporating at that stage, and we can have a porous system. But this is the ideal system that we want. We want a homogeneous system of water, broken starch granules into perhaps amylose and amylopectin, and maybe some broken starch granules, and in there we can get these products. So in this system, you can see that's our starch going into the extruder, but these are actually products that we've made, and just the difference is actually the quantity of added water. By changing the water content by just 2 or 3 or 4%, you can actually have different expansion. So this one is a bit dense, but when we actually reduce moisture content, mechanical energy goes higher and we can get this puffed product. Next slide is just perhaps go and touch about the content that Azad actually looked into when he was talking about engineering and material science. I would like to just highlight what's happening in this system. So inside the extruder, if we go to the starting point, we've got the powder and water. It's here. The starch is in the form of semi-crystalline system. We add some water to it, but the starch and powder is actually in the form of a glass in here. It's hard. When we add water to it, what's happening is that we actually increase moisture. This graph is showing how starch and wheat flour is moving from glass to rubber. So this line is actually is showing how starch can be moved from glassy state to rubbery state. This is coming from the material science. So first we add water, we make it wet, then we heat it. What's happening is that we're actually moving from a hard, glassy system into a rubbery system. That's why we can actually create that melt, because the particles are flexible, they can come together, and they can give us that cohesive structure. After cooking, what's happening is coming out of the die, we cool it down, and also we actually lose some of the moisture. That's why it's coming actually from here. It's coming back and gives us this low moisture expanded system, because we're cooling it down and we're actually losing some of the moisture as well. So in this system, we start from a glass, we go to rubber, and we come back basically to glass. Again, that's happening in a matter of perhaps a couple of minutes. Very quickly, this is what's happening for the RVA. The RVA is just measuring the starch. That's actually for native starch, and this is for what's coming out of the extruder. Very quickly, in here, these parameters are actually telling us how much starch is transformed during extrusion, as we've discussed it. So that's temperature, pressure, SME, residence time, added water, and mixing. Those are going actually to dictate what's happening. Very quickly, extrusion is impacting molecular weight, and we can see that if SME goes up, the molecular weight goes low. So that's what's happening during the extrusion. I have another couple of just slides. I'll finish very quick. Yeah, sure. So in here, it's actually showing how temperature and SME during extrusion is going to impact starch solubility. So that's actually very relevant to process design and product quality as well. So take-home message is this one. Extrusion cooking is very efficient way of cooking starch. In this 1 or 2 minutes of cooking during extrusion, we can damage a starch close to about perhaps 20 minutes of starch cooking in a pot in the presence of hot water, let's say. So extrusion actually can transform starch very quickly, and that's why we call it starch cooking, but it's very different. That's my team. Some are here, and some acknowledging some of the funding bodies we've had projects with, and thank you very much for your attention.
Thank you, Oscar. Thank you. In the interest of time, we'll move on to the last presentation in this session. And it gives me great pleasure to welcome Professor Osvaldo Campanella. He's currently the Carl E. Haas Endowed Chair in Food Industries at the Department of Food Science and Technology at Ohio State. But he's spent... Askar, have you got the clicker? No, sorry, it's on the tape. It's the... Yep. Green is forward, back, laser pointer.
Okay, thank you for the invitation to Jordan, organizer. It was a long trip for me. Just came yesterday after 30 hours of travel. And I realized today that my presentation was today, not tomorrow. And then I will try to do my best, but anyway, there was no change. I mean, the presentation was done in the plane, but you know, after listening, then I want to introduce some concept. Anyway, but if you see the title of the presentation, is something that was mentioned here before. The moisture is very important in the extruder. When you have an extruder, you have a screw configuration, but if you change the product, you change if you change the moisture, you change the product because you are changing the rheology. And this is what I will be talking today. Anyway, why, you know, many times when you are writing proposals, many people that they don't know extruder, they are saying, oh, extrusion is no innovation, it's an old technology. It's not, yeah, obviously, if you listen to the talk today, it started, I don't know, 1800. It's an old technology, but it's been changing. And then you see there the example that we can have. We can create texture, and we can create innovation. You have there 3 products, which is, they have been discussing today. We have expanded product with low moisture. We have the famous TVP that has been done for, I don't know, 20 or 25 years. And nowadays, with a high moisture extruder, and then different product. Same machine with a few change and changing the process condition. We can have ingredient functionality. You know, we can change the functionality of the ingredient, and then I know that there are a lot of talk tomorrow, and then there was a few today talking about we can change the starch. I mean, my previous talk was relating to that. We can change the protein. We also have nutrient and anti-nutrient in the formulation that can be modified by extrusion, and it's quite important. Customization and innovation, and you know, there are new products. I mean, the cholesterol presentation today was showing that what you can do with one machine. Smart manufacturing, artificial intelligence, I will show you what we are doing at the end. And this is something in my interest to have this very short trip to Australia, because, you know, there is a good group here that we want to collaborate. You know, to do artificial intelligence, you need to create a very large database. And then we need to do a lot of experiments. And then collaboration is very important for that. Sustainability is very important. And today, as Chad was saying, you know, basically, what you put in the extruder, you don't lose anything. There is no solvent going out. And also, you can use a material which are not very expensive, they are sustainable, and they have all that possibility. And later is optimization of nutrition. And I will show you, and this is one of the slides that I introduced this morning, that is important, you know, how you can change the protein just to modify the nutrition. Okay, and then, but you know, to do all those things, you listen this morning, it's a lot of challenges. It's not easy. It's not like you have the machine, you put the stuff and it's coming out. You have to do a lot of work, and then also you have to do formulation, and then, you know, you have protein, you have polysaccharide, you have other ingredients, and then you have to mix those in the extruder that you need to change the material property, get the proper rheology, get expansion, or maybe get texturization, and get the product. And then there are a lot of challenges in that part. It's not as easy as like putting the stuff and it's going to be coming out. There is very important challenge in the scale-up. You know, we are using in the laboratory, we're using a small extruder, and then we have to scale up, and then he was talking about that. Scale up is not an easy way, because, you know, most of the time you can do a product in the lab, but you cannot do it in industrial scale. It's changing because, you know, temperature, shear, the size of the equipment. And I will show you a case, what I introduced also this morning after listening to that talk. The engineering is very important for that part. And then in that case, rather to do a scale up, we did a scale down. And I will show you why. Okay. Another challenge is just basically get the texture, the flavor, and the nutrition. And then this is something that has been discussed this morning. We are trying to imitate meat. And I can tell you, after 20 years of working in extrusion, there's no way that we are going to get it. we had to create an alternative protein. And I will show you an example, also introduced this morning after listening to Dennis. Okay, and process optimization, I believe that artificial intelligence can help us. Tomorrow there will be a nice talk of Jordan. He's doing quite nice work in artificial intelligence. I saw the presentation in US, in Seattle, last year. And we are going to talk a little bit about some of what we are doing and what we can do together. And cost is very important. Okay, and then if we discover that when we are making all this very nice plant protein product, but they are costing more money than the real meat, is a problem. And that is happening right now. If you go to a supermarket and you buy imitation sausage, it's not the same as the real sausage, and you have to pay more. And then people say, no, I don't buy it. And then this is quite important. And cost is also related with the formulation. If you know to make this product, I mean this meat analog, we need to have isolate or concentrate in about maybe 60%, 70%, 80% protein. It's very expensive. It's not cheap. And then if we can reduce the price, that may be affecting or influencing the cost of the product. I will give you an example. And then talking about the moisture, this is something that was done many years ago when I was in New Zealand, but was giving some idea for something that we are doing right now. I'm talking about low moisture, and you see there the moisture that you do for getting an expanded product. And that was the first cholesterol extruder in New Zealand. I don't know. I mean, this is what yeah. It's a VC21. And then, as Danny was showing, rheology is very important. And then at that time, we tried to measure the rheology in line, and then we tried to measure coming out from the extruder. And then, if you see there, attached, it was not that extruder, it was smaller. This is a VC32, it was a 21. We created this rheometer. Okay, it was a capillary system, which was a slot, and then you see there you can measure, I don't know if I can, but you see that you can measure the pressure in different points, and then when you measure the pressure with the distance, it's quite important how you do it, because in the past where people, when you want to get the rheology, you need to know different shear rate. And in the past, people were changing the rheology, changing the throughput in the extruder. But if you are changing the throughput in the extruder, the product is different. And then whatever you are measuring at the different shear rate, totally different product. And then what we did over there, you see there between the die and the extruder, there is a bypass. And they were bypassing the flow to change the flow through the rheometer, keeping the specific mechanical energy constant and keeping the die pressure. You see there in this one, this is done with a 99% amylopectin. It's a very branched starch. And then the other is done with a 45% amylopectin. And then you see the rheology is quite different. And this is what we were talking, formulation is important. If you buy a different starch, it's going to be a different situation. You see there, the experiments were done in a way that the die pressure and also the semi, they were not changing. And then we were sure that we were doing an experiment on the same product. And you see there on the last part, you get the rheology, and you get something interesting. You get, when you have amylopectin, the rheology is lower compared with the amylose. And then what is happening that there is a lot of explanation. The branching is easy to be fragmented. You have a better plasticization of the water. But in a way, having that lower rheology is allowing you to have a better product. And then when you have more branched molecule, you have a better product. And then if you go to the plastic research, they know that. When they are using polymer, which are more branched, they are getting better expansion. That was given an idea of a project that we have with a large company trying to do increment the amount of fiber into snacks. And then we know, and then we saw some formulation from cholesterol if you use fiber, it's no more than 7 and 8%. And then that company want 25% of fiber. How we can do, and then there's no expansion, the product is very bad. That old project done many years ago in New Zealand gave me the idea, and then was helping us with the hypothesis. This is what you see there, this is what you have in corn fiber. Corn fiber, basically you have protein, you have cellulose, hemicellulose, and you have another polysaccharide called arabinoxylan. And then those one are more functional to have expansion. And then what is the idea? What was the hypothesis? Why, when we are using the fiber, the bran, we mix with the corn grit or cornmeal, which is the best product for making expanded, you have a phase separation. And today, I think Danny or someone was talking about phase. Phase is very important. I think Asad also was mentioning the same. There are different phases. And then in a way, if you have this fiber without modification, you are going to have a problem because they are going to separate. If they are going to separate, the expansion is not happening. And then the hypothesis here was if we disperse, and when I say disperse, it's a molecular dispersion. Somewhat we modify the fiber to disperse and make the fiber more similar to the starch that we are mixing in the formulation. And then one of the ideas came from that old project. I said, maybe what happens if we have arabinoxylan, they are more branched. Can we get it? Can we analyze? And then this is what we did. And then the hypothesis was, okay, if we disperse that fiber, which is coming from the corn, perhaps it's going to be a little bit more easy to expand it. Okay, and then this everything about the expansion, and then you see the glass transition is very important, the rheology of the material is very important. Everything has been discussed in the book, and also was mentioned today here. And then we managed to do that, and then basically this is a very old way to get arabinoxylans, and then you have an alkaline extraction, you have neutralization, and then you separate different fractions, and you try to get the more branched one. Okay, when you do that, you can dry, and then you see the rheology is very different. And then CAX means corn arabinoxylan, and then the other one is the hydrolysate. You see they are different in size, but somewhat the corn arabinoxylan is Newtonian, even at 10% concentration. Why? Means that they are having a globular structure, and that maybe that globular structure has some effect in the extrusion. There are a lot of papers published in that concept. We have some ideas, and then when we got that product, we managed to say, okay, we can put 6 grams of that product in 500 milliliters of water. That is equivalent, we counted the amount of fiber that you have, 3 bowls of oatmeal, 10 bananas, 20 slices. Funny, I put that picture in a proposal, and it was criticized, and we didn't get the money because by mistake I put a bottle of plastic. They say, oh, they are not looking at sustainability. I mean, that was not even related, but you know, sometimes happens. Anyway, but going to extruder, this is what happens when you are having the expansion, and you see there in the middle, on the right you have no fiber, it's a cornmeal or corn grit, and then on the left you have 25% fiber, no modification. See what happens when you have a modified fiber. Basically, the expansion is similar, and we are getting product. The only difficulty right now is just to get the fiber, because you know you have to get some company to make the fiber. We are working in that part and see how we can improve that. Okay, and then based on that old paper also, we did a paper based on this hypothesis, and then basically we need to understand the fiber to know what is the fiber that we need to use for extrusion. And that was a project done with the company Mondelez. And you see there, we characterize, and then you see there you have the corn arabinoxylan, and you have the wheat arabinoxylan. They are quite different. In a way, the chemical structure is very more branched. with arabinose island. And then when you do the extrusion, also you see the effect. You know, in a way, the hypothesis is working. When you have chemically branched molecule, you have the chance to get a better product. Okay, expanded product, compared with arabinose island. We also combine, and then this paper was published in 2022, and then you see there you have all the characterization of molecular size. They don't change much in the molecular weight, but the branching is different. We also measure in the branching, but you see these are two commercial products, and also you see there the rheology is quite different. It's another way to see how those fibers are going to behave. But what is important when you do the extrusion, and you see there, these are the two commercial fibers. This is the corn, the product without fiber. This is with the corn arabinose island. You know, in a way, this kind of branched structure that chemically branched, and also the molecular weight branching, and the molecular weight is basically controlling how it's going to be the product when you have to expand it. Okay, key takeaways. We can do 25% modified fiber inclusion, but you have to modify, and you have to select one. Even the commercial one, they don't work. You know, inulin is very heavily used, but don't put in the extruder because you're not going to get the right product. We can also valorize byproduct. Now we are working with Spain grain from the beer company to use as a fiber. Okay, I put there circular economy is very important, and we are trying to use those materials to do this kind of product. But also, you know, sometimes we need to get expertise from the plastic industry. That idea of the branching, it came from the plastic industry. And then he was saying today, they are more advanced than us. Okay, but then why don't we use what they know? And then it's helping us. Okay, and also we are doing some collaborative research. It's very important. You know, we are making a product, we are engineers, but what happens when the product is consumed by the people? It's a good thing, it's good nutrition, the taste is important, and we are working, expanding the research, and then I'm working with people, Forte in Ohio State, we have the medical school, and they are doing the gut microbiota analysis of the different extruder. That part needs to be done. If we had, the question today was, if we need to get a better product, and then the sales are not going down, they're going to go up, we need to understand all those things. And then I don't know those things. I am working with a person that knows, and then we are having a project together. Okay, and then let's move to the high moisture. And then you see there, this is a nice paper, was published. I had to review that paper, I know. It's a very nice paper, and then you see all the changes, and then there are predictions to 2030. I don't know if it's going to be happen or not, but you know, this is what is the prediction, and there will be a lot of type of proteins that can be used, and then, but again, and I kind of repeated what Danny was saying, it's not selecting the protein. You need to go and get what are the best conditions, and I will talk a little bit. How is my time? I have 10 minutes? Yeah. Okay. I'm afraid to be. Okay. And then you see there, this is some of the product we can do. This is that was done in collaboration with Klextral, and we are talking on the top, and where this is supposed to be a meat analog. But you see the picture of the real meat. It's very similar, but you will see what happens when you don't do the whole analysis in the system. This is the equipment that we have. It's a VC32 with cooling die. And then this is some of the product we were getting. I think that was probably that product. Okay, and then what is the main driving to have texturization? You know, we have in the extruder part, we have the reaction, but at the end of that, we have to create the texture, which is another part. We are modeling that part. I mean, I gave up modeling the extrusion part. It's too complicated. You know? I mean, maybe Emin can do it. It's really complicated. It's because the rheology is terrible. I believe that the cooling die is easier. But you know, at the end of the day, you are in the industry. Even the small extruder, it takes a lot of time to do analysis, trial and error. And you mix your ingredient without knowing much, and then see what happens. With a small extruder, one of the advantages is you don't have to use large quantities, but in general, the scale-up is going to be an issue. And then what we are doing right now is trying to work with different techniques that we can do before to put in the extruder. Okay, and then we play with the rheology, we play with a few things. We have, it's an RVA, it's not an RVA, we transform our rheometer in a high pressure cell, and then we can run formulation at the extrusion condition, 140, 150 degrees. We have some data, and then with that data, basically, we go to the extruder and do the extrusion and see if what we are trying to get is helping us to get a better formulation. And then what we were finding was the protein gelation is very important. What happened in the texturization is a gelation. Okay, and then you have to gelate one phase, which is very rich in protein, and it's very important to understand the gelation. Obviously, rheological property is very important. Extrusion behavior is very important, and also very important in that part, where all the reactions are being produced, because you know, you are transforming, and I would like to say something, what I say in a conference a month ago in Minnesota, when the people were talking about in that part of the extruder, we are denatured the protein. This is not true. The protein is already denatured. I mean, we are measuring, we are getting protein of many companies, very important companies, and we measure if they are denatured. You don't see any denaturation peak. I mean, you know, and then it's transformed, but it's not denatured. It's already denatured, because, you know, when you isolate, you spray dry, that's it. The native protein doesn't exist anymore. And then be careful, because, you know, you see in books, and then it's very confusing, because you say, oh, what happened there, you are denatured the protein. It's not true. You are modifying. It's an aggregation problem, and something is changing the protein, but it's not denatured. Okay, you see there, for example, we are also trying to use other material, and then for many years we were working with zinc. Used to be a very inexpensive product because no one was using. Now everyone is using, and we had to change because, you know, that's costing a lot of money to buy the zinc. We used to get it free. Now you had to pay. But, you know, zinc was helping us a lot. And then in this case, we want to try to do a product that basically is a mean analog with no gluten. To tell you the truth, if you have no issue with gluten, this is the best protein to do texturization. You have no problem, but, you know, the market said, no, gluten, no, it's gluten-free, okay, and then we got to do other things. But you see there, you can get product. We are similar, just modifying the formulation. And then the formulation we modify based on the initial experiment that we are doing in the rheometer to see how the gelation is happening. This is a recent paper that was published last month, in where you see we are using different type of ingredient. And then, for example, we are using protein from the pumpkin seed, you know, which is a waste product. And you see they are basically you need to understand the chemistry, you need to understand the rheology, as you see there. The chemistry we understand, and then I saw Sudin showing FTIR analysis. We use FTIR. And you see there that basically beta sheet is one of the very important configurations of the protein, which is not, probably it's already denatured, but you know in this product, you have that configuration with very high content of beta sheet. And then you produce, you know, with different concentration, you can create texture which are, you are seeing fibrils. And then you can do an analysis from those things. And then you see the factor of what the zinc is doing, basically what the rice starch is doing when you are doing those mix. And then those kind of analysis helping us to know what is going to be happening inside the extruder. Now we are concentrating more in the texturization and the cooling die, and how it's so important to know that before we go to the extruder. I mean, our extruder is not very small. It's kind of large. It's, to run a mean analog, we had to have 40 kilo per hour, which is quite a lot, especially when you had to buy the ingredient. But it's easy to scale up. I mean, the people from Cholesterol can tell me. The next one is the industrial one. And then this is something that I work a lot with Cholesterol, and I like it because, you know, first, it's a lot of collaboration, but also they are selling equipment that can be scaled up in an easy way. Okay, this is another thing which is another challenge. It's related to the cost and also nutrition too. This is a product that we did with a hemp flour and hemp protein. You see there, the idea is if you use a hemp protein, it's very expensive. And then what we're trying to do is, what happens if we mix, rather to have the whole hemp protein, we can put some flour. We can put hemp flour, which have starch, we have fiber, and do a meat analog. And the thing works. And then there, if you compare, this is 60 hemp protein, and then 40% gluten. Okay, that's supposed to be the perfect combination. Normally, the standard is soy protein, and in this case, we use hemp protein. We can start to change. Now we say, okay, we can reduce the gluten, and now we have 20% gluten, we have 20% pea protein. Okay, the texture is still produced. Now we got rid of the gluten. Okay, now we have 40% pea protein, and then the product is okay. At the end, we said, now we want to reduce the cost, and then rather to use pea protein, which is also very expensive, you use hemp flour. Believe me, the product was very good, but it didn't pass the cooling die. I mean, was created here. Was so texturized in a way that couldn't flow in the cooling die. And then what we decided to do, what happened if we modify the flour to make more functional? And then what we're doing right now, and I will show you one slide, modifying the flour, change the insoluble fiber into soluble to do more functional, to see if we can get that case. And now, in fact, we are producing, and you will see some pictures, we are producing about 25% of modified hemp flour, which is, in that case, you use the same machine. You use the same machine to modify the flour first, and after you mix with the hemp protein, and you do the meat analogs. This is the stuff, and you see there is no change. This is some of the experiment that we are doing in that device that we have to do the rheology, that basically we can simulate the condition on the extruder. We pressurize the cell. In fact, it's a commercial sale that TA Instrument is selling. And then we have the condition, and you see there what happened. Okay, when we are using less protein and we are using more flour, or we modify, we start to get the product, and then mainly of the parameters, they are not changing much. Okay, and in a way change a little bit the color, because those speck of black is because of the fiber of the flour. But you know, the texture was not changing. We had to do more work, especially digestion. We are also doing LCA analysis to see that the product is no more expensive than a real product. Quite a lot of work going on. Okay, regarding to cost and texture, since we were talking about phase, and then we need to understand the phase, that was another idea, and where now we were using a pea protein, but we use a fiber. And pectin was a commercial fiber that seemed to be working. And you see there, when you're adding the fiber, you do the confocal, and then you do the electrical microscopy, and there is no change, no major change in the texture. But we need to understand what is the reaction between the protein and the fiber. And then we use an interesting measurement, which is basically called QCM. You have a quartz vibrating, and then first you deposit one of the layers, which is the protein, and then after you expose that sensor to another flow, in this case with the pectin, which is a soluble system, and then the change in the mass absorbed here is somewhat related to the relation between the protein and the pectin. Okay, and then you can also measure rheology, but it's quite important to see what are the conditions in where my protein is going to be reacting with the fiber, and then that is done in 10 milliliter of liquid. It's not a big quantity, but it's helping us to do the extrusion. And then we did extrusion, and then now we put 5% fiber. You see, there's no change. Okay, and then formulation in the lab to see thermodynamics or physical-chemical condition of those potential interactions may help us to design what is the right formulation. I would like to show you a case. This is a paper that we published 2022 or 2023, trying to do a chicken analog. And then this is the product coming out from the extruder. That was done in collaboration with Klextral. And this is a real chicken. Okay, the difference here, that was cooked, was coming out from the extruder. Here we had to buy chicken breast and cook it. It's different, but you see the microscopy, they're not the same, but you know, they have bundles of fiber compared with the analog, but they're quite close. And if you see the texture, they are not far away. You know, hardness, chewiness, cohesiveness, the mid analog, they are quite a little bit different, but not far away. We also did the digestion. And then you see there, here you measure the degree of hydrolysis. In vitro digestion, you measure the soluble protein. They're quite close. We also did the essential and no essential amino acid. And somewhat in the conclusion was the essential amino acid for the meat analog or the chicken analog was a little bit lower than the real meat. It was funny because when submitted the paper, was accepted, but they asked if they can embargo the paper. I didn't know what mean embargo. They said, no, it has to be for 1 month, and after we're going to release it. Anyway, when it was released, was quite nice because they said, can we put it in the cover of the journal? Which is, yes, it's put in the cover. And that was the cover of the paper. And then you see there is people from Klextral and people from Ohio State. And everything was okay. I remember I was in France on sabbatical, and I started to get calls from many radios. And this is what happened later. So we are making fake meat, and this is why I agree with him. Probably was our mistake, you know. So we are doing a chicken analog. It's not. It's a different protein. And I remember one of the questions that they asked me. Said, "Yeah, but you are producing a protein, a product which is having less protein or less important protein." And my question was, "Do you like bread?" Yeah, of course. Look at the protein profile of bread. I mean, it's different product. And then maybe this is what we have to say. When we are saying, oh, we are imitating meat, we are imitating chicken, I mean, we're quite close, but you know, there are many things which are different. And then someone is going to come. There were 52 of those. I put only 2, but 52 of those things that we are making fake meat. There's something, you know, that comment today from Dennis, we need to call something different. We cannot call imitation. Okay, what happened with, I saw, Emin was talking about today about intensive property, and that
concept came to me when we were writing the book with Jean-Marie Bouvier from Clextral. And we wrote one chapter about intensive processing, the last chapter of the book. And at that time, I didn't know much. And then once the book was published, I got an invitation from a chemical engineering was doing a lot of intensive processing. And then they invited me to write a chapter on the book, but I was too busy. I said, no, I don't have time. And I feel guilty now because, you know, intensive processing will be showing up many years before if I will have the time to write that chapter. Anyway, but now it's coming out. You know, I saw it, Emir was mentioning, and also, I mean, Denny was mentioning, it's very important. Extrusion is very good process because the energy that you use per kilogram that you produce is very low. There is no, you don't throw anything. Whatever is happening, you put in the extruder, maybe you lose a little bit of water, but nothing else. And then it's a very sustainable system. And then in that chapter we have, this is something that I put today. Provide the need for the poor, yes. Extrusion is accessible to all level technical education, yes, but we need to be knowing more of things that are happening there. Social acceptance, probably is yes, because it's a little bit noisy, but no smell and no big problems. And then at that time was quite interesting because we have a project funded by NASA to Instant Pro, and Instant Pro was contracting us to scale down. This is an Instant Pro extruder. It's about 600 pounds, it's about 300 kilo to process soybean. And then NASA want to put soybean in Mars. They said, can we do a small extruder? Basically, this is me taking the measurement and taking the dimension. We did a model to understand what happened with that extruder, and then we use the model to scale down, and this is the extruder, 2007. This is my hand, you know, this is the screw part. NASA didn't go to Mars. It was a problem with a crisis, they didn't go. But Instant Pro sold, I mean, NASA got the license, and then, I don't know how, but they separate, I don't know if you know the story, and that extruder went to Africa. This is the extruder. And then this is the people working in the topic, and then this is the news. Okay, how we did that? Using modeling, using what we were talking today, reaction, fluid mechanics, and rheology. Okay, and then took at least 3 master students to do all the rheology of the material, and then after we had to do the scale down. And that scale down is based on mathematics. And then Instant Pro just converted. I mean, we gave all the scale, and then they made the product. And now it's using in Africa. This is extruded for many applications. Okay, what we are doing now, trying to do modeling artificial intelligence. We talk about rheology. This is the question that we are using right now. Okay, and then the material rheology is there. In that project, material rheology was very important because, you know, the Instant Pro extruder doesn't have external heating. It's being heat by basically the friction. I mean, the material is, and it's very important in soybean because you have to inactivate anti-nutrients, and then if you don't get the right temperature, you don't get the right friction, you have a problem. We don't have that problem, and remember, we are not modeling the extruder, we are modeling the cooling die, and then the rheology is very important, and then we are trying to use viscoelastic model. There was some paper published, but they are using power law or Bingham model, which are very simple. We are trying to use viscoelastic system. And then this is the other part, which is important because this is the phase part. How that phase, still I don't understand that problem. We are working. We are trying to solve that problem separately for that, but we had to solve all those problems to be able to help us with data. You know, remember artificial intelligence, we need to have a lot of data. And then some of the data were coming from here. And then I checked with an expert in artificial intelligence. Yeah, if it's from simulation, it's also okay. And this is some of the result of our model. And then you see there, depending on the condition, especially the temperature, which is controlled by, yeah, I think I'm okay. It's controlled by this equation. Okay, and then depending on the cooling in the die, you have texturization. You see here is not texturized. Here is very highly texturized. Again, temperature is very important for that. Okay, and then you see there, this is when before a temperature is about this critical temperature. You start with that system, and then if you are above, you don't get anything. If you are below, yeah, basically you start to have those texturized systems. We are modeling that part. This is some of the results. And then the part of artificial intelligence, and you see there is something that has been discussed today. This is what we can do. Okay, we have the pilot plant extruder. We are measuring the formulation. We also have information on the formulation with the rheology. We measure cholesterol is good for that. You can get flow rate, screw speed, cooling temperature, everything. Also specific mechanical energy. Get the final product. We want to get a device to measure texturization in the extruder. If we get the funding, we will do it. We also do measurement of the product, which is the normal texture analyzer, but also we are using NMR to measure rheology, it's Rheo NMR, to see how those phases are distributed in the final product. And then here we measure all those properties, and now we are planning to include sensory evaluation. Okay, and then this is the math. That we don't do that, you know. It's done with an expert in artificial intelligence. And again, you know, our proposal was reviewed. I mean, I got the information last week. We didn't know what was going to be happening. And it was highly ranked, but you know, they said I didn't understand that part. We had to put it in a better way. But you know, it's mathematics, you know. The fellow that's doing that work is the computer science and mathematics. But anyway, what we need to do is that part is going to be linking what we know. And then we start to do some experiment. And then this is based on 50 experiments. Now the students are doing 100 more. If I can collaborate with this guy here, we can have more data. Okay? And then we start to do with those very simple 50 experiments. We found something that we knew. When you increase the amount of gluten, you get a better texture. You know, we already know, but now we need to do more formulation. This is only done with a formulation with gluten and without gluten and soybean, but now we need to use or mix all the proteins and all the stuff that we can do and create that database that is going to be giving this information. And I believe this, the last one. That's my group. Some of them are graduated. This one is graduated 2 weeks ago. Do a lot of extrusion work. There are papers coming out from cholesterol. I don't know if cholesterol, you are talking about this die that you can have static die, but also you have a rotating one. We have data for that die, which is coming from the thesis, but you know, this one also finished. Okay, but most of them are working, most of them in extrusion. Is also finishing, doing fermentation and see how the fermentation can affect the extrusion to make fish feed and related to the project. Anyway, thank you so much, and I hope that I did on time. Yes. Okay.
Thank you, Osvaldo. So, Danyang, do we have some questions online? One. So, Keith, do you want to come off mute and ask the question, please.
Yeah, hi, thanks for a fantastic presentation, Osvaldo. Just by the by, this is sat on my desk. I don't know if you can see it. And it's a shame I'm not with you. I'll be able to get you to sign my copy. So maybe the next time I meet you, you can probably sign my copy. My question is with all your experience, etc., we're in a crazy world of lots of conflicts around the world. I enjoy chasing the science and the graphs. It satisfies my engineering interest. But if I was to take an extruder, maybe an InstaPro, taking Dennis's example and show it on the back of the car and on PTO, take it into sub-Saharan Africa, what proteins would you recommend that I would take with me to be able to convert food into protein to feed the millions that are starving of food in sub-Saharan? I'm not talking about feeding the fat and the wealthy in New York and London. I'm talking about how do we look at the future of trying to feed the populations that are starving, not necessarily that those have plenty. What would you recommend for me to take? What protein should I take in my truck with my Dennis Forte extruder to try and give food? What would you recommend, Osvaldo?
Yeah, thank you for the question, because it's a good one. You know, many times when I giving this presentation in the US, where they are telling me why you're working with protein in the US, which people are consuming a lot of protein, which is right. You know, I believe that, you know, your question is very relevant, because, you know, we have to be working for material that can be used in another country that they cannot get enough soy, they cannot get enough pea protein. And then, for example, hemp protein is one that is very important, because I don't know, I didn't know much about that, but, you know, in that conference in Minnesota last month, there was someone working in production of hemp, and they can grow without much water. The yield is very huge. It's like a wheat, you know. And then it's another product which is called Campanella, which is also coming out. In Africa, they are working with millet, with that extruder. There's not much protein there, but, you know, I would say hemp is going to be a possibility. The other crop that has not been utilized enough is sorghum. Sorghum is, you know, when I was at Purdue, there was a fellow that was a breeder. He got the Nobel Prize in agriculture. It's kind of the Nobel Prize in agriculture. He was developing some sorghum that was growing in Africa. He was from Africa, which didn't need water. And then I would say sorghum is a commodity that can be used. And then we are planning to use that. Again, you know, soybean is perfect for, you know, Ohio, Indiana. They love it, that part. Cannot be used in another place, and then we have to explore other alternatives. And then I would say hemp, sorghum, they could be good candidates. Thank you for the question, because it's an important one.
Thank you.
Thank you.
So one more, we'll do one more online, then one on the floor, and then I think it's time for lunch. So, Jason?
Hi, Osvaldo. Great talk. I only saw half of it, sorry, but hopefully I'll get a recording or look at the slides, because it was really good. I really love your work. And a quick question was really about your mini extruder. You said you use simple equation, or, you know, dimensional analysis, I assume, to scale that down. Everyone talks about the challenges of scale up all the time. It's hard to scale up, hard to scale up. Is this hard to scale up because people aren't using the mathematical equations, aren't using dimensional analysis appropriately? If you've been able to scale down, you know, humanly these things should be scaling up as well.
Yeah, this is a good question. Scale up is not easy. You know, before coming here, I was teaching a course in Argentina, and then they have a small extruder. It's about 16 millimeters, and they pay a lot of money for that extruder, but with the idea that you're going to be doing consulting with company, or helping the company that basically puts some money for the extruder. And they were having problems. For example, the extruder was working okay in the high moisture, was able to do a good texturized product. But many of the companies, they want to work with byproducts, which are high fibers, and they want to do expanded product. For example, using the rice bran to do an expanded snacks. And that extruder was not working. The main reason, I tried to help them. The main reason is you cannot achieve the pressure that you get in the die that you get in the industrial extruder. And then my point, and then the company came and said, you have to give a justification. I said, look, that extruder can help you to not to scale up, can help you to screen the formulation and screen the sun condition after you have to go and do in a large extruder, because I don't believe that you will be able to scale up, because you cannot reach a condition that you have in the real extruder. This is what, I like the extruder that we have, the Klextral 32 millimeter, because the next one in the line is an industrial type. And then the scale up is more easy in a way. And then I will say, when you are far away from your lab to what you want to scale up in the industry, it's going to be impossible.
So, yep, we got
just a comment on
the question.
Okay, let the question go
no,
first.
Comment first,
comment.
Then the question.
You can't scale up unless you know what you're doing at the small scale. This is where the problem begins. When we do work at the lab level, all we do is say, oh, it works at 300 RPM. We don't even know what that really means. So how do you scale up if you don't know what you're doing now? If you don't do the engineering, if you don't study the heat and mass transfer and the energy flows and everything else, how can you possibly reproduce the result at larger scale? And this is where we fail every time in scale up, because we don't know what we're doing in the lab or in the pilot plant, so how the hell are we going to reproduce it in the factory? And that's why we always stumble. And the products that are ultimately launched in the marketplace never reflect what was developed in the lab, because they all look lovely in the laboratory, but we don't know what we actually did, so we don't manage to reproduce it in the real world. That's the challenge. This is why we've got to go back to the rheology, to the fluid dynamics, to understanding the engineering at the small scale, and then future product development and future product launches will be far more successful.
Thank you. Yeah, it's correct. I would like to add, 300 RPM in a small extruder is not the shear that 300 RPM in a large one. Okay, and that's it. With that, you cannot scale up anything.
Okay, one question here, and then we'll go to lunch, and I'm sure there's lots more at lunch for you, Osvaldo.
Yeah.
Thank you very much. Actually, I'm interested on the fiber modification that you mentioned. So either before extruder or after extrusion, the fiber goes through changing through modification or through the shear or whatever happened during the extruder. Would that still have the fiber properties in terms of digestion, effects on our gut microbiota, etc.? Have you ever tested that?
We have, yeah, let me answer. You have two questions. The modification was done outside the extruder. We were planning to do inside the extruder, because the hydrolysis with sodium hydroxide, basically what you do, you have these arabinoxylans which are linked with ferulic acid, and then when you do the hydrolysis, you break the ferulic acid, and then you kind of solubilize the bran. And then we tried to do it inside the extruder, and it works. There was an issue with the, Klextral maybe. It was not a Klextral, it was a Coprion. Destroy the screw, when you use very alkaline condition. Not destroy, but you got to change the screw. And then you had to use a different type of screw, which are basically resistant. Regarding to the microbiota, when we did that work, there was a group in Michigan, University of Michigan, working with the microbiota, and they found that also the microbiota was favored when you are using branches, and then the corn fiber was better. There is a paper published, and I will try. I didn't put it because it's not my experience. I'm an engineer. I don't want to talk about nutrition much, but it has been proved. But now we want to prove a little bit more, and we have a proposal to be sent to look different type of fibers, following that paper of 2023, but doing the microbiota analysis. I don't know. We hope that we're going to be funded. Yeah.
Thank you.
Thank you. So thank you. Thanks, everyone. And I'm sure, Osvaldo, there'll be lots of questions for you and the other speakers during the lunch break. So for this, just firstly, a small token of thank you for thank you. And if you just join me in thanking all the speakers in that session, please.
Good afternoon, everybody, and welcome to session 3. I'm going to start because I'd like to start on time and make sure that everyone gets their time slot. And also for the people that are online, it's good that we're more or less starting when we should and promise. So welcome to the session 3. It's on challenges and opportunities for extrusion, process and products. What I'd like to say is that this is really a session that we would like to explore how extrusion can tailor food design, particularly for functionalities such as texture, taste, how it can release nutrients and flavor. Linking it to food design is really sort of starting to begin to get to understand what's really in the black box that is extrusion, so what happens in the machine, and actually can we use it sort of to design the structures that we want to get the functionality that we need. And today we're hopefully going to hear and probe some of that, at least around what sort of products are made and how we can identify or work with the product design. So it's my great pleasure actually to introduce our keynote speaker, Dr. Anneline Padayachee. She is, what she calls herself is the food and nutrition doctor. She is a nutritional scientist and communicator, and she is an industry consultant, and she intersects between nutrition, food technology and public health. So we're really going to understand a little bit more about how we can deliver nutrition through food design and processing. She has a PhD in plant bioactives and plant matrix, and she's got over 15 years experience working with the food industry, government, research and communities across Australia, APAC and Africa. And she says her work would be to explore how processing, food design and policy intersect with equity, bioavailability and cultural relevance. And I think that's really fantastic and a great introduction to her talk, which is, if I can just say, it is going to be around food processing to purpose, what extrusion could mean to nutrition access. Over to you.
Thank you, Ingrid. Yeah, it's good to be here. It's really good to be here at CSIRO. I was thinking when I walked into this room, I was a student here a long time ago, and I used to sit near that window and sleep. It's like, they've got a lounge there. I've got to pay attention now. So obviously, I've got some content in my presentation that touches on human nutrition, and we're all humans. And so I want you to be very clear, this is for educational purposes. I am not diagnosing any one of you. Do not take this as medical advice and decide to diagnose yourself. You can learn, talk to your healthcare professional, but this is for educational purposes, all right? Okay, so nutrition and food processing. And we talk about nutrition and we're looking at nutrients in food, we're looking at human health, disease development, and then you've got processing. And usually the two don't ever talk to each other except when it comes to nutrition information panels. And that's usually the consumer trying to work out what is on that nutrition information panel, right? So what we're going to do is we're going to look at exactly what Ingrid said, is processing for purpose. Not just processing for shelf life or longevity or being able to transport it to a different country. I was literally just yesterday on a ship, a live export ship, heading to Indonesia. I got off. The ship's still heading to Indonesia. Obviously, that's why I'm here. But you know, food is quite often it's transported. If it's not live cattle, then it's got to be processed in a way, packaged, frozen, so that it has the shelf life and the durability to get to the other side. So how do we actually start thinking about this a little bit differently? And I'm going to be real honest, nutrition is like the coolest thing at the moment, and anyone who's into nutrition, this is the time we get to shine. But it is not a trend. It's not here for now. It is here to stay. Like food safety is imperative. We don't doubt food safety. We don't think twice about food safety. Nutrition is here to stay. It's a strategy that any food company needs to get their head around. So before I go on to the next slide, I just want to get a feel for who's in the room. Hands up if you're industry. Okay, like engineering people? Oh, okay. Food technologists? Okay, academics? Okay, who else is there? CSIRO people. All right. Okay. This is interesting. Okay. Cool. Okay. Engineering. I've never actually presented to engineers before, so this is fingers crossed. Let's see if this works. All right. Now, I've broken it down and I've tried to, nutrition is not as straightforward as what's in food. Like a tomato has 100 milligrams of vitamin C. There is 20 grams of protein in 120 gram steak. That is literally the tip of the iceberg when we're talking about nutrition. And so I'm going to try and get you guys to understand the complexity of it and where does processing play in this whole mix, right? We're going to look at extrusion because it's a technology as old as time. It's been around for forever, but it has been used, you know, to create these amazing different types of food products that have really long shelf life. And yet it actually has a very good impact on human nutrition and digestibility and the release of nutrients in the human body. And we're so focused on really cool, new, novel technologies, nothing wrong with that, but we're kind of forgetting about some of these old ones that are well established and actually have a lot of really high value and a lot of high purpose. So before we kick off, we're going to look at the context and challenges that we have, because I know you may not think you're part of this, but you guys all have a massive problem, especially if you are an engineer. Even though consumers don't think much of you, they will never point a finger at the engineers, but they just hate the food industry in general. And the truth is, you guys create the machines, so if they really need it, if they knew, they'd hate you the most. All right? So, food factories, large processing plants. You see any documentary out there that's coming on Netflix, they all do not like processing anything that's in a factory. And we know that processing has evolved over time for shelf life, for durability. We've got all these cool textures. Food safety, definitely, you know, in the 1950s and 60s, that really came into vogue. And it has stayed that way. And now we've got consumers who pretty much have a brain at the end of their hand in the form of an iPhone or a Samsung, who are making these amazing decisions. If you think about, like, okay, hands up if you are under 30 years of age. See, come on, Sushil, I know you. We did our PhDs together. You are not under 30 years of age. The people who are under 30, 2100. If you eat right and move and sleep 8 hours a day, you probably will still be alive in 2100. Like, just get your head around that. I think I will be, I've worked it out, like 103 or something, and I intend to be here. But I'll be really old. But that's what we've got to realize, this reality, is we've got a different cohort of consumers who have access to information in a way that has never been done before. It is just there, and it's expectation. And so if we're not part of the conversation, someone is going to take our seat at the table, and they probably won't represent what the industry actually does. Yeah? So you end up with all these misnomers. Now, nutrition as a science is one of the newest science. It's only about 200 years old, and it was developed off the back of the periodic table. So when we discovered the elements of the periodic table, we were like, ooh, this is cool. Let's go see where it is. And then they found it in food and in cadavers and in diseases, and then kind of joined the dots and created this science called nutrition. And so if we look at how it's evolved over the eras, 1920s, we were really looking at nutrient discoveries, RDAs, so how much do we need to eat to prevent malnutrition. So addressing specific issues, so, you know, vitamin C and scurvy, calcium and osteoporosis, iron and anemia. So that's what the focus was on. But then we had the wars, and that wasn't that great, but we moved through the wars, and we came out on the other side of the Great Depression, and so boom, the baby boomer parents were booming because it was peace and prosperity, and there was a lot of money, and there was, you know, people had a more affluent lifestyle. They didn't need to use food vouchers as much. They didn't get ration packs. They could actually make their own choices. President Hoover, when he was a candidate, he actually used that as his candidate run for presidency. It was a car on every driveway and a chicken in every pot once a week. Because chicken was a luxury back then. And so you can see with this, you know, change in society, women entering the workforce, more food is available, yet they're not actually available to do the cooking, bake the bread, and make the KFC chicken. If Kentucky chicken was created in any other era, it would have flunked. But the Colonel was onto something. He saw women heading to work, and he was like, I got an idea. I will make them boxed chicken that they can pick up on the way back home. And so it had nothing to do with nutrition. It was just trying to solve a problem. And so we see a rise in chronic diseases. And so then that's like, whoa, this is new. We've never seen this before. We've got the medical world going, what is going on here? There's a change in the food supply, not just a change in society. They looked at the food supply. And so we've got issues with fat, sugar, and salt. And there is some legitimacy in that, for sure. So we come, we deal with that, and then at the same time, we're heading into the 2000s, and we're noticing different dietary patterns between cultures and regions of the world, and so we come up with dietary recommendations based on specific nutrients, which leads to the evolution of population health and food-based dietary guidelines. Gut health became in vogue because the gut microbiome received official organ status only in 2013. The newest member of the human body, even though it's been there for a while. We just didn't know that much about it. Looking at genotypes, omic technologies, which has led us to dietary guidelines based on food groups, specific for different regions. And now we're moving into a different era, and we're still doing all this stuff here. Don't get me wrong, we haven't stopped here. We're still doing research in all of this, but we're building upon it into the 2020s, moving into the future. Very much so looking at mechanisms of action. Personalized nutrition. So what do I eat for my body at 2:00 p.m. on a Monday versus what do I eat next year when I'm a whole year older on a Saturday? How is that changing internally? What do I need to have optimal outcomes, whatever that may be in life? And food system framework. So now nutrition is not just parked off in health. It is actually part of societal framework policy, because nutrition is not just about health. If you do not have a food supply, you don't have nutrition. If you cannot access the food, you don't have nutrition. If you poop it all out, you still don't have nutrition. And that's where the food industry has a really big role to play in this space. Now, this report was done by Lux Research, which is a really large research group in the USA, and they did this 2021, and they said the food company of the future 2050, this is the key things that they actually need to focus on: health, the microbiome, and future consumer centric, as well as the others. But developing food for health, not making health claims, but being specific, developing food for health is actually the future. And the reason why we've got to make that differentiation is because consumers are smart and they know stuff, and you can make your marketing claim and all you got to do is just open up a whole can of worms and litigation. So developing food for health, though, is showing actual beneficial outcomes. So, moving into the future, 2100, we're heading towards roughly about 10.8 billion people, and some of the people in this room will still be here, hopefully, and you will think back to this moment in time. How do we get to that point with the food supply that we've got, with the transportation issues that we have, with global geopolitics and all those sort of things? How do we get to that point with a growing population where we have a look over time, we can see where everybody is growing? So, all the different regions of the world over time. This is the number of people per kilometer of land area. So high density. I was just in the Northern Territory and I learned that that state only has roughly about 280,000 people in the whole state. No wonder you can drive for like 5 hours and not see a human being. But as you see where we're heading, there's two key things I want you to see. Number one is Canada and Australia pretty much don't change. One is extremely cold desert country and the other is hot desert country. So we say roughly about the same. But everywhere else, the population is growing. Especially in your places like Africa and your Asian countries, it's higher population mass, more dense. And so if there's more people taking up more land space, where do they get their food from? And what sort of food are they wanting to consume? Not what sort of food are they eating, but what do they want to eat? What do they need to eat? And where are they going to get it from? Even New Zealand's going to have more people than us. Like, I don't know how I feel about that, Australia. But we are a big desert country, so it's not like we can really be mass production of humans all over the place. We've got other roles to play in terms of probably feeding these population groups. Now, on one side of the fence, we've got a lot of people who are really hungry. This was just last year put out by the AFEA. So nearly 750 million people are in a chronic state of hunger with a high risk of undernutrition. So they're not eating enough food, full stop. 2.3 billion are moderately food insecure, so they can have some level of malnutrition. Anemia is actually increasing, and anemia is one of the biggest predictors of low birth weight babies and infant mortality rates. So mums need to get that anemia under control. And at the same time, we're actually, flip side of the coin, we've got over 1 billion people hitting the obesity markers simultaneously, happening in real time. So how does this oxymoron in society work? And this is where you've got micronutrient deficiencies on one side and then food abundance on the other side. Access to food does not mean nutrition. You can have a full belly and you can still have micronutrient malnourishment. You can have micronutrient deficiencies and or malnourishment. And so nutrition in food is not about the presence of food. Like there's the presence of food right there. We've got a fruit bowl just sitting right there, which is great. And we can all walk over there and access it if we choose to. But if that food bowl is caged up and all you can do is see it in the distance, doesn't matter that it's literally in the same room as us, emitting ethylene gas into the air that we're breathing. It means nothing because we cannot actually get that nutrition into us. It's about the quality, the formulation quality, and the accessibility. So, how does nutrition work? And I thought I'd put this in here because I did think that, there is going to be engineers, and I've never interacted with engineers before. So, nutrition in the human body is just a processing system. We got this really cool factory. It starts in our mouth and ends down the other end. The other hole down the other end. And in between it is this great processing system, right? So first thing I want you guys to get, and I use this slide all the time, we eat food, we do not eat nutrients. If you guys sat down to lunch and you got a pile of pills and some protein powder, you would all be complaining to Jordan how disappointed you are. I know I certainly would be. There's no pleasure in eating that way, right? So we eat food, not nutrients. But those nutrients, protein, vitamin A, carotene, dietary fiber, iron, are trapped in those foods. So you cannot differentiate those things apart. If you play with food, you play with nutrition. Now, quick crash course, just so we're singing off the same song sheet. When we're talking about nutrition, I know protein is like the flavor of the month and it can do no wrong. I was in the USA and they were marketing popcorn on its protein content. I'm like, seriously, dude? It's 97% carbohydrate. Why? No one eats popcorn for protein. You got your macros. Macro means greater than 1. It's big. We need it in more than 1 gram per day. That's why it's a macro. So your carbs, your protein, your fat, that is what gives us energy. Micros, we need it in less than 1 gram per day. So it's a micronutrients, that's your minerals and your vitamins. And then the non-nutrients is things like fiber, water, and your bioactives. So your micros split up between your vitamins and your minerals, your other compounds, and then your macros is the energy component. Like these guys provide more than just energy, but we do get our energy from our macros. And alcohol is not a macronutrient, but I did I did decide to put it up there because that's pretty much all it gives us is energy. It's empty calories, basically. At least with protein, yeah, you get, or fat, or your carbs, you do get your energy, but you're also getting amino acids that's doing something else in the body. So yes, that is the basics of Nutrition 101. You will all now not be qualified dietitians, but now you can think about your own diets when you're at home and doing stuff like that. When we look at these, so I'm just going to use the carbohydrates and proteins because that's what I'll talk a little bit more about. I'm just going to use them as examples. When we even go into our carbs, for example, we've got our simple carbs. So they're made up of one glucose molecule, a monosaccharide, or two glucose molecules, a disaccharide. They're really easy for our digestive tract to break down. In the monosaccharides, we can just absorb that straight up, off it goes. The disaccharides, we just need to split one bond, and then we can absorb it. Super easy for our stomach to break down. Then we have our complex carbohydrates, and they're complex because basically that's what they look like. They're just complicated. They're very big structures made up of individual glucose molecules in giant size form. And so we've got to work a little bit harder. We need some enzymes. We need to churn it over in our stomach a bit longer for us to actually break it down. You got to realize the digestive tract is not a stationary tract. You've got the stomach, it's moving through the 6 meters of small intestine, and then it moves into 1.8 to 2 meters of colon. It doesn't sit there. It is constantly moving slowly through. So it's not a static system. So that's why our body needs to work optimally. And ideally, the food needs to be processed optimally so we can get the nutrition out of it. And then we've got things like our dietary fiber that we cannot actually break down. So we get indirect energy when it is fermented in our gut. In terms of our amino acid, of our protein, so the biggest thing about protein is the amino acid content. So if it's got the amino acids that are in yellow are the ones that we cannot actually manufacture in the human body. We have to get it from food. There is no ifs, buts, or ands. We have to eat it. And so if a food contains all of those, that's called a complete protein. And if a food does not contain all of these yellow amino acids, that is called an incomplete protein. And so all you got to do is basically mix one incomplete protein with another incomplete protein, like baked beans on toast, and you can create a complete protein. The foods that have all of the amino acids that we cannot produce are, unsurprisingly, your animal-derived foods. So your dairies, your meats, your chickens, all those sort of things, because protein's in muscle, so that's why. That affects the quality of the protein, the amino acid composition. And then is this beautiful machine. Now, for me, this is the most important organ system in the entire human body. My sister's cardiac scientist, so she thinks the heart is the most important thing, but this is amazing. So you've got this cool machine. Think about it as another processing system. The stomach does the breaking down. And basically, it's a balloon that contracts, the muscles contract, it releases the acid into it, and it just sloshes it around like a washing machine, breaking it down. So what you've just eaten, that's what's happening right now. And if in about 2 hours' time we took a sample at the end of your stomach, it would look kind of like a chunky carrot soup. Yeah? So then it enters your small intestine, which is where enzymatic degradation happens, and absorption. So the enzymes are released. You can definitely see changes in your pH as well. The enzymes are released in 6 meters of small intestine, snipping it down into its individual molecules of amino acids or of individual glucose molecules, because then it can be absorbed across the small intestinal wall and into your bloodstream. And once it's in there, the body shunts it over to wherever it needs to use it. Whatever is not absorbed in the small intestine will end up in this beautiful one called the colon, which is where fermentation happens. And so the pH starts at about 5 over here, and because it's fermenting it and fermenting it and fermenting it, by the time it gets to the other end, it's down to about pH 7 because there's less fermentable content in that food, unless it is designed to deliver fermentation to the end. And that is actually really important because you want to keep your pH of your colon low to minimize the risk of different types of cancers. Increasing pH actually increases that risk. So this designing foods for health in mind is really important to know how this digestive tract actually works. So if we're wanting to get stuff in the colon, you want to make sure it's not absorbed in the small intestine. If you want to get stuff into the brain, into a new baby that's being developed in the womb of its mum, then you want to make sure it's getting absorbed in the small intestine. Through it all, we've got bacteria, different amounts and different families. And so, yeah, it ranges from your aerobics all the way down to your anaerobic. Further down the chain we go. So that is your digestive tract. If you start thinking of it as a machine, a processing machine, all we're doing is processing food internally to get nutrients out of it. And what we do outside of that, out here, is processing of food externally, ideally now to get the nutrients out in our body. So nutrition that's on the label does not necessarily mean that's actually nutrition in the body. The biggest factor that affects nutrition in the body is bioaccessibility, releasing it from that matrix. If it is not released from the matrix, I actually had a different slide in here. I took it out because we're after lunch, and it was a beautiful stool, a real stool. And so I thought, yeah, that's probably not going to be that great after lunch. But if it is not released from the matrix, that's all you're doing is you're making good quality poop or peep. One of the two. We should collect it and use it for, manure or something like that. But we want to get it out of there. So let's have a look at, now that you've got the nutrition understanding, how do we start thinking about processing in a different way? So, is processing the problem or is the formulations the problem? Now, you don't need to live under a rock to know that the processed food industry is probably one of the most hated sectors in the entire universe. Okay, you guys are all from hell. We're killing people. We are all money-making evil machines. And so you can kind of see that, you can understand where this idea comes from. If you look at the diets over time, so hunter-gatherers versus the agriculturalists, how it started, and modern affluent societies, there is a difference in the nutrition components in those diets, right? Because the food supply has changed. We're moving from running around and eating, a deer once every 3 weeks and lots of tubers and berries to just literally going to the shops and getting sausages and whatever you really want. Just go pick what you want and you can eat it in an instant. And it's always available. I don't need to hunt for 3 days to get it. So that has definitely changed. And so with that, we do see changes in our chronic diseases, right? So is processing the problem, or is food accessibility an issue? Probably that. It's a good issue to have. Or is the formulations an issue? And for a long time, we haven't actually considered the nutritional component to the processed foods that we have out there. When we look at how food processing has evolved over time, so at the top, I like this graph, but it is very confusing at the same time. So we've got right at the start, hunter-gatherers, all the way through to high income, globalization, today's world that we're living in. And you can see the types of processing that has evolved over time. I mean, the first refrigerator was only in 1874. That's Maggie stock cubes, 1908. There you go. First breakfast cereal, 1912, Kellogg's. So that probably used extrusion or something like that. How that's evolved. We've moved from dealing with a consistent food supply. That was the issue we were trying to do then. Once we got that right, we tried to deal with a safe food supply. That was the issue. Foodborne illnesses was the problem. So we're trying to deal with that. We figured that out. And then we started focusing on convenience. How do we make it readily available all the time? And so those things will never go. We need that. But now we also need to add this health level to it. So, consumer sentiment, you hear it all the time. We're going to have the health star ratings may become mandatory come November. We'll see how that goes. And so consumer sentiment is largely distrust. I don't know what you do. It all happens in a factory. I don't understand what those ingredients are. That sounds like a whole list of chemicals that I probably used to clean my pool with. how can I possibly eat it? And so then you've got these nutritional scores that is meant to try and make them, understand. And so different countries use different ones. No, we don't use the NOVA system over here, but NOVA definitely has been probably the biggest hurdle, and it still is. And then you've got all your influences, especially in the medical world. So this is one of the leading anti-food industry influences. He is a medical doctor, and he's not practicing as a medical doctor. I think his specialty was viruses or something like that. And so, you can look, this was just a year ago, 1.1 million views. And so when a doctor speaks about health, you listen, because we go to the doctor for health advice, right? When a food engineer speaks about food, no one listens, because food engineers generally don't speak about food. I liked what Nana said. We've got to start communicating better. We've got to get out there. And it's not just get out there and tell our story, but it's about being strategic in helping consumers to understand what we're all about. So these are the health scores that are happening all around the world. So this health star rating is not a unique thing to Australia. The countries that are in pink is where it's actually mandatory. The countries where it's orange, currently, up until this moment, is where it's voluntary, but November it may change for us. And so you can see it. It's very, they're aiming for the same thing. They're using a lot of the same data. It's nutritional content in food, and giving it a nutrition rating. But it does cause a lot of problems, because a consumer might say, well, this box of breakfast cereal, Kellogg's cornflakes, has scored a 3.5, but my steak that's unprocessed has scored a 2. How does that make sense? The industry is paying for this. So there's this level of distrust purely because they don't understand that you're meant to compare breakfast cereals with breakfast cereals. You'd like to hope that, you don't go buying breakfast cereals in the meat aisle, but there's a level of education that consumers need as well. Now, I thought this was fascinating. This just came out about a month ago. Articles on ultra-processed, and these are not necessarily food technology articles. This is also medical science-based articles, is increasing astronomically ever since about 2010 is when Montero, the guy who came up with the NOVA system, he published his first paper roughly about, I think, 2012. And so ever since then, it is one of the biggest trends on PubMed. So if you want to really get your paper out there, just put ultra-processing in it, and you'll get picked up. So we've learned about what is extrusion, and in all honesty, it is a methodology of ultra-processing. If we were going to give, if you don't know what NOVA is a classification based on the degree of processing. So foods in, sorry, I'm seeing a couple of blank faces. So number 1 is raw ingredients that have not been processed. So think about, just gone blank. Fruits, your vegetables, things like that. So those are number 1s. Number 2 is called culinary ingredients. So salt, oil, flour, things that you wouldn't eat a spoonful by, but you need them in other foods. Then number 3 is processed foods. And so that's when you take number 1 and number 2 and you make number 3. So like a breakfast cereal, yogurt, those would be category 3. And number 4 is foods that are based on 3 and possibly 1 and 2 as well, and do not look like anything you can identify with. So cake mix, lollies, cupcakes, potato chips. Like a potato chip doesn't actually look like a real potato. Pringles, those are sausages. Those are considered your ultra-processed foods. So it's based on the degree of processing, not on the actual nutritional composition. And yet it is used as a method to explain nutrition, even though it's not based on nutrition. And so obviously, anything that's processed comes out looking like it was created by the devil itself, right? You'll have a bright red sign on that product. So looking at where does ultra-processing and extrusion fit in, well, extrusion is literally creating extremely, I'm not even going to call it ultra-processed, this is extremely processed food products. That whole process, that even, you guys might think this is a work of art, but taking yourselves out of your role, if you showed this to any person out there, they would be mortified that their food was manufactured using this. because it's nothing that they can actually relate to. So that's why it's a bit of a problem. But what we need to show is that this is more than just about making cereals or shelf-stable and efficient methods, even though it is that. It actually does improve digestibility. It does improve bioavailability, especially in our grains, which is where we've got a bit of a problem with digestibility. Now, some of the slides I'm going to show you are very intense to look at. I could not work out a better way of presenting it, so I have had to cut it out of the journal article, so they're a little bit intense to look at, but you'll get the point of how I was going to say emulsification. What was this? What technology? Extrusion. Well, how extrusion actually does this, right? Oh, what happened? My slides have gone, so thank you. All right. So let's have a look especially at our grains. So with our legumes, like your chickpeas and your pulses, things like that, you've got roughly about 17 to 30% protein content. Your grains, like wheat, barley, they're about 50% less. These grains are rich in lysine, so that particular amino acid, but they're poor in sulfur-containing. So the cereals, are low in lysine, and they're deficient in sulfur-containing amino acids, whereas your legumes are rich in lysine. So when I said to you about your different types of amino acids, they're indispensable ones, the ones that our body needs, this is what I'm talking about here, right? Now, how this works, what does protein actually look like? Like you had some chicken, if you've had your pasta, there's protein in that. What does it look like? If we had to look at it, it looks like this. Okay, it's like a ball of wool that is tightly wrapped around itself. And so in order to get these amino acids out of this coiled up ball of wool, we've actually got to go all the way to an individual strand, because there's the individual amino acids, and the enzymes come along and snip it up like a string of pearls, and so our body can actually absorb it. And so this is what happens during extrusion. You start off with that really tight ball of wool, and during that shearing process, it actually uncoils it, that's the right word, into these individual strands. And then our body, at a pH 2, which is what our stomach is, can actually uncoil it further, allowing enzymes to actually get in there, break it down, so we can absorb it. So this technology is working with our digestive system. It is doing it super well when it comes to these legumes. Now, this is why I said this is a little bit wordy, these slides, but bear with me, right? So, you asked the question about digestibility of nutrients. Someone asked it just before the last session. Yeah, so here we go. We've got different types of beans, chickpeas, faba beans, and this is looking at the effect of extrusion, and these are all your different conditions of extrusion. Firstly, on the amount of protein that is in that product. And so this column, it just basically says that they could not see a change in the protein content in that product. But over here, now this is done through in vitro digestibility, so ideally we'd put it through a human and collect a sample out of their gut. What we have seen is consistently under in vitro digestive conditions, an increase in the bioavailability of protein. So instead of making really high quality protein-rich poop, if this was in the person, they would actually be absorbing more of that protein because of the use of extrusion on these particular grains. So that's protein. You've got your kidney beans on the other side as well. So it's amazing across the board. 5 minutes, cool. This is for dietary fiber. So the effect of extrusion on dietary fiber, in some cases it has increased the soluble dietary fiber. So that's the dietary fiber that gets into your bloodstream, absorbs cholesterol, and essentially poop it out. The insoluble dietary fiber, that's the stuff that gets into your colon and ferments and feeds your gut bacteria. So what we're seeing is that it does vary. It does have a differing effect on both insoluble and soluble fiber. And then this one. Now, if anyone's ever had IBS, it's not fun. But IBS is a problem for a lot of people. Irritable bowel syndrome is the terminology we give to someone who's got digestive issues that we cannot actually define. Can't say you've got cancer or something like that. We don't know what's wrong with you, but you're bloated, you need to eat and run to the toilet, or you're constipated for days on end. It is a real problem. And there's not much medication you can really do for it. Unfortunately, the legumes are one of the biggest triggers for irritable bowel because it has these compounds called oligosaccharides. And they are actually sugars that we don't absorb very well in our body. So they last through the small intestine, end up in the colon, and provide it's like, you know, giving up your 3-year-old a big bag of jelly beans. They just go hyperactive. Same sort of deal in the colon. And so with extrusion, across the board, there is actually a decrease in the oligosaccharides for all of these different types of legumes. So we can actually create products that are suitable for people with irritable bowel syndrome and help them to eat some of these legume products. And then lastly, the anti-nutrients. So these are nutrients that actually work against the nutrients that our body needs. They will bind them so we can't absorb it. That's pretty much what they do. That's the main thing that they do. So these are different types of anti-nutrients, and they are predominantly present in grains and legumes, not so much in meat type products. And so that's a problem. Yep, cool. And so across the board again, we see a decrease in the anti-nutrients in the grains that have undergone extrusion. So if you look at it from all different angles, this is actually a very cool processing technique. It does generate some heat, so some of the micronutrients do actually decrease overall, but horses for courses, right? So we've got to see, how does this fit into the human body? Now that we're starting to think about processing from a different light, how does this technology work with what we've got in here? It is literally trying to unlock a lot of these nutrients from the matrix, which is super important. So I'm nearly at the end. And I want to finish with this story because I think this actually hits really home. So this little kid, you think he's malnourished and he hasn't got enough food. That's not true. He's actually eating sufficient calories. He's got a condition called protein energy malnutrition, which means he cannot actually get the protein out of the food he's eating. Heaps of starch, but not enough protein to get it. So he can't access the energy. And so that's why he's severely malnourished. They don't survive past 5 years if they're lucky. So this particular pediatrician, he worked for the WHO. He saw this in these third world countries and refugee camps all around the world. And you can save them. You've just got to put them on an IV drip. But how do you get that into all these places? So he told his friend, who's a food scientist, and he actually made, I think he was involved in making Nutella, about this problem that he sees with these kids. And so his friend, he was like, I think I can solve this. And so he created a product. Now here is a child. This is in 2022. She's a year old in Haiti. 4.5 kilos. You can even see her digestive tract, right? They put her onto this product. I'll show you what it is. 3 times a day, and this is her after 12 weeks. And once they get to that point, they can start eating normal food, and their stomach can actually absorb it. It's called Plumpy Nut. And basically, it's peanuts, skim milk, powder, lots of sugar, and some vitamins. It is an extruded product because that actually helps to release these amino acids from the product. So I'm going to finish with this story. Just lasts a minute.
My name is Bello
he has a
Tabedjena.
really good thing to say.
I come from Ethiopia and represent a company called Helena Enriched Foods.
He's actually an engineer as well.
Involved in the production of nutritious products. We are the first Ethiopian company producing RUTF. We started with iodizing salt until we embarked on a franchise agreement with Nutriset to produce the popularly known product Plumpy Nut. Malnutrition is a very severe problem, and from the Millennium Development Goal, there is a big plan to fight malnutrition in Africa, and especially in Ethiopia, where its high prevalence is observed. And this product is a very important intervention. We expect increased production where it belongs. The need in Africa for such type of products is great, and there is a growing understanding by our governments for such type of products, and they want a quick response. And we expect also from
quick response in
Nutriset
terms of nutrition
a similar quick response
uptake.
to increase the production locally of such products for the really abundant, needy population of malnourished children. In addition, these products have got a lot of connections with agricultural products in agro-processing. So the government looks in that direction as well.
So they grow the peanuts in Ethiopia. So it is actually a combined effort between farming and agriculture, food processing, and public health nutrition simultaneously. So I want you guys to just think about this. This is an example I came up with. So we've been doing extrusion. We've created this sort of bar, simple ingredients that we need to make the bar, but it's got minimal nutrient density and absorption. So it's just a fancy luxury, really, a cheap indulgence, versus using the same technology and thinking about how does this get absorbed, building that into the formulation and the processing so we can actually create nutrient delivery systems that are also relatively affordable. Moving from using it as a tool for cheap products to actually using it as a tool for nutrient accessibility. Now, I said must because I'm a purist. But if you're unable to do a must, this article's just come out by Mike Gidley, and we're done. And he was talking about how we need to actually put this on labeling, nutrient release. So this is the next iteration of the health star ratings. So if you don't understand it now, it is coming, and then you'll be forced to do it. So we have to get on top of it. So lastly, before my last slide, if it can't be accessed, you can't absorb it. And I thought I'd get you guys to see how you fit into it. We're all actually part of the same system. Nutrient release is down the other end, and here's the extrusion. It starts the whole process off. So I've got 4 questions that I would like you to think about if you're doing research and if you're working in industry. Stick this on a Post-it note. How can you actually do this answering these 4 points? And if you can do that, you can be one of those 50 companies that Lux Research says will be nailing it by 2050. Done. Thank you.
Thank you. Thank you. Thanks very much, Anneline, for a really entertaining and very informative talk. We've got a couple of minutes for a quick question, and I'm asking anyone who's online first if they've got a question either in chat or...
Yeah, we do have online questions in chat. Say, pasta is extruded. Would one consider pasta ultra-processed, or it comes down to the number of additives?
No, so it's not coming down to the number of additives. It is based on the degree of processing. That's what the NOVA definition is based on, the degree of processing. So yeah, it would actually be considered an ultra-processed food product. It'd be classified, if we're going to go by NOVA, it is a number 4. Especially your bow ties, because I mean, really, where do you see bow ties in nature? So that's the other component, is it identifiable? Or I've never seen it before, so your little smiley faces, as cute as those are, that would be, according to NOVA, part of the UP4 category.
Okay. It can be quite there's a big topic on whether you agree with NOVA or not as a way of classification of processed food. Are there any questions in the audience? There are.
I'm also here tomorrow.
Pablo.
Great presentation, Anneline. Thank you. So prebiotics. So you mentioned irritable bowel syndrome as a, prebiotics as a disadvantage, and then the decrease of the prebiotic, if I understood correctly. But what in terms of having a prebiotic oligosaccharide? I was thinking more, oligosaccharide as a prebiotic, right? No, it's not?
No, that's not a
Is
good
that
thing.
correct?
Yeah, so I guess you could say it does have prebiotic behavior, because a prebiotic is anything that your gut microbiome can ferment. But in the case of this, it's such simple sugars, super fermentable, unlike your dietary fibers and your resistant starch that takes a long time to ferment. It's like literally getting a 2-year-old and giving them a giant size injection with a big bag of jelly beans. Your bacteria just go off the charts, and they produce a lot of gas. And then so individuals who've got IBS, not only are they have lots of flatulence and diarrhea, like they will literally extend out. And that distension affects how they can breathe. So some people have to go to hospital and get oxygen because they struggle to breathe because the bacteria are just having an absolute chaotic party on the inside.
But
So
if you don't have
oligosaccharides,
IBS,
yeah, if you don't have IBS, you should be you eat chickpeas and you're fine. Yeah.
and it's something you want to preserve in an extruded. That's where I was going.
Oh, do you want to preserve
Yes.
those? I wouldn't say it's so much if you want to preserve it. You're not going to absorb much of it in your small intestine, right? So if it's not absorbed, your body won't use it anywhere in the body. It will end up in your colon and it will be fermented by your bacteria. And so yes, there's a bit less to be fermented by your bacteria, but that's not a big deal because you're having other food products with your resistant starches and your dietary fiber. So for a person who's got no issues in their gut, they're still okay. But a person with IBS, those foods that have that in there are totally off limits if it's really bad. Yeah.
Okay.
And unfortunately for them, they're just left like, you just can't eat this, you can't eat this, you can't eat this, you can't eat this, you can't, like everything is almost poison. And they're not going to die, but they're in a lot of discomfort.
All right. We'll have one more quick question from this gentleman here, and I'm afraid we're going to have to ask questions afterwards because we're running out of time. Have run out of time.
Okay, yeah, a very good talk for an engineer. I learned a lot about nutrition. But I don't agree with the qualification of super process.
Yeah.
I believe that the number of ingredients is the problem.
Yeah.
Because, at home, if you get to do pasta, that example, you get the flour, you cook it, you apply heat, you apply shear to make the dough, and it's no super process.
Yeah.
You do the same in the extruder. But what happened is since I do in extrusion to do meat analog, I go to the supermarket and I look all the commercial product, and then the product they have less amount of ingredient was 25, which is including carbometric cellulose, which is they use also for painting, siloxane dioxide, which is used also for painting and for cleaning.
Yeah.
And then I believe that is the problem. And then in this NOVA approach, I think that they are not counting the processing. Now you mentioned today, it's a lot of anti-nutrient that this has been improved, this stability, and they are not counting in the equation.
No. I don't necessarily agree with that.
No, I know.
But
I mean,
unfortunately, it is a problem, and
It's a problem.
you've got your health influences are probably the biggest issue because they've latched onto something that looks really bad, but they do not understand food processing and food components.
It's correct. Yeah.
And that is driving a lot of policy change as well. And so unless, like I said earlier, if you're not at the table, someone else will take your spot and probably misrepresent you. And then the food industry on the whole, we have to navigate it, and we're disempowered, and we probably will end up doing stuff that does not actually help nutrition delivery. Like anti-nutrients is a big problem, and extrusion will help that. But yeah, you're exactly right. It's a big problem.
Okay. I'm going to have to shut the conversation down, but please catch Anneline to ask her further questions. She's going to be hanging around. Thanks. Let's everybody thank Anneline again, please. I would like to introduce our next speaker. It's Professor Peter Halley from the University of Queensland, and he's going to be talking about scale-up extrusion. He's going to show some case studies, which I always love, actually, about low and high moisture extrusion.
Green and red. Just test it. That's the pointer. Oh, yeah, okay. Green, yeah, no, there's two. Oh, there's one, but that's the big. You mean the big one? Yeah, that's right. Sorry. Thank you. Big green. Hi, thanks very much. And thanks to Jordan and the team for inviting me down at almost the last minute and squeezing me in. I've never been squeezed in before as much. Yeah, so today I'm sort of, I should be honest and say that I'm a practicing polymer scientist, but I've been working with Jason Stokes up there and the team at Faber. Samira is one of our key people up there as well, continuing, I suppose, the work on extrusion of biopolymers. We've always done work on starch-based polymers. We also had some people, Professor Peter Torley, I think now at RMIT, and Professor Polly Bury at USQ, were in our labs as well, and also was always working on, well, some of us were doing starch-based biopolymers, some were doing starch for food applications, but our common tool was the extruders, the single screw, the twin screws, the injection molded articles. So we've learnt a lot from each other, looking at different applications on starch-based materials, and now sort of extending out through the fantastic funding from FABA as well. And as you may know, FABA is one of those accelerators that are trying to get universities to help partner with startup companies to get through that higher TRL valley of death, they used to call it, in terms of funding, but also valley of death in terms of proof of principle of scale up. So this is a bit of a journey, so stick with me. I'll switch between biopolymers and our current examples. So the case studies will be both bioplastics and food related. But let's say for the first series of years, I think the CRC food packaging started in '95. That shows how old I am. But what happened, and I think you'll hopefully see a commonality perhaps, is that the CRC food packaging established us, got us a lot of extruders. We added on with those other funding schemes throughout the years, through Biotechnology Innovation Funds, CRCs, ARC funding, Australian Research Council, all the way from '95 to now. And I'll come back to why that's important to actually understanding truly a system, and had a range of different industry partners. The first two were the original partners, and then they left, but we spun off a company anyway, Plantech Technologies, that still develops starch-based biopolymers. But the key steps here were that we were doing a lot of things at once. So I think people have mentioned this today about laboratory work, pilot scale work, full scale, scale-up work. Which one do we need to do? I think you need to do them all, because you learn so much in each different stage. So I'll just go through some of the examples where we looked at model systems, took that to lab extrusion, took it to pilot scale, if you like, and optimization of that extrusion, and then actually did some toll manufacturing with some partners as well. So for this biopolymer example, we initially collaborated with CSIRO Plant Industries. I think Matthew Morell was down there. He's now up at UQ Coffee. But he had a range of different types of starch materials. We were looking at different types of starches industrially in the CRC, but he had some genetically modified or biotechnologically modified starch materials that would alter just by changing or blocking some of the branching or debranching enzymes. He could have a very controlled way of developing a starch with a certain amylose to amylopectin content, so the linear or the branched types of chains in starch. So we learned a lot by having very small amounts of these starches, model starches, maybe grams, but we also had this very small or Thermo Fisher now, I suppose, mini lab extruder that we were able to really look at some extrusion of very small samples, and we had a very nice FTIR optics unit on the recirculating zone, so we could really understand what was going on with some of these very, very small amounts of model starch materials with their varieties that he was controlling very well. So it was very, very controlled changes to the amylopectin and amylose content in the starch. So that a lot of learning started at that very small level. We understood about the structural order. We were able to do X-ray diffraction and NMR tests. Mike Gidley and a PhD up there, Iwatan, developed a new technique to be able to really dig into the X-ray diffraction with the NMR data to pick up the different types of helices that were being developed. There was an increase there with amylose content in a certain type of crystallinity polymorph. And they really just understood a lot more about these very model, or these small changes were made to the starch so that could help us. That we're not scaling up yet, we're just getting an understanding, I guess, of the starch material. Then I guess take it to the next stage, and another PhD comes along, Neil, working with Bob Gilbert up there at Coffee when Bob was there. This is sort of a smallish scale twin screw extruder, And essentially we were looking at a single type of temperature profile. We were just interested in what happens to the to the starch material as you go down the extruder. So this is 60% starch, 20%, almost 30% glycerol, about 10% water. It's a starch-based plastic mix, and we wanted to know what was going on because we'd had some successes with high amylose starch in some of our industrial work and the scale-up work to make blown films or to make extruded cast film. With Plantech, but to be honest, we didn't really know why it was happening. So we sort of used this extra, or next level up, I suppose, extruder to sort of try and understand what's going on. And we would stop the extruder. I think Sushil said that today. Sometimes you just got to open the extruder and see what's happening as it's going along. And they were able to stop the extruder, open it up, take samples, and actually try and determine what's going on. Now, it might be a bit hard to see that. I've forgotten which button I'm supposed to use. That's the light, that's it. Can't see. That's okay. But what have you got there from left? Left is the highest amylopectin, so it's the most branched material, and that's what the molecular profile. So it's the radius of gyration. Sorry, wrong way around. But anyway, but what's happening is there's a lot of material as you're going down the extruder that's actually dropping in molecular weight. So the high branched amylopectin material was showing a lot of molecular weight degradation in the extruder as you sampled it as you're going down. When you started to go to 55% amylose, the more linear chain, or even the 85% amylose, there was much less degradation, much less molecular weight changes there was more amylose content there now, so much more less breakdown of the amylose. That taught us why, for many years, we were struggling with some of the waxy maize starches, the very low amylose content starches, why that wasn't performing well in the extrusion trials or in the film blowing trials. We had to actually do this work to actually inform some of the industrial work. So I always like to say that there's learnings to be made at each level that help the other level, help like the scale-up level. And then I guess you go to the larger scale. So this was with our Entech, I think it was, larger scale extruder. Plantech, who was starting to develop the film, really wanted to know, yes, this is all good, but what's the optimal screw configuration for perhaps mixing and blending, and I dare say almost gelatinizing the starch material, but not making it thermally degrade in the extruder. So essentially, it doesn't give you much information, does it? But it's just saying that with different numbers of screw configurations, there was an optimal, I guess, configuration based on peak cold viscosity that's measured through RVA. But then if you went too harsh in the profile, you actually saw these properties falling away. So once again, I suppose that's the information you got from the pilot scale. Oops, sorry, the pilot scale work was to really understand, okay, with these different configurations now, can we change the formulation a bit? Can we look at the moisture content that the starch material was put into the extruder with? How does that change with configuration? We're measuring basically the SME as well, because that's always a very good measure to see how much specific mechanical energy you're putting in to your system, to see it change, to see it perhaps hopefully turn into a thermoplastic starch material. But then you could go too far and you could get much too aggressive screws that would actually show more degradation of the starch. So once again, we were sort of using the 3 levels of extruders to give us more and more information about what would help us when we went to large scale. So hopefully that's what we're going to do now. So we've had good funding from FABA. We've set up people. We've set up the systems. We have a smaller scale Thermo Fisher extruder at UQ, and out at DPI we've got the joint UQ DPI Klextrol machine. We're hoping basically to try the same thing. So to understand information about, say, initial systems formulations in the small scale extruder at UQ, and then understand how can we optimize extruder conditions. We can play around with that extruder at UQ with different screw configurations, screw temperatures, and then we can go out and see how that would work in the pilot scale Klextrol machine. So I guess I'm trying to say we're trying to use the same principle or same path out there. We have the setup now, the pilot scale extruder at DPI with a joint arrangement. They give us the space and look after the space, and we bring the operators out, and they bring their operators as well. So it's a typical, but you all know what that means. There's a typical extruder configuration out there. We've tried a number of things, but as Samir and I were saying, we can't really talk about much of the confidential stuff, but we can give you an outline at least. I don't think I need to know, you guys don't need to know why extrusion is good in terms of applications and why continuous processing is good, if there's a few chemical engineers here as well. But basically, we've looked at different types of examples. One was texture modified foods to sort of create more calorie dense foods. We'd done a lot of work with Jason and myself on texture modified foods and the rheology of them in terms of their swallowing behavior, but this is now to try and develop similar types of products on this continuous extrusion line. So that's sort of one of the areas we've started looking at. Also, Sam's background is a PhD in reactive extrusion too. So we always know that the extruder is a reaction vessel. It can change both physiochemical properties of materials. So we started off looking just at some examples with texturized vegetable protein materials. And looking basically at the effect of different types of soy protein isolates. But if you come to Eiffel's talk tomorrow, he'll talk you in much more detail about his work linking fundamental properties like rheology to extrusion processing for these different types of materials. So once again, a sort of a smaller scale information going to lead to knowledge for us when we're doing larger scale trials with these types of materials. Also, I guess low moisture extrusion work, pea protein isolates, soy protein isolate I've mentioned before. There's trying to overcome some of the difficulties that we've had with feeding and is ongoing out at 3 minutes to go too, out at Cooper's Plains in the larger extruder. I think I took off this little video, didn't I, Geordie, to save time, which is great. And I guess this was doing a third trial to try and really understand things like changes in moisture and understanding how the overall capacity of the material was flowing through based on what we could change for the industry partner formulations. And I think also just to touch on the other project that is starting to look at more high moisture extrusion. It's really interesting for a polymer melt extrusion specialist like myself, coming from a single phase perhaps system. These systems aren't single phase. They're very multi-component phase materials, probably more related to polymer composite extrusion and manufacturing. But anyway, we're at least starting to understand how those physiochemical changes occur and what sort of shear conditions we can change to produce that material, and then starting to think about playing with the longer cooling dies. I say longer. It's longer dies than we're used to in polymer extrusion, at least anyway. And yeah, I think this is just more of an example of where we did alter the formulations and then just had a look at the different textural changes. So I suppose I can't really delve too much into the exact formulations that the partners are doing, but let's just say that we're using the same, I guess, understandings that we've had developed before in the biopolymer work to the new food systems, and hopefully giving companies confidence that they can extrude their materials, but also doing the small scale work to understand why they're seeing differences in formulation changes in their pilot scale extrusion as well. And that's obviously some of the things that could be happening during an extruder, both on a physical and a chemical level. And I think I've already covered oops, these two slides are probably too long, and I'm running out of time. And you don't need to know all of the different aspects of reactive extrusion as well, but let's just say that I like extruders because they are continuous processing and scalable, but you can also make the chemical modification as well at the same time. But that's all I've got, so thank you.
Thank you very much. And as we've just got time for one question, so is there anyone online? No? All right, from the floor, please. Anyone? Sushi.
can speak louder. So Peter, so you are a guru. You know, very insightful. So my quick question, Peter, is like you have a process 11 at UQ St. Lucia and cholesterol at the DPI, right? Both are a different extruder. They have a different screw profile, a different geometry. Everything is different. Nothing works similar, right? How do you link process, not 11, I think 16 to cholesterol? So what is the linker between these two?
Yeah, sure. Sure. Look, I like going back. Yeah, I ask people, don't get too confused about, I want this result here and this extrude and this formulation to actually be scalable to that. People do that, and people can do that with dimensionless analysis that I think one of the questioners said today. You can do that, but you can also get a lot of information off different machines anyway. So like at this scale or at this kilograms per hour or this formulation size, I can understand a lot about that, you know, that smaller scale extruder, what is it, the 18 millimeter diameter perhaps? AFEA will tell us tomorrow. Versus, say, the 28 millimeter, Sam. So I can get different information from both of those tests that will help me eventually. Because in Plantic, we didn't actually understand until we went off to a 54 millimeter toll manufacturing compound what really was happening. But I think you understand what's happening here. You can match it with some characterization. You understand what's happening here with some background from the first level of understanding. So I think you're just building your understanding. I don't think you have to have, you know, the exact same. It's not like chemical engineering scale-up where you're using the dimensional analysis and you really need to know exactly what size changes are. But yeah.
Go on, quick.
A very quick one. The answer to your question is the extrudate does not know the extruder brand. End of story. It only sees shear and temperature profile. That's it. Yeah. No product drops into a screw and says, "Ooh, it's a French piece of steel, it must be good." Or, "No, it's Austrian steel today, it's going to be different." It is just a damn extruder. A spinning screw inside a barrel. It might be co-rotating, counter-rotating, single, twin, French, German. I don't give a damn. It's just shear and time, temperature and pressure. Full stop. As soon as you start thinking this way, you'll start applying decent engineering approaches to what you do, and you'll stop talking about brands of machine. Don't use the fact that you've got a whatever Thermo Fisher or whatever brand. Yeah. That is bullshit.
Thank you.
Stop.
I think we'll leave it at there. Thanks very much, Dennis. I think we've got the point. Thank you. Thank you, Peter, for a great presentation. Could I please ask the next presenter who is online? It's Domas Gali Patria, and I hope I've pronounced your name well. Sorry if I haven't. You are from the National Pingtung University of Science and Technology, and he is going to talk about the impact of feed composition and extrusion, conditions of high moisture TVP properties via single and twin screw systems. Over to you.
Okay, hello everyone. Can you hear clearly my voice?
Yes, we can.
Yeah? Is my voice clear? Okay. Okay, let me try to share my PPT. Okay, good afternoon everyone. Before I start my presentation, I would like to say thank you so much for the organizing committee, especially for the CSIRO and then Australian Food Engineering Association, who provide this great event. And then special thanks to Dr. Jordan Panel, who kindly act a bridge between me and then this event. Unfortunately, I cannot attend this conference because you know that I don't know why I have no difficulty to get my visa. Anyway, but thanks to the committee who still provide of or give me the opportunity to share my works by virtual. Okay, actually I'm a PhD student in under supervision Dr. Jian Lin, distinguished professor from Department of Food Science from National Pingtung University of Science and Technology, Taiwan. This is my academic background. Actually, I got the scholarship from National Science and Technology Taiwan for my PhD since 2022 until 2026. Then last year I attended the 22nd World Congress of Food Science and Technology, IFOS conference in Rimini, Italy. Okay, this is my published work in recent 5 years. Actually, we work on the puff snack, rice analog, pasta, and then noodles. Yeah, of course, we our field is food extrusion, so we produce all of this product by extrusion technology. However, for the currently, we focus on develop the plant-based meat production via cooking extrusion. In our lab, we have two type of the cooking extruder. The first one is twin cooking extruder, model process 16 parallel by Thermo Fisher Scientific from German. And then the second, for the single screw cooking extruder, we have a model TYE30 made from the Taiyu industry. That is the local company in Taiwan. And then this research, maybe I will explain how we will compare to between the twin screw and then a single screw on producing TVP. Okay, we talk about the role of the meat and processed meat in global consumption. Meat offer high quality protein and essential micronutrients vital for global dietary requirements. Desired texture, juicy, tender, and savory flavor contribute to high consumer acceptance. And then grilling and roasting enhance its rich, appealing aroma, driving culinary preference. But we have the challenge on the meat, yeah, especially for the livestock farming, contribute significantly to greenhouse gas emission, impacting global climate stability. And then ethical consideration regarding intensive animal farming practice are prompting consumer and scientific attention. And then the last one, definitely excess consumption of red and processed meat is linked to various health risks, including cardiovascular disease. If we talk about the environmental, you know that for produce 1 kg of meat, it needs approximately 6,000 to 14,000 liter water and 3 to 8 kg feed. So what the meaning? It's meaning actually this will be a competition between between human and then animal to get the source, especially water and feed. And then the 1 kg live weight of the animal can produce approximately 25 kg footprint carbon and 14.5% methane emission. So this is definitely impact to climate change in the world. On the other hand, the number of the vegan, vegetarians, and flexitarians has been gradually increased worldwide over the years, approximately 0.2% every year. Therefore, plant-based meat alternatives are increasingly important as consumers tend to reduce or avoid consuming animal products in their diets, and food substitutes for conventional meat are in demand. And textured vegetable protein on the plant-based meat hold promise as possible solution. This is I got the data from the Allied Market Research on 2020 that actually in the recent days a lot of the company or the manufacturer they produce or the sell that TVP product or plant-based product. We see that mostly they are in US and then Canada, Europe, China, and then maybe in Taiwan also. If we see this data, I didn't see a lot of the product TVP commercial in Africa and especially in Asia. This is the opportunity to us, for us to make the collaboration between researchers and then with company to push, encourage the commercial TVP or plant-based meat sell to the customer. And then this is a key factor influencing TVP production. For the producing the TVP, the two most important factor. First factor actually is the raw material or feed composition. It including type of the protein, like the soy protein, wheat protein, pea protein, and then protein content and quality. How much protein content in that material, and how good the quality of the protein, of course, and then moisture content, and then other additive. And then the second key factor influencing TVP production, there is processing condition.
Yeah. She was very nice. I didn't like the Indian guy, the other Turkish guy.
Okay. Can I continue my presentation?
Yes, please do.
Yes, please.
Thomas.
Okay.
Apologies for that.
Okay. For the second factor is processing condition, like extruded type, including single screw or twin screw, screw speed, and then temperature profile, feed moisture, die descent, and pressure. For the die descent, we have the different type of the die, right? That I showed before in the Professor Osvaldo presentation. He showed the the big extrusion with long cooling day. I don't know how long this cooling day and how affect the cooling day on the production TVP. Maybe is any study regarding that? I interest about that. Okay, for this research, it's meant to impact of feed composition. In this study, we use the deflated soy flour and extrusion parameter. We use different screw speed on the production of the high moisture TVP through the single screw and twin screw extrusion. Why we use the TSF on the production of the TVP? Because you know that TSF, it helps reduce raw material costs compared to using only more expensive ingredient like soy protein isolate or PPI or with protein. It will be cheaper. And then TSF typically contain around 20% native fiber, which contribute to product functionality and adds nutritional value. TSF is minimally processed and often labeled simply as soy flour, which align with consumer preference for clean labor or less processed ingredient. And then the last one, TSF retain a significant portion of the original isoflavone, because isoflavone are mostly found in cotyledon part of the soybean and not removed during the oil extraction. Okay, because we in this study we compared to with between the single screw and twin screw, we are using the single screw with, because this single screw has 3 different zone barrel heating. Yeah, barrel temperature we set for the first one is 50, and then the second barrel of 80, and then the last barrel is 130. And then for the twin screw, its extrusion has 8 zone barrel. We set up a start from the temperature. We set up from 0 to 130. Okay, this is the result on water absorption ratio and cooking loss. In both of the extrusion, twin extrusion or on the single screw, water absorption ratio increase with addition, increasing the TSF ratio, TSF content. Twin screw generally achieve higher water absorption ratio and lower cooking loss if compared to the single screw cooking extruder. And then single screw cooking extruder show more fluctuation with
Thomas, you have 5 minutes. Sorry.
Okay. With higher cooking loss value overall. Then increasing activated soy flour content improve water absorption in pot system. Okay, this is for the texture profile result that twin screw sample consistently show higher value for hardness, springiness, gumminess, and chewiness. The result highlight twin screw superior structuring ability suitable for achieving meat-like texture in plant-based product. For the color, the addition, I will show the figure. The addition of TSF, increase of the TSF effect on the color will be darker and reduce the light L value, because we know that TSF still contain the carbohydrate, so become the mild reaction. But if we compare twin screw to single screw, twin screw is a little bit lighter. This is isoflavone content on glycoside form. Definitely, if higher increase the TSF content, the value of the glycoside isoflavone content will be increased in both of the system, twin screw or the single screw. Also, it happened in glycons form. So, in the isoflavone content increase both in the twin screw and single screw. Okay, for the conclusion, twin screw outperformed single screw in producing high moisture TVP with better water retention, lower cooking loss, firmer texture, and more stable isoflavone profile, confirming its technology advantage in structured plant protein processing. And the result demonstrates that careful manipulation of the TSF ratio and extrusion screw speed enable tailored production of high moisture TVP with desired functional and nutritional attributes, supporting the development of optimized plant-based meat alternative. This is also the previous work, our published paper. We try to produce the TVP made from the tempeh flowers. You know that tempeh actually the fermented soy. Why we need to ferment it? Because during fermentation, the protein content will be increased and changed on the amino acid. Yeah, tempeh actually is a traditional food from Indonesia, and we try to grind, become the flour, and then incorporate to TVP.
Thomas, you have 2 minutes.
Okay, this is the last one. Okay, this is the last but not least. I warmly to invite you all to attend IFOS 2026 World Congress Food Science and Technology. Will be held in Kaohsiung, Taiwan on October 25th to 29th. Let's connect, learn, and innovate together in field of food science and technology. I look forward to seeing you on next week. Thank you so much.
We've got time for one question. Was there anything on the chat? No. Is there anyone in the forum who would like to ask a question to Thomas? I think everything was really clear and okay. So with because we're running a little bit out of time, I thought, well, we'll go to the next speaker. But thank you very much, Thomas, for your presentation.
Okay, thank you so much. Thank you so much. Bye-bye.
I'd like to introduce our next speaker. It's Dr. Eva Maria Schmidt. She's from the University of Adelaide. Oh, I like the sparkle. I'm not the only one all colourful today. And she's going to talk about testing high moisture extrusion. I have to try and remember what HME stood for then. Performance and commercial soy isolates. Thank you.
Thank you. And I hope everyone is still fit for the next 2 sessions, and then we have our afternoon break. So to start off, I want everyone to lift their hands. Yeah, everyone stretch your hand. And only drop your hand if you never ever tried fake meat or meat analogs before. If you have never tried it before, then drop it. Otherwise, keep. Okay, that's many people. Keep your hands up if you actually finished the product. Yeah, okay. And last question, keep your hand up if you would confidently replace your mom's Christmas roast with it. Okay, probably not. Good. So there are some flaws, but I see every one of you basically has been exposed to meat analogs. However, there are some improvements which can be made. And since, you all know the product, so you're the perfect participants for my small game. Who wants to be a fake meat connoisseur? So the question here is, what needs to improve so that you not just want a meat analog, but you crave it at midnight or after, of course in a sour condition. So there are a few answers for you. Is it texture? Is it the sensory profile? Is it juiciness, which you think it is lacking in? Or does the color just not appeal to you? So that's a question. And since we are all together, the answer is that all of the above, of course. And there are many more reasons which I didn't even put up here. But if we really just looked and decided between the four, it would be, and that's what literature is also suggesting, texture. Texture you shouldn't underestimate. We were talking about trying to make food basically edible for poor countries, but we are here in a developed environment. And if people don't like the product, they wouldn't buy it. And texture has a major impact on this. So for my PhD, I was trying to imitate is maybe a big word, but I was trying to get as close as possible, particularly to this chicken fibers. And the idea is, so that's made by nature, and I wanted to engineer it basically, put it through the extruder, and realistically it looks like this. For me, the question was, is it really shear force, or is it not a bit of luck as well? Because I struggled. And going forward, it can end up both ways. So this one here, broken, there's a small video. You see, it's a consistent product, definitely a network there. However, it breaks apart and there's no real fibers. On the other side, you can get a far away regardless of which extruder you use. Here you see, no, you don't. Sorry. The video playing anyways. So it looks very unimpressive just by looking at it, but once you tear it apart or break it, bend it, there's actually the inside, you see fibers developing. Okay, and what was the difference between the two of those samples? I used the same ingredients, I used the same conditions, but with the ingredients, I had different soy protein isolates. So even the soy protein isolate itself, same botanical origin, but from different manufacturers from different countries. And this made a huge difference. So for my formulation, I used, as I said, different SPIs. Manufacturer is not disclosed here, so we just say A, B, C, D, E, and one and the same SPC. And just for you to see, if I didn't use the SPC, the soy protein concentrate, what you get is a very elastic string. You would always need some fibers, some polysaccharides to basically create fibers and not end up getting a pretty elastic belt-like string. So that's why I put SPC in the formulation. And as you see here, I try to show you with the soybeans here, even though from the same botanical origin, same family basically, everyone has their own character, everyone behaves differently, and some don't behave at all, I would say. I also added pea fiber, a bit of salt, sodium bicarb to slightly increase the pH as well. And what I did was looking at the physiochemical properties, first of all, just of those SPIs. And this brings me just for the agenda. We will look into the extrusion process. Importantly, the material characterization. As I said, I only had SPIs. And then the performance, what worked and what didn't work. And we try to connect the dots. So I'm just skipping this actually. We have heard about this before. Of course, the extruder has different phases and there's different things going on. Importantly to point out at the beginning, native state, so your material is denatured already basically. And the shear in the extruder and then the heat leads to unfolding. That's what we want to achieve. And then in the melting phase or zone, there's happening at the same time. We have an unfolding, new bonds form, they will be broken again and continues. And just in the cooling, we actually start seeing polymerization and then a laminar orientation, ideally with fibers. And again, I acknowledge Asad for having talked you through this perfectly fine. So we have the process for parameters, and on the other hand, we have the final product. And the simplest thing is to see the product and change maybe your process parameters and see what happens. That's a very empirical approach, works, but is maybe not enough. We need to look into the process itself with its system parameters and physical characteristics, which are dependent from each other. And then we can always go back to our process parameters and go forward to the actual structure. Good. So what I did was basically looking at the ingredients, at my soy protein isolates, and then also into viscosity and solubility, and lastly into specifically the texture. I did some other parameters as well, which I won't show. So what's happening? This is basically my extrusion formulation. I will reel it to you. Mostly SPIs, but obviously mixed with some other ingredients, and I end up getting 5 extrusion mixtures. The only difference being the SPIs. Everything else is always added and is always the same. We put it through our extruder at RMIT, I have to say. And then we get extrudats. We visually examine them, and we also look at the texture profile. Degree of texturization is a good one to have actual data. So it's basically the ratio between cutting, for the forces of cutting the extrudat across the along the extrusion flow direction and across. Okay, to the material characterization, just in brief, I analyzed it. There's no big difference. We should ideally get 90% for SPIs, but there was a bit of maybe contamination. Water was taken into account already. SPC, obviously, with 72% lower, but that's expected. And the P fiber I also listed. So nothing super different here. Even the fat content in this low amount, maybe it acts as a lubricant, but it's not significantly impacting our extrusion. So first of all, the basic analysis is always protein solubility and maybe PDI as well. There's a small difference. Solubility, obviously, how much protein is soluble when you put it or disperse it. And protein dispersibility is just a bit of a harsher treatment if you want. So you would put I used an ultra-tarax to disperse your proteins and not just put it into a beaker and mix it through and wait for an hour. But you see it's clearly the same trend. And here you see as well that the proteins, all soy proteins, but they differ quite significantly. We didn't have access to the manufacturing process. Obviously, the companies wouldn't tell us, but you can guess when something is more soluble, then obviously the process must have been much more gentle. I also looked into, just briefly, the particle size distribution. What I did is, DL stands for liquid, so I looked into the solid powder and into the liquid once I solubilized it, and I called it swelling. It's maybe not an official name. How much water is basically taken up by this, and it correlates pretty well to the measured water holding capacity. Connecting the dots. So obviously there's always an interrelation between all those factors, which I haven't shown you all. Important is protein solubility. Particle size gives you, or distribution gives you a good insight, as well as water holding capacity. And this table here should come as no surprise. If water holding capacity, for example, is high, then obviously you would expect a juicier product. Okay, and now to another measurement to look a bit, I wouldn't say into the extruder, but to see how proteins hydrate and whether they can retain or not retain their viscosity. And I'm emphasizing we are not successfully imitating the conditions of an extruder. But with the AFEA, as you can see here, it's a small paddle. You put your protein solution into it, and it would measure viscosity, a viscosity trend. Yeah, we don't have to go through this procedure, but it takes 20 minutes, so much longer than half a minute of extrusion residence time. We also have a very gentle shear, not comparable with those twin screws. Maximum temperature for me was 95, which would induce denaturation, but obviously is not high enough to compare with the extruder. And the particles are, I would say, fully hydrated. At least the solids concentration is almost half of what we have in an extruder. And that's now the profile. It looks like raw data, but you can actually get a lot out of it. If we don't have to go through all, it's maybe easier to compare it. So that's our 5 SPIs. And what we can see, they all show the same trend, however, a different extent or height. And as I showed you before, the swelling, for example, it's the same trend as you see at the first holding phase. So we see how proteins interact with water. The same with solubility at the end. Is the viscosity retained? Or we have, for example, here SPID does not really show any viscosity increase. And that's also related to solubility. If something is not soluble, it would form aggregates, and there's no chance of getting it into a network, which would cause resistance. And lastly, how did our SPIs perform? So we put them through the extruder, the mixers actually, and we look into what we get out of it. This here's the degree of texturization. It's maybe a bit small. You can see if it was 1 means the forces, regardless of across or along the extrusion direction, would be the same. They equal each other, and there's no fibers. There's basically, it's a gel. And the higher you get, the more fibers you would become. So SPI A and B showed fibers, not perfect. We are not perfectionists, maybe, but at least you could get something out of it. In the middle-ranging extruded E had a really high water-holding capacity, and it shelled really strongly. You see it here. So I would say it ranged in the middle, but it got really hard. What did not perform well was the other two extrudeds. They both showed low solubility, low water-holding capacity, which matches pretty well with this. And lastly, so we see soybean protein is not soybean protein. There's a huge diversity. HME performance can be predicted pretty well with protein solubility. That's maybe the first one we would go for, but it's of course not enough. You need water holding capacity as well. And particle size distribution. RBA is 20 minutes. It's much quicker than rheology, but it doesn't mimic the extrusion process. And lastly, outlook. Obviously, that's what we heard. Some have already done it. Closed cavity rheometry definitely helps to understand the process better. Then the question is, would I rather pay more for high quality protein isolate, or would I still go with my cheaper one but add things or process it differently to make up for the functionality? And the allergen reduction, that's something else we are talking about. high moisture extrusion, so the treatment is not as intense as it would be for low moisture extrusion. So the question is, can we at least get a little bit of those allergens reduced? I don't know. Lastly, acknowledgement, especially to RMIT, even though I'm now at Adelaide University, all my research happened back at RMIT. And yeah, thank you if you have any questions.
Thank you very much. Maybe we can reserve questions, please, to Eva Maria at the break, because we're running a bit short of time. It's my fault, of course, but I'd like to introduce, thank you. I'd like to introduce our last speaker of this session, Dr. Billy Lowe. There he is. He's from RMIT University, so you probably are colleagues, and he's going to talk about high moisture extrusion of lupin protein isolate. Thank you.
Hello, everyone. My name is Billy. I'm from RMIT. So thank you to Eva for starting off the presentation, because we were lab partners during our PhD, and we worked on high moisture extrusion. So she worked on soy, I worked on lupin. So I'll briefly go about the background. So basically, I think this is all covered in a lot of the talks. We're trying to find alternative ingredients to feed the world. So one of the suggested trends that's happening right now is looking at plant proteins to replace the meat diets that we have. So as mentioned, social media was a major source to encourage this trend. So the food industry has to adapt to this trend, and we need to look for ways to include plant ingredients into food products. So just a bit of background. So we're talking about lupin here. So lupin can be used as an ingredient in food products. Australia is one of the big growers for lupin. We produce about 1.6 million tonnes, and we produce about 80% of the world productions for the lupin market. Lupin is actually cheap to grow, and it's also much cheaper than soy. So if you have a look here, we've got on the top there, that's lupin albus, and also on the bottom, that's narrow leaf. So they are the two most common lupin varieties that we have out in the market, and also what we grow in Australia. So depending on the variety, of course, and also where it's grown, the composition may vary, but the protein content and the fiber content are relatively high, so that we can actually use this as a possible functional ingredient. But there are some limitations to everything. There's always got to be a limitation to something. So even though that lupin protein has a high protein content, it does have poor functional properties compared to other ingredients such as soy protein. So if we have a look at some of the markets in terms of meat analog products that are out in the market, majority of the ingredients that are used out there are either soy protein concentrates or isolates, as highlighted by Eva. Pea protein is another one that can be used to make these plant-based meats. So there's actually a gap here. So basically we can actually try to actually use lupin protein to actually make these meat analogues. So if we have a look at the research that I did, we're actually trying to determine whether lupin protein can be used as a functional ingredient in high moisture extrusion. And also the other most important question is, can we actually substitute it with soy and completely take it over and use lupin protein instead? So there were the two main questions here to see whether it can be done. So this is our twin screw extruder from RMIT in the pilot plant. We've actually been talking about the process of it. We have the heating zones, and also at the end here, we have the cooling die. Not much of that has been spoken today, but that cooling die actually helps to set the protein and to get that texture for the meat analog. So this is our extrusion conditions. Basically, we have 6 heating zones, and also we're using different temperatures inside the heating zones. And also we have a cooling die, which we set to at a much lower temperature, at about 50 degrees. We put our powder through at a feed rate, at a consistent feed rate with a screw speed of 150 RPM. And we're actually injecting water into the system at a consistent flow rate as well. So, okay, so this is our product formulation. So what we did here is we actually got some lupin protein isolate from Germany, which is much more expensive than gold at the time when I was doing my PhD. Really, I think gold is more cheaper than my lupin. And then we also got some commercial soy isolates and also concentrates in Australia. And we also have some other fibers, some salt sodium bicarbonate, and also silicon dioxide, which is an anti-caking agent because the lupin protein isolate's quite poor in functionalities. One of the functionalities that's really poor in is interacting with water. So we do need an anti-caking agent in there. So if we look at the analysis, the very first thing we need to look at is actually looking at the powders before going into the extruder to see what does it interact with water? Does it give us any gelling properties? Does it, give any good solubility when it's interacting with water? Once after that, when we've got the extrudates, we then look at the texture, the color, and also we look at some microscopy on the surface morphology of the plant-based meat. So this is the pasting property before the extrusion that was done. We actually looked at the individual ingredients and also the formulation. If you take a look here, soy protein isolate and the soy protein concentrates does create some sort of a gel when it's heated from 25 to 95 degrees using the RVA. So we can actually see that from heating to 25 to 95 degrees and then cooling it back down, we do get some sort of a gelling network. With lupin, we got nothing. Lupin did not give us any gel at all. It was just, it was almost like water. So you can actually see that from the individual ingredients. But if you start increasing the soy and the lupin ratio by decreasing the soy and increase the lupin ratio, you can actually see that the viscosity or the pasting properties is actually decreasing. So by increasing the lupin protein isolate in the system, we are losing our gelling network in the system. So once knowing that, we know that we might have this issue along the way. We're hopefully that with the using high moisture extrusion, we are able to use the texturization to hopefully improve that. So this is some of the videos that I took about the product that was coming out of the extruder from the cooling die. So on the right here, on the left here is the control. Basically, I have no lupin in there. And on the right, I have added some lupin in there with a ratio of 25 to 75 for the lupin to soy. And you can actually see that from the right here, I'm getting a product that's coming out of the from the cooling die, and you can actually see some texture of the product. But immediately when I'm adding in the lupin in there, you can start to see that the product is slowly breaking. It's actually not really cohesive because now this is reflecting back to the RVA where it's actually reducing the viscosity. It's not creating any gelling, it's not improving the integrity of the product. Then we went further. So we looked at 50-50 and also 25 to 75 between soy isolate and lupin isolate. From here onwards, you can actually see that the texture for the surface of the product is slowly decreasing, and we actually don't see those cracks on there anymore. With the 50-50, I actually tried to take it out and show you the texture inside. You can actually see that it's becoming, it's still a gel, but we're losing the integrity of the product. For plant-based meats, when you pull the product apart, you should see the fibrous structures in the product. But by increasing it with the lupin, we don't see that anymore. So lupin does have a play in the product, but it's on a negative impact because we are losing the structure for the product. So we also looked at the texture of the product after when we've extruded put the powder through for extrusion. We noticed that by increasing the lupin protein, we can see that the hardness of the product is decreasing, which is expected coming back to the AFEA graph where the gelling properties of the lupin is actually impacting on the product, therefore the texture is decreasing. We also looked at the SEM, so on the surface morphology of the product. If you have a look at the control, at the top there, you can actually see a lot of fibrous structure, which is what we're expecting to see. And that's why in the market, majority of the ingredients that we use to make plant-based meats is soy, because the fibrous structure is there. But as you increase the lupin ratio, you can actually see that that fibrous structure is no longer present. So, which lupin does have that adverse effect on making the meat analogues. So in conclusion, so this study investigated the lupin protein in high moisture extrusion. Lupin protein does have poor pasting properties and hydrating properties in water. So I only tested this in water. Increasing the lupin protein isolate in the formulation decreased the pasting properties. And by increasing the lupin protein ratio, we now have a much softer product. So that does definitely has an impact on the overall quality of the product as well. This also impacted the fibrous structure of the extrudate, which actually can be seen visually as well as can be seen on the microscope. And also, this study shows that lupin protein isolate can't actually be substituted with soy protein isolate to make the product, or in general can't be used alone, standing alone ingredient to make meat protein, to make meat analogues. But it can be complemented because we still have those high protein and high fiber composition, but we just need to complement it with other ingredients, such as soy, or maybe we'll add some starches in there to help make the integrity of the product. And thank you for your attention.
Thank you. Thank you, Billy. You did an excellent job of getting that well on time. Is there room for one question? Is there anyone online? No. Okay. Sushil.
Good presentation. I have a few questions actually, but I'll start one or two questions.
Just ask one, Sushil, because there's another person.
Your lupin, was it Albus or Angustophilus?
Sorry, what was that? Sorry?
Your lupin, which variety was it? Albus or Angustophilus?
I don't know, because the company I bought from Germany was a biotech company, and they were quite new. They would not give me any details of how the protein was.
Yeah, because Albus and Angustophilus are east and west.
Yeah,
they are totally different, right?
Yes.
If you don't know the variety, then how can you say that lupin is not functional?
Well, because we actually.
Yeah.
Because
that lupin was not functional. I agree.
No. Yeah, I agree. That one's not. Yeah. But then we also did some tests on using lupin. Before we went onto lupin protein, buying lupin protein, I extracted lupin protein myself with flour, and we tried it with extrusion as well.
Okay.
And that didn't work as well.
Yeah, we have done a lot of work with the lupin protein. They behave far more better than the soy protein.
Okay. They're not the ones that I've got.
Yeah, on the right condition. Yeah,
on the right conditions, yes, yes.
Thank you.
We do have a question online, and I've been asked to give that a bit of priority. So it's Keith. I see your hand up. Do you want to ask your question, please? You need to come on mute, off mute. We can't hear you, and you're frozen. Okay. Well, we might have to wait.
Thanks, Bill, for your present.
Go ahead.
Yeah. Transmission. Okay. Can you hear me?
Yes. Yeah. Yes, we can.
Okay. Thanks, Billy. I'm going to ask you a daft question. I might get a daft answer. When I talk about lupin protein here in the UK, they sort of laugh at me and say, is this a Monty Python sketch from the famous John Cleese one of Lupin's All Your Life? Because we hear about lupin protein, but we only grow about 17 tons in the UK, and farmers will only grow them as a nitrogen fixer for recycling of crops. So is lupin protein is going to be a source of product that we would, you know, the POMs over here would probably import it from Australia as a substitute? Yes. Or do you see lupin production growing in the Northern Hemisphere as well? Would you know?
Okay, so I'll talk about Australia first. So when I was starting my PhD, I've spoken to a few farmers that are actually trying to get their lupin into more of a functional ingredient. Yes, you're right. Lupin is used as animal feed, but we can get more value out of that. I know one, don't quote me on this, I know that one company or one farm in Western Australia was trying to get their lupin into lupin isolate. I don't know how far they got with that, but yes, I'm not sure about in UK, but in Australia, we are trying to get the lupin market up and running into more of a viable ingredient. So we are working a lot of that in Australia because we are one of the biggest growers, and we need to use that more, utilize that more.
Yeah, okay. The bodybuilders up here use lupin protein, but they buy it in a small pouch, which costs a fortune via Amazon and eBay. But
yeah,
so thank you for that. Thank you for your answer.
Yep, no problem.
Thank you. It's good. Thank you.
Okay, thank you very much.
No
I better. Could you please thank all of my lovely speakers for this session? Lovely speakers, if you could come up to me because I've got a little Prezi bag for you as a thank you. And also someone must be forgetting their scarf for you. Perfect. Thank you very much. I think you have a 15-minute.
Before we have the break, let's take a group photo. It's likely there is no rain outside. Just outside the reception, that area, let's be quick. Oh, here. Okay, so let's be quicker. We'll have a photo here, and before we go for the afternoon tea. Good afternoon. Let's get started because we are already back. So next, it's my pleasure to introduce Karsten Schellhas, and is a technology consultant with over 30 years experience in meat processing and over 5 years in alternative protein development across Canada, the US, and Europe. As founder of Schellhas Food Technology Consultants, he helps meat companies create innovative products, adopt new processing technologies, and grow their brands. His talk is important parameters for producing hybrid products. Let's welcome. Up to you.
Hello. Can everybody hear me? Does it work? Yeah? Okay, good, perfect. Thank you very much. Thank you, Jordan and his team, for inviting me. It's a great day. I learned already a lot. And we started this morning learning about the history. We talked about flow. We talked about shear, different extruders, soy protein isolates. But now I think it's time we talk about how to make certain products. And that is something what I specialize in very quickly because I'm an outlier in the industry. I went through a traditional German apprenticeship as a butcher, did my master degree as a butcher, worked in small companies up to the largest meat companies in the world. I did lots of fermentation products, salamis. I'm familiar with downstream extrusion. And then 8 years ago now, I worked together with a company, Riser, in the US. And at that time, I suddenly ended up in alternative protein when Beyond and Impossible came to us. They came from their KitchenAid machines and suddenly scaled up. And all hell broke loose, as we learned today. And yes, that was the truth. All hell broke loose because different shears and different mixing times had a big impact on those products. So we fixed that, we moved on. Lots of other companies came. So I think I've been in over 30 or 40 plant-based companies. I also then did hybrid products first at Upside Foods, where I mixed cultivated meat with plant proteins. That's another story. Then I was with a mycelium company in New York, where we fermented using solid-state fermentation mycelium and made mycelium bacon from it. Then I was approached by a company to look more into hybrid processing. And today we are talking about hybrid processing. So I'm using protein isolates or TVP or HME, and I mix it with meat. And here we see what is the rise of hybrid meats. What are they? Meats are innovative food products that blend traditional animal-based meat with plant-based ingredients like protein, vegetables, and fibers. The goal, target audience is more the flexitarians. We all know that. And I want to concentrate on that because hybrid product is nothing new. That has been done 40, 50 years ago, but it was under the goal to produce something less expensive, especially in the meat industry. Then you had soy flour, you had breadcrumb starches, phosphates, you had low-tech mixing and forming. It was about economical sausages. In England, they do that for almost 100 years, where they add breadcrumbs and everything to their sausages. So that is quite not new. However, now everything has changed, new generation, a new focus on sustainability is there, and suddenly sustainability, health, and innovation is important. We suddenly have pea proteins in there. We're talking about high-tech extrusion, and one of the major differences is also a clean label approach, where in the beginning, 40, 50 years ago, it was more about making cheap and don't tell the customers. Now we want to tell the customers and tell about the advantages of all those products. Here are some industry examples. We have, for example, Purdue, a large US company, that's a $10 billion company. They have their Chicken Plus since 2019, I believe. They mix it with cauliflower, chickpeas, and plant protein. What is interesting, they claim they have 1/4 of a cup of vegetables in there. So that's why, that is one reason why that product is actually very popular with families. They give it to their children. The Better Meat Company, in Sacramento, they have a fermented microprotein made in bioreactors, and they just signed major deals with meat companies, letter of understanding that they will supply a lot of tons to meat companies. Applegate Farm, they are around since the 2019 with their great organic blend burger, 50% organic beef, 50% mushroom. They are also successful with their product in the United States, also belong to a very large meat company. And then we come to Albert Heijn in Netherlands. They are it's an old supermarket chain in the Netherlands, and they have now the goal to replace their meat offering by almost 50% in the next 10 years and offer hybrid products. I was there a couple of weeks ago in the Netherlands, and that is their product. They're using MAP packaging, very advanced. They have a very nice extrusion. They have good color, everything. We talk about MAP packaging later. The color here in that product is made with tomato paste and then also tomato powder. We need to understand when we talk about hybrids, proteins are different. We have on one side, we have the meat protein, which is myofibrillar protein, actin myosin. And then on the other hand, we suddenly have the plant proteins, which are albumin and globulin. They don't like each other. Also, there's different pH values, there's different temperatures, there's different fat content and things like that, and that has a big impact on further processing. What is one big mistake here by Albert Heijn is, this is a regular and this is a hybrid. Only a green arrow here shows that it is hybrid. I was at 3 stores. 2 delisted the product because customer complained they thought this one was a regular meat product. So this is $1 billion company, and to make a mistake like that, I don't understand why they do that. They wanted to maybe save money. They have the perfect technology on processing. You see the nice grinding, fiber alignment, everything wonderful, great color. But then they make a marketing mistakes which will cost them a lot of money. Also here, the disadvantage is when you bring those 2 different proteins together. Here they have buffered vinegar in there. This is an acid regulator to preservative, but also bring the pH together. And they have 1, 2 other regulators in there. So this is to show you, yes, there is a market for it, but you would clearly need to differentiate your product from your own product so they see it's a hybrid. So now here we come first to meat selection parameters, and then we come to plant protein selection parameters. Meat choice. If you have the chance, always get fresh meat for that. That's the most important. If you get frozen meat, then you save a lot of money on one side, but then you have to thaw it. When you thaw meat, depending on how you thaw it, you will lose between 0.5 to 5% of your weight. Not only that, you will also lose nutrients. In the old days, they just threw meat in the water, then you lose 5%. Then they had vacuum packaged meat, which they throw in water, and that has a disadvantage. It grows bacteria in the package. And now they actually have professional thawing rooms like that here. You put 20,000 kilo of meat in there. You have air, you have probes in the frozen meat, and then it's automatically the airflow adjusted to temperature, and then you can bring down the thawing loss down to 0.5%. But of course, that's a big investment. Fat content, 20 to 30% is important for the flavor, for the juiciness, overall juiciness. Grind size, this is critical. lots of people thinking over mixing or under mixing creates challenge. Yes, it does, but the size of the grind is important for the structure, bite, and texture of the meat, of the final product. Do you go 3 millimeter? Do you go 5 millimeter? Do you go 8 millimeter? All this is important. Sharp knives is important. What kind of grinding system do you have? Do you have enterprise system? Do you have Anchor system? I don't want to go too much into that. Then grinder. I've been to companies that do hybrid products. They throw everything together in one grinder and stick it in there, and then you're breaking the fiber structures of the plant proteins and some meat, and you're losing bite and texture and everything. So what you need is an angle grinder. I'll show you a picture later. Okay, plant proteins. So here we come to one challenge, and that is in the meat industry, you learn from day one, you have to check incoming meat materials. Is it old? Is it fresh? What is the pH, AW, blah, blah, blah. In the alternative protein industry, that needs to be done better. Where is the protein coming from? How has it been extruded? Is it dry extrusion? How's that called? Dry fractionation, or is it wet fractionation? It all has a big impact on the functionality. The protein types are important. Clean label goals, balanced protein isolates with whole food ingredients. TVP size is also critical for the final bind. If you have a 3 millimeter ground meat and you have a 5 millimeter TVP, different grind sizes create lots of problems. You have two-tone effects and other problems with that. Finding the right balance is also important. Burger example, they do 70-30, 70% meat, 30% plant proteins. Sausage can be 60-40, nuggets could be 50-50. That all needs to be tested to get the real mouthfeel and balance. It is also said that a hybrid product should have at least 70% meat, because then you have enough iron in there which can actually absorb by the body. That was a USDA said that. USDA is American meat, so who knows who paid for the study? I don't know, but there might be some truth to it. So functional ingredients, big problem in the plant-based industry. Here we have methylcellulose from cotton or chemically. Methylcellulose, I don't know why they ever used methylcellulose from the beginning, because it has actually disadvantages. When you make a hot dog or a burger, it has a really great bite when it's hot, but as soon as it's cold, then yes, it's bad. It's you have a sausage and you want to package it, you cannot because it's falling apart or things like that. Then they tried citrus fibers, they tried psyllium and other things. They added kappa carrageenan to have a better bite in the cold stage. Doesn't help. It does not help. There's only one thing which helps, and that is another controversial thing, and that is transglutaminase. So that is also very controversial, because they tried it 40 years ago in the meat industry, and they massively failed, because there were some really smart people and said, oh, we can use some old meat pieces and we put it together with transglutaminase and create a steak. But then that wasn't cooked very right, and then they had some food safety issues, and all hell broke loose. So they forgot about it. Now suddenly I'm sitting in in London at the Plant-Based Expo, a very large company has a presentation and they say, we have the perfect solution. And they were talking and talking. And at the end I said, oh, that's transglutaminase. And the lady looked at me, how do you know that? Because we used it in the meat industry. The advantage with transglutaminase is it really works cold or hot, but it also depends which plant proteins it has, because transglutaminase works with glutaminase and lysine. So you need to have plant proteins which are rich in glutaminase and lysine. So soy works, pea works, things like that. But emulsifier, soy lecithin, different starches. We learned a lot about starches today, very important. Here, starches, you have to be careful. As we learned, they give away water. So if you package a product and your sausage and you have lots of starches in there and you overdo it, then you suddenly have water in the package, especially with hybrid products, because the meat absorbs the starches like crazy, binds it, but then it releases it again. What is that called? Syneresis? Syneresis, yes. Flavor, umami-rich seasonings like yeast and extract and mushroom powders are used. Mushroom is great. On a production flow, that's not so. So hybrid burger processing steps. So this is very rudimentary, but I just wanted to show you a simple one. Hydrating fava bean and protein. Hydrating depends on the size of the TVP. The bigger, the longer it takes. But what we learned is you can fasten that project if you put the TVP into a mixer with vacuum function. Then the vacuum sucks the water into the TVP and you use it much faster. This is important when you go in big factories and they don't want to wait so long. Cook and finally chop mushroom. You do that in a bowl cutter. I show that later and then combine everything. Then you form the patties and then you chill. Forming the patties, it doesn't matter meat, plant proteins or hybrids. You should have a temperature of about 4C to 6C, maybe even colder, to get the right forming temperature to form the burger. I will show you a picture later. Hybrid bratwurst sausage, meat preparation, it's a little bit different. Pre-grind pork shoulder, 5 millimeter, hydrate pre-protein, combine the ground meat, chill, and then if you sell it raw, then you stop sear, you package it, or you cook it. This is the temperature needs to be higher, especially when we have plant protein, because they have plant meat protein coagulates at around 55, but plant protein much higher, over 80. So you have to think about that. So this is an angle grinder. An angle grinder is you have a screw which goes down here and transports the meat into the actually grinder. That helps. It goes very gently into the grinder and you don't push it down there very, very hard. Gentle processing is important, especially for hybrid products. Mixing, process efficiency, and that is all important. Here, grinding size can be 3 millimeter, 5 millimeter, 8 millimeter. And what is also important, you have different speeds for the grinding itself here. So you can a little bit slower or you can go faster. Seidelmann is a company who builds equipment for 180 years. So they know what they're doing, but you also pay the price for it. Then those are the mixers. I was talking about the mixer, uniform blending. This is with vacuum function. This is all pro touch screen. It can be connected to your phone. You can control everything You can also have nitrogen or CO2 injection in there if you want it cold for forming later. This is mostly used for plant protein hot dogs. That is a bowl cutter. Speeds go up to 6,000 RPM. You can have 3 or 6 on knives in there, depending what you want. You can mix in there, you can cook in there, you can have nitrogen injection. This machine does everything. From meat, about plant protein, chocolate, everything. And now we coming to the extrusion. So this is a VMAX stuffer. And they, in the meat industry, we call that extrusion because in that VMAX machine is a double screw. And the meat goes in there, positive placement, it falls into here, and then there is a double screw, goes like that, and very gently transports the hybrid product out here. Now, you remember the picture from Albert Heijn. They had very clean fiber alignment and looked great because they have an inline grinder here. That means you go here through an inline grinder, and then it forms, then when you have ground meat, it comes out very clear and long fiber strength, and it looks great. And when you have a burger, it gets automatically formed and then cut 113 gram. But here temperature is important. So below 4 Celsius is great for the product. And then you can do, they do up to what, 120 burgers a minute, for example. So now we come to another challenge, is packaging. Best would be for a hybrid product, and you've seen that from the Albert Heijn picture, MAP packaging. That is modified atmosphere packaging, and it has different purposes. It's a shelf life extender, color, and moisture. And it works with 3 different parameters, with oxygen, with CO2, and with nitrogen. And what is important is, for example, if you have a chicken-based product and plant proteins, you don't need color. So you don't need to add oxygen to it. You only have CO2 and nitrogen for preservation. If you have a beef-based product, then you have maybe 70 to 80% oxygen in there and 20 to 30% CO2. Now the challenge is, if you have oxygen in there, it's great for the color. It's great for the methyoglobin to stay bright and red. The disadvantage is the more oxygen you have, the more the shelf life goes down. So you need to find a balance with your hybrid product when you produce that. That is the most, there's VarioPack, that is a really good company, it's very well used in plant protein companies. Key consideration for equipment selection is the protein type and moisture management. This is the same like an extruder. You don't have a perfect extruder. You have to understand what kind of products you want to make, and then you select the machines. Yes, the meat industry is a little bit more variable than an extruder. Yeah, it's a little bit, I wouldn't say easier, it's just different. Texture sensitivity, avoiding overshearing of the plant proteins, big problem. With grinding or mixing, you have to be careful. Biggest mistake is people not looking after the equipment. Knives are not sharp. That is one of the biggest challenges in that industry. Hygienic design and cleanability. There are 10 principles of hygienic design. When you buy a machine, they should cover this. Rounded edges, water needs to run out, and so on and so on. Production flexibility for different hybrid SKUs. So is it possible that on the same machine you can do a burger, shish kebab, and ground meat at the same day, at the same time? without cleaning. Yes, if you have the similar ingredients, same ingredients, it is possible. You just take attachments out, you put a burger attachment out, and you put a shish kebab attachment in the machine. And that is important production flexibility. And here is something that is, don't look at the prices, they're all out of date. This is something what I don't see too much in the plant-based industry. Calculation. Yeah, how much does it actually cost us? Yeah, to put in there. What are the raw costs? What are the cooked yields? That is something where there is should be more focus on, because at the end we need to make money. Yes, the young generations, they want to change the world. That's great. I support that. But at the end, you have to make money to pay your people. Hybrid burgers, here's the same, just some examples. For each product, you need to have something like that. That's critical. In the meat industry, we have seminars, weekend seminars, just for calculation. So here, texture, flavor optimization to avoid a two-tone effect. So two-tone effect by hybrid products is a challenge, because you have the red meat and the pale plant proteins. Then sometimes you have little piglets in the vacuum package that develop, and you need to prevent that. You can use tomato paste, you can use tomato powder, pre-emulsify the right grind side. That is all important. Flavor. That is a pet peeve from mine. When I came into the plant-based industry, everybody was working with Firmenich and Givaudan and all the big flavor houses. But they never used individual spices to give it some individuality. And we need to do that. So one company I know in Indonesia, Green Rebel, I don't know if you heard of them, they making a rendang. That is one of the first products I could actually eat. This is freaking good. Sorry. I mean, this is good. And but they're using 10, 15 different spices. They put some love in there. So, and in the meat industry, when I did my apprenticeship, the master butcher, every morning they went into the room, they closed the door, and then he scaled up his spices. Then 1 hour later, he came back, and then, but he never told us. So that is something where the plant-based industry maybe can learn a little bit. We need individual spices to give it a certain flavor and texture, and put some love into the product, you know. It's very important. Regularity and label consideration, I don't know too much about that here in Australia. Maybe later. That is something you are in a gray area. For example, in the US, USDA is looking after meat processing. The FDA is looking after plant proteins. So what is happening now? Who's coming? USDA, every day you have somebody in your plant. FDA comes maybe every couple of months, if you're lucky. So this is a really gray area. What is important here? Is it food safety? Food safety is very critical in the plant-based industry. They should test incoming raw materials for listeria, for example, the pea proteins and all that. That is something sooner or later that will come. The map packaging we have, additive strategically managing spoiling risk, all that is critical. So all over food safety. You need to have food safety departments, even in an alternative protein company. That is critical. How is the plant protein stored? Is it stored at 30 degrees Celsius? Or no, can you go down to below 10 at least? The processing room. Ideally, it should be at 4 degrees Celsius. This is freaking cold. If you work 8 hours in a 4 degrees, you better put some long underpants on. It's cold. But at least around that temperature, it is food safety for the plant protein companies. It is very critical. So conclusion and innovation opportunities. There is huge opportunities for that hybrid product, but you need to be aware of a couple of things. You need to be about food safety. What are the ingredients you have? What is the equipment you have? Then also, do you build your own facility or do you have a co-man? That is a seminar for a whole weekend. A co-man or building your own facility. I'm old-fashioned. I build my own facility and I want to own the property because then I have something in my accounting books, and I can go to the investors and say, here, I own that. I have the machines. Yeah, you have a lot of high upfront costs. Yeah, but then you own it and then you produce it and you control the whole process. That is imperative. Yes, you have NDAs. Doesn't matter. Your IP gets stolen. And it's not because of people are bad or something. It's just how it is. Yeah, you can protect yourself. Yes, it will work for a while, but at the end, things happen. One last thing, cultivated meat and plant proteins. I made products at Upside Foods. That is easier because for me it was emulsifying much easier than real meat and the plant proteins. I used 20% cultivated meat and 80% plant protein. The products came out great. The team loved it, but the owner had different ideas in which directions they want to go. I suggested we should sell it in a few supermarkets just to get some customer feedback, but also we need to show investors that we can make money, not only spend it. Upside Food got 500 million from Jeff Bezos, Bill Gates, Branson, and so on, but nothing to show for. So, there is a future for cultivated meat, but it will take some time. It will take decades. In my opinion, they should forget making steaks. We need to solve problems. The problem is the meat industry is running out of money, meat. So if we can say, okay, if you put 2 10,000-liter bioreactors in front of your factory and I produce, let's say, 500 kilo of meat every day, I pump it automatically into your factory, wouldn't that help your supply chain? And the owner would say yes. And that's where we need to go. Thank you very much.
Thank you very much, Karsten. It's very, very different from what we heard from the extrusion side. So it's a very good ideas. Any questions from floor? Osvaldo?
Thank you. Very good presentation. I have several questions, but I don't know which. I will ask one which is related to food safety.
Yeah.
You talk about listeria, and listeria is coming from the meat or from the plant?
Yeah, that is a very good question. It comes from both. It comes from the meat and it comes from plant protein, especially if there's a lot of red beet in there. Red beet's supposed to be loaded with listeria, I was told. I don't know if that is true, but it comes from both. Mostly from meat, you have to say, because contamination is great. And listeria is something. I was in a factory where we found listeria. We were looking and looking, and we couldn't find it. It was half a meter down the drain. That was sticking. And that's why it is important to have as much stainless steel in your factory, because listeria bacteria cannot stick to stainless steel. So that's important. Of course, what I'm saying, everything is very expensive, but I'm German, so.
But listeria is
once you cook, it's not a problem. I mean, it's ready to eat meat.
I'm not the listeria specialist. Even when you cook it, it can survive sometimes.
Okay.
Yeah.
Thank you.
Because, you have one more question? Okay.
Yeah, one more question, yeah. And if you have more questions, come later to me. I will try to answer it.
Thank you, Karsten. This
You're
is not a question, it's kind of a question. But so in Australia recently, there is a company who got the FDA approval for cultivated meat. They are VOW. Are you aware of that?
Yes.
Have you approached them? Yeah.
Yeah.
So yeah, there you can get some ingredients for your hybrid protein.
Yes. So WOW, great company. They, if I remember correctly, he also builds their own bioreactors. This is a different challenge. The bioreactors. Here's the same. They making a pate-like product, and I'm happy for them, and I wish them lots of luck. But it's not solving a problem. Yeah, we need to produce products which are solving problems we have in the world.
Yeah. Why? Like,
Good. Yeah. No. Good.
So why is it not solving the problem? Having that,
Liver pate. Liver pate. They're making liver pate, for example. Yeah. So that is not solving a product if you make liver pate. Not everybody eats liver pate, or goose liver or things like that. It is, when you're in France, of course, you need to eat it. Otherwise, they deport you. But that's, we need to find,
I think that we'll stop here. And if you have a further question, ask Karsten. Yes. Thank you.
Thank you very much. Thank you.
And I think we are behind the schedule, so we needed to move. Now go to the session 4. That's the innovation in extrusion equipment technology. And the first presenter speaker is from Cletchell Lewison. He's the Asian Pacific process engineer. His topic is breakthrough in plant-based protein extrusion.
Hi again. I hope you still have a little bit of energy for this one. So we were talking about snacks earlier. I will focus on the proteins now, and I will show you what are the latest innovation that we develop at Clixroll to be able to produce to match what our customers are expecting. So, we can see the map this time. So I don't know, I will not go through this, but so yeah, maybe I will just go back on our location if you're interested in. So our headquarters is in France. I don't know, for those of you who have already been to France, so it's really nearby Lyon. And so that's our headquarters. We also have a subsidiary in the US, in Florida, in Tampa. So that's our main location. In France and in Tampa, we have R&D centers, so our own pilot scale extruders. So feel free to contact us if you want to perform some trial. We have many different extruders you can try there. EV32 for R&D, we can also scale up. So, if we focus on Asia Pacific, so we have people. We are actually a small Clixroll here. So our main office is in Ho Chi Minh in Vietnam. I'm based in Singapore. We have Gaetan and Eric here in Melbourne. We also have a guy in India. So yeah, we are almost everywhere. So if you need to contact someone from Clixroll, feel free. I will go really quickly on the market and application. So now I will focus again on the human food, and we will focus on the first one, the plant-based protein. So I will go quickly on this one. This one is interesting as well. We try to give the opportunities to everyone to try our machine. That's why we are expanding our R&D network, meaning that with our partners, you can also try our machine. So I will just focus on the Asia Pacific one, maybe in Australia. So we are working with the University of Queensland. So they are there, the FABA team. We also work, of course, for ages with the CSIRO. So the aim is really for us to give the opportunity to people to see our technology. I can also come on site to support if you want to develop new recipes, just to see the machine running and so on. So we also have I would say our main platform in the region is in Singapore. So with Nurasa, maybe you heard about them already. So there it's an EV32. You can try like the proteins, it can be HME, TVP, snacks, and many different applications. Okay, so if we focus on the protein, so we have two ways of producing the protein through extrusion. So I'm sure you all know about that, but for some people who are maybe only on snack, I will just go quickly on this one. So we have the dry process and the wet process. So in the first step, I will focus on the dry one. So here you can see a layout of, so here you can see the extruder. Here, so it's really adhered. It's the really important part of the processing line. Then you have the dryer here. So here it's an EV dryer. So Gaëtan showed you this morning our two main dryers, the EV and the EV Plus. So on this one is the EV one. Usually, so it's kind of a large range, but we can go from the small machines. So EV32, for example, we can go to 100 kg per hour. And for industrial line, we sold some line, for 3 tons per hour. Okay, so it depends again on the type of raw material that you are using and what you are looking for as a final product. So if we focus on the raw materials, mainly I would say the TVP are made from soy. Usually it's deflated soy flour. It can also be soy concentrate, but for like, of course, the price, the cost of the raw materials, usually industrial use the deflated soy flour. And it's working well. So we heard a lot already about the proteins, what makes a good protein. So also for us, that's what we use when we try new raw materials. That's really important. So extrusion is not, okay, we can say it's a black box, but you cannot put whatever inside and then you will have like a wonderful product at the end. It's not working like that. That's why I'm here. I have my job. So we need to find the good parameters to match the raw materials you are using, the good thermical energy, the good mechanical energy to achieve what you want to achieve. More and more, we try to, like, people are less and less interested in soy, I would say. So pea is also a really good source of protein. It's working well for TVP. And we have wheat as well. And we have like new kind of proteins like emerging, and it's working for all over the world. Even in the US, we're working with those kind of proteins that we call the pulse proteins. So in this category, you can find the mung bean, the chickpea, the lentil, the fava bean, the lupin. So we have many different things, and also ingredients, so starch, flours. The aim is also to be able to match the target. Sometimes you cannot, depending on the functionality of your proteins, you cannot use 100% of those proteins. That's why you need to add sometimes other kind of proteins to add starch. So it really depends on what you want to achieve. So this is an example of what we tried at Clickstrol. So for the shapes, like you can do many different things, but you always have to think about what will be my final product, meaning what will be my post-processing, what do I want to do with my TVP. If I want to grind my TVP after extrusion, there is no meaning of making a really big TVP, which might be more complicated to produce. So you always have, if you want to make like a chicken patty, or if you want to make like chicken chunks or something like that, you have to think about what will be my next step, and not like focusing only on the extrusion. So if we go back to this slide, so we tried many things. So the regular one would be with the soy concentrates. So this one, the wheat gluten also is something that we know it works well. So it has been there for ages. But the new ones would be like for example, the sunflower concentrate, the lentil concentrate, the fava bean as well. So we can do many things, but sometimes we have to mix. For example, some proteins are not that functional, so we need to mix them with pea or with soy, because we know that pea and soy are really like working well through extrusion. And also, so that's the small things that I'm adding here. For TVP or for HME, if you use a soy concentrate, for example, from a supplier A and a soy concentrate for a supplier B, both are soy concentrate, but it will not react the same on the extruder. Even for the same supplier, if you change, like you don't understand what's happening, you call them, oh, it's a new batch, we changed the way that we extract the protein. So it's also really important. Even from the same supplier and the same reference, sometimes from one batch to another, you have to adjust your parameter. So this is just example of the post-processing. So with TVP, you can make like tuna tartare, sausages, burgers. You can make many things. You can mix the TVP also for pet food. It can be used to mix with fresh meat. So we can do many things. So that was for the dry process. Now we'll focus on the wet process, and that's where we put a lot of efforts on this one. So I will show you some latest innovation. So just to show you the regular process, so this is the layout. So you can see again, so you have the upstream, meaning like the hopper, the mixer, and so on. Then you have your extruder. You can see that the extruder here is longer than the one for TVP. So we need a longer machine to be able to have like a good mixing, a good shearing inside the extruder. And also you can see here, so that's the specificity of the process, the cooling die, which can be which is thermoregulated. So for this one, it's an industrial one. So you can see we have 5 different zones, meaning that you are able to really control your temperature and what's happening inside your cooling die. That's really important. When we have a look at this one, usually we are like the extruder can swallow the raw materials, but the limiting factor is the cooling die, because the proteins needs time to be able to recreate the bond between each other. So usually your extruder can have a really high throughput, but the die is like the limiting factor of your line. So if we have a look, I will go quickly on this one. So that's with the regular die. So usually we go to 8 millimeters and we work on a thicker product because some of our customers were asking for this to make like wall cut products. So we are now able to go up to 25 millimeter. If we focus on the recipe, so the basic as well are the soy and the pea. And we also try new raw materials. So the same with the pulse, same from TVP. So we tried those ones. And I did a trial a few months ago for a customer in Singapore with insect protein. So the aim was to see what was the maximum rate of insect that we are able to add into the process without like having a lot of disturbance in the process. It was, sorry? We went up to 30%, but organoleptic, I would say, profile of the product was not that good, but the process was fine. So this is example of the post-processing, but what I want to focus on is that I told you that the limiting factor was the cooling die. So we developed a new one. So you can see, so I will show you a video. So maybe you know this guy, because he's really famous at the CSIRO. He worked here for ages. He was working on the EPT. Now he's our like protein guru in France. So you can see we have 2 outlets of the extruder. That means by adding this cooling die after like industrial extruder allows to increase the throughput. So we can go up to a 1.2 ton per hour. So this colleague is going to the gym every day, and you can see that he's struggling to open the stripe. So that means you can have like something really hard. Of course, you can like work with the parameter, add some water, more water inside to get something softer. And to get something softer, we develop something else, another technology, which is to answer like another request from a customer. So the first one was to increase the throughput. This one is to work on the texture. So we developed what we call the Galaxy technology. So this one is, we can call that like a dynamic die, meaning that you have your extruder, then you have like a cylinder, and inside you have an inner cylinder, and then I think I have a video. It will be maybe easier for this one. I will go back after, so I will show you this one first, so you can see how it works. So the aim was to make the proteins rebonding like in another way, like under a dynamic atmosphere. And the result is that we get like a really different texture from what we observe with the static die. We can have something like more soft, like softer. And then also the way you will see when they will open the stripe, I think it's on the video, you can see that the way that the proteins are bonding to each other is different than the static die. So that's also a great opportunity for the industrial actors to be able to propose something new to their customers. So here you can see the machine running. So the outlet quite different, but it's really easy also to use. It's even more easy to use this one than the static one. So you can see here, it's really different. And this colleague is not going to the gym, so you can see it's really like, it's really soft. Okay, so I will go up. Sorry, I'm almost done. So if I go back to this one, so the texture is really unique. So this has been developed with a Swiss university, Sion, right? So we scale up for this one is like a EV53. So this like Galaxy is made for EV53. So dynamic system, you can adjust the rotation, like the rotation speed. And also what's really important is that it's in the same way that the static one, it's thermoregulated. So you can see the thermoregulators here. So you can really like select the zone. And also the inner cylinder is also thermoregulated. So you can really like have a really focused process. About like the throughput, so for this one, it's up to 400 kg per hour for the soy and 300 for the pea. Pea is like, for those who have tried, pea is more complicated to like have a good stripe at the end than soy. The product is 10 millimeter thick, and yeah, startup and shutdown, like it's way easier than the regular die. So in production mode, you can see the inner cylinder inside the outer cylinder, and then you can, like, you know, Clickstone machines are openable to be like fully cleaned. It's the same for the Galaxy. We can open it to clean everywhere, even when you go. So in France, I don't know here, but the soy is like allergic, like materials. So you need to really clean deeply your machine before going to another production, I would say. So that's why this one is really important. So okay for this one. So this is the last slide. I'm almost done. So we cannot tell like one technology is better to another because it's really different, and we cannot like compare them. It's just depending on what we want to achieve, what the industrial want to achieve, we're able to answer their request. Meaning, like if they want to really work on the texture, they should go with the Galaxy, like meaning something softer, even for fish analogs. And also, it depends also, of course, on the raw materials they want to use. So yeah, that's our main innovation. So if you just have to get some takeaway from this presentation, is just like we are trying to innovate for industrial, also at R&D scale. But for this one, is like we try to answer to requests from our customers. The first one was to increase the throughput with the high capacity die with the two outlets, and then also work on the texture, which is the Galaxy technology. Okay, I'm done. Thank you very much for your attention. So if you have any questions, I will be happy to answer them. Or we still have a booth at the very end of the room there, so feel free to drop by. Thank you.
Thank you very much. And we have one question online. Jason, you go first.
Thanks, Liz, and yeah, thanks for mentioning EQ. Our series going very well there. But I had a question with your rotating. It's really interesting to see your rotating device. So you're applying a Couette flow to that system, and do you see very different flow? Like the internal structure is very hard to see from here. The internal structural components and what led to different softness. And I'm assuming it's that balance between a Couette flow and a Brazil flow in that die. Is that the major difference in that system, or is there greater things around cooling and stuff that's there that I didn't appreciate?
Okay, so yeah, so I'm not sure I got everything because the Australian accent is a mess for me, but I'll try to answer. Sorry for that. Just let me know if it's not clear. So, oh, sorry. Can you just put the screen again? Thank you very much. I just want to show you this one. So here you can see you can see two pictures on the screen. So on the right hand, you have like the static one. So you can see like the fibers inside the stripe. You can see the way the proteins are bonding inside. And then if you compare to the other one on the left side, like you can see the arrangement of the proteins is quite different because they are not like bonding in the same environment, meaning that under like the dynamic, I would say, movement of the dye, you will create like different kind of bonding between the proteins. It's what will give you the like the different texture. And for the water amount, I can tell like the one I showed you on the video, the water amount was quite low because it was really hard. But usually we use almost the same. We just use a little bit more water in the Galaxy one because we need also to be careful with the pressure. So of course the material can handle, like the equipment can handle the pressure, but as it's dynamic, we have to be careful to like manage the pressure in a better way. And also as we are looking for this softer texture, we increase like by 5%, I would say, the moisture content. It also depends, of course, on the type of raw materials that you are using. But for same raw materials, we use like almost 5% more water in the Galaxy dye.
Thanks.
Did I answer everything, or?
I'll have to come back to it. I think it's just thinking about the flow. It's just trying to think about the flow patterns in the cooling dye, because your normal dyes are Purcell flow, and these dyes are Couette flow.
Yeah,
You've got a sliding surface.
Yeah. Okay, thank you,
It's hard to
Jason.
communicate
Anyone?
Yeah, feel free to reach me if you have any question about that. Will be easier, I think. Thank you.
Any questions on the floor?
Thanks for the presentations. Can you actually stop the rotations and make it work as a static one so you don't have to buy both?
No. No, it meant like you can reduce the rotation. So you can work with a really slow rotation, but the aim is really to have like something, because you can just go with the static one. If you want something not like rotating, you will get like a different one because it's not the same shape, like you will not get the same texture and so on. But the aim of this one, and also the like, it's important, the rotation is important to make sure like the product will go through also the dye. So that's why you can choose the speed, and with the speed you will have like different results. But this one needs to be like the inner cylinder needs to be rotating. Yeah.
Okay, any further questions? If not, let's, there is Karsten.
I'm just curious about the insect trial. Can you tell me a little bit more? Is it all NDA top secret? The insect trial.
Yeah, I can. What do you want to know?
Yes, yeah, so the percentage and what was it for, and how did it work through?
Okay, so basically the aim, so the company was extracting oil from the insects, and they were having like byproducts, and it was like high in protein, so they wanted to know how they can use it. So we tried through extrusion. So the aim was more about valorization of the byproduct. The result where you can go up. So again, it's for these raw materials we're using with soy. So if you use like another soy supplier, if you use another insect supplier, it will be completely different. What we observe is that up to 20%, it was like the process was stable. The taste was okay. It was really umami, like the taste of the insects. And then when we tried to go a little bit up, like when you open the stripe, you can see like you see less and less bonding, like less and less fibers, but the texture was more like plastic. Plastic. And also, if I remember correctly, the pressure dropped a lot when we increased in the extruder. So yeah, I think it's interesting because maybe that's the future of food as well. Like we talk a lot about plant-based, but also insect is an option. So for now, and with these raw materials, for sure, we can do like a HME with 100% of insects. But maybe one day, we never know, we'll have like the good raw materials made from insect, and we'll be able to create like a 100% insect.
Thank you.
Yeah.
Can I follow up the question? You know, the insect protein that they are using the most is cricket.
Yeah.
But you know, they could be an allergenic problem because you know, and this is the concern that I have with the security. You know, I mean, we are trying to do too, but you know, it's a concern that you know is bothering me a little bit. I would like to listen your comment.
Yeah, about like the stuff that crickets can be allergic materials.
Yeah.
So yeah, it's also the case for soy, for example. So that's why you need to first I would say like clean the machine, of course, all the time. Like when you want to go for something else, I'm not really sure where we stand with the like introducing with the FDA and so on. Where we stand with the cricket, if it's like I don't get the English word now, but if it's recognized as like an ingredient that we can use in the industry right now, I think we are on our way to. I don't know if that's the case now. Yeah. So that's why we can see that people are asking more and more to perform some trial with this kind of raw materials. But it's the same, like, I mean, maybe crickets like is allergic materials, but I mean, it's the same also for soy, and maybe with other kind of insects. I think some people are working with worms. I've never tried worms. It was also crickets. Maybe it's different. I don't know. I'm not a specialist in this area, but maybe if it's like pea is not allergic and soy is, so maybe it's the same also for insects. So we just need maybe to find the right one. Yeah.
Let's thank Rohit
Thank you.
again.
Thank you.
Right. Next, invite John from Saudi to his talk is Saudi in-house capability in plant-based food.
Okay, thank you. And thanks for the opportunity to talk today. I've learned a lot of things, most of them good. The only bad thing is that whenever that camera is pointing at the screen, I can see the back of my head. And the coverage is not as good as it could be. So I'm going to have to take the sunscreen out for this summer. All right. What is SADI? So SADI is the South Australian Research and Development Institute, and we work for the South Australian government on primary production. Normally, we're a very productive state in terms of our crops, our livestock, our fisheries, and our aquaculture. This is a shocker of a year. At the moment, we've got a drought. All the animals have been sold to market. We've got hazardous algal blooms in the ocean and affecting the aquaculture industries. So the state productivity is going to go down this year. So what I'm going to talk about today is a little bit different from what you've heard in some of the other talks. But the first picture is our 24 millimeter twin screw extruder. And we have two extruders. South Australia has one commercial facility that produces plant protein concentrates, faba bean concentrate. And so we invested, knowing that that was happening, we invested in extrusion technology and also air classifier technology that I'll talk about in a little while, in order to facilitate and to de-risk some of that work while they were getting it built. So we have 11 millimeter and 24 millimeter twin screws, 8 temperature zones, medium and high moisture capabilities, face cutter, all the things that you'll be very familiar with from hearing all the other talks this morning. And our output range goes from 400 grams an hour to about 20 kilos an hour through those machines. When many of our clients come in, they see the 11 millimeter twin screw machine and they have a little bit of a laugh because they've never seen one quite as small. It's a bit of a Donald Trump But after seeing it in operation for an hour, they say, wow, I wish we could have one of those, because it actually tells you a heck of a lot. One person working, not wasting a whole heap of ingredients, particularly if those ingredients are in short supply. And you don't have a heap of material to get rid of at the end of the day. And you can learn a heck of a lot. And it is one of my favorite machines. So the sort of work that we do, because we're South Australian government, we're not paid to do basic research. We're there in order to help our food industry in order to de-risk some of those things that they might be looking at. And so what we have to do is to work with those companies and then not talk about the work that we do. So it's quite difficult to give a talk like this and to be enthusiastic about all the things that we've done when we've been told not to talk about it. So what I will talk about instead is ingredients. And we've been hearing today, I'm very pleased with the other talks that we've heard, talking about how critical it is to understand your raw material and your ingredients. South Australia grows a hell of a lot of pulses. My colleague there is standing on top of a 10-metre high pile of faba beans in a stack that contains 50,000 tonnes of faba beans. We grow about 300,000 tonnes of faba beans a year when it rains. We grow chickpeas, we grow lentils, we grow field peas, we grow a little bit of lupin. The chickpeas and the lentils are worth a shed full of money, over $1,000 a tonne. Peas, faba beans only get the farmers about $300 to $350 a tonne. We export almost everything that we grow, and we don't add very much value to it up until recently. And so one of the things you find is that when you're dealing in a global market with a global commodity, competition for access to places like the Indian market or the Egyptian market is very competitive. But what happens when you fill those markets? You've got all of these beans and peas left over that you have no use for, apart from feeding animals. And yet they're perfectly good for human consumption. So what have we been doing? We've been looking at a lot of the things that the questions, what can I use as raw materials to make my ingredients? So we look at things like locally sourced grains, particularly those that are low value, the faba beans and the peas. We're looking at import replacement. Can we use any of that material in order to replace soy? We can do the genetics, the environment, and the management type experiments that say, what happens if do I have to use my best beans, or can I use the stuff that's been affected by drought or frost? Well, the good news is you can use the stuff that's been affected by drought or frost. You don't have to use your best beans. Use those for your export markets. We can harvest the grains, do the grain cleaning, dehulling. We can mill it down different particle sizes. Air classification, I'll talk about that in the next slide. We can do the wet extraction, but again, South Australia's the driest state in the driest continent. We don't have a lot of fresh water to spare. Spray drying, we can do that, but South Australia has some of the most expensive power in the country. So you don't want to be doing a whole heap of expensive energy-consuming activities. We can do the extrusion. We've got a product development kitchen, and we can do sensory analysis. All of those things are within SARDI, and the green box basically shows that all of those activities occur in one building. So those of you who've been there, a couple in the audience who can verify this, but we can basically, 30 meters, we can walk from where we do the dehulling and the cleaning to where we have the extruders and to where we have the air classifier and the kitchen. So, and the sensory analysis is just across the road. So if you wanted to come and work with Saadi as a small company or a company that wants to do R&D, we can do all of those things because it's about where the ingredients come from. I think to take Dennis's phrase, they're just machines. We have 2 machines. We can work at different scales according to how much ingredient you've got. All right, for those of you who haven't seen ingredient processing, because it all arrives in bags, mystery bags that come in, delivered to your loading bay. These are faba beans. This is an ancient dehulling machine. You'll notice that the stainless steel work has been put on for health and safety reasons. It was made in India in the 1970s, and there's a lot of exposed parts there that just would not pass government standards today. So they've been manufactured, but it's a good machine using 2,000-year-old technology, rotating steel stones. Dehulling, cleaning, clean beans, milling, producing the flour. We've heard a lot about ingredient functionality and characterizing this. We can't show you the soy data that we've got, but it basically matches what Evie showed. This is something that we've done ourselves with some of our oat varieties. So even within one species, oats, we've got different varieties that are grown for different purposes. When we put them through the RVA, they react differently. So both in terms of their initial, I won't say, yeah, it is gelatinization, there's plenty of water there. But then in their thickening, once they've cooled, look at the difference here in the different properties of the oats, different varieties of the same crop. And it's to do with flour particle size, whether it's been killed or not, and genetic variation in the lipids and the beta-glucan levels that are in that product. So you need to understand your product to know what you're going to get at the end. Is that good enough, Dennis? Good. All right. Air classifier. Our throughput on this machine is about 2 kilos of flour per hour. It's got a jet mill and an air classifier. And so it goes through the jet mill first, doesn't get out of there until it's small enough. The air classifier then splits it into 2 size fractions, coarse and fine. The coarse bucket here is mostly the starch. The fine bucket here is mostly the protein. With faba beans, we go from 28% protein in the flour. The coarse fraction still has protein in it, 17%. The fine fraction, we can get up to 63% protein. 2.3-fold enrichment, no water, minimal power. Only happens in seconds, and you've got non-denatured starch and protein products at the end. We can do the things that you've been hearing about today with those types of products. We have to blend it. Working with faba bean on its own, you won't get that. You have to blend it with other ingredients. My particular favorite is gluten. My main point today, you do not need to make powders, flours, protein concentrates or isolate in order to make food, plant-based food, delicious, nutritious, and cheap. You can make faba bean pasta very easily, 28% protein. You can make burgers, sausage rolls with 3 ingredients, plus flavoring, oats, beans, cooked peas, faba beans, and mashed vegetables. Delicious. You can come up with locally sourced beans in sauces. Sourced and sourced, yeah, work on that, John. This is our version of baked beans, made with locally grown faba beans, peas. People love them. Instead of using imported navy beans, we can use our own crops that we're already growing and storing. And then my particular favorite is what I'm calling a farmer's bar. It looks like a muesli bar, but instead of using nuts and seeds, it's made using peas and beans. And oats. I love oats. So, working with Saudi Food Sciences, we like to keep it simple. If you use the state government non-disclosure agreement, we can be happy. Don't try and use your own NDA. State government lawyers hate it. IP, you pay the money, the IP is yours. We don't have any hold over it. Contracting, depends how big the project is, but it can be as simple as a purchase order. Costings, we can do a fee per day or do a staged project approach depending on the size of the job. If you're a business or you're a student, sorry, same rules apply. We need the money. For OC health and safety reasons, we have to drive the equipment, but you are absolutely, as the client, encouraged to attend and be an active co-pilot for those trials. And that's it. Thank you.
Thank you, John. Any questions for John? Yeah.
More than a question, is a comment. I like it, your dry fractionation, because you are getting protein, about 67% protein. You know, the isolate maybe have 80% and the concentrate 70%. And this is what you need to do meat analog, for example, a TVP, and then you are quite close. Adding other component that you may do it, be able to do it, without having the issue with the wet fractionation, which you have a lot of problem with solvent and...
It's close, but it's not good enough. You can't use those concentrates in the same way as the isolates. And the other problem with going as high as 63%, you can achieve that, but you're only getting about maybe 20% of your total flour comes out at that level. You've got 80% of your flour is stuff that you might not have a customer for. And you need to store that or to get rid of it or to sell it in order to make the whole thing viable. You can't make it viable just on the protein fraction alone, which is 20% of your yield. So, goes back to, can I use that to make a faba bean pasta? Of course you can.
What is the 80% stuff that you lose? It's a fiber, isn't it?
Well, no, it's going to be high in starch. It's basically all of this.
Because you get 17% of starch, yeah.
Yeah, so it's got 17% protein, it's about 62% starch, and there's fiber in both components. That doesn't split according to the...
Cannot be used for mixing with to make another kind of product?
Oh, it can be,
yeah.
But we don't have local customers that make that. We have some big food companies here, but nobody who uses that type of product. So I'm not saying it can't be done, but we just don't have them yet.
Mm-hmm. Thank you, John. If you have any further questions, just scan that QR code and put in the forms, and we'll pass on to John. Thank you, John.
Thank you. Thanks.
Thank you.
That was good.
Our next speaker is Andreas Hoft from University of Sydney.
Hi everyone, my name is Andreas. I do a PhD at Sydney University, currently in year 3, the fun year. Yeah, when I go to a conference, I think about, do I actually contribute something new? Chances are most of the things have been covered before, and thanks to John now, the novelty of my title has me moving back to slide 5 to actually show you something you probably haven't seen multiple times before. But I'm going to talk about processing of dry fractionated fava beans. You know what that is. Using a microcompounder, you probably don't know what that is. Raise your hand if you heard of one before. 1, 2, 3. John, you don't count? Awesome. Great. Dennis, of course. I just need to show this. I was told I need to show this. First of all, we understand the landscape. There's a great necessity, I don't want to say demand, but necessity for complementary proteins. I understand that's the preferred terminology at CSIRO. A lot of people call it alternative proteins. And here I was going to make a great joke about how many pulses we grow in Australia, but John's pile was just so much more impressive that I'm just going to say we grow a lot of pulses, but we're not really good at eating them. We're good at exporting them. So the question is, how can we functionalize those into protein-rich food applications? And one approach, of course, is extrusion, and that's what I want to look into. We have now briefly covered this. We have an approach called dry fractionation, which allows us to more environmentally sustainably extract proteins from pulses compared to wet fractionation. We don't need water, we don't need chemicals, and we don't denature the protein. So that's quite an important distinction. It came up a lot today. When you have a dry fractionated protein that had not been further processed, the protein is still in its native state. It's highly soluble. And when you process it, that first denaturation actually occurs in the processing, not in the extraction. We then have this quadruple problem of raw material, processing conditions, high moisture extrusion, and then, of course, making a product with that. We've now covered many times how challenging that is, and especially in the context of using novel ingredients, we have the problem of often having very small amounts. When I started my PhD, I was given 300 grams of dry fractionated protein, and I was asked to extrude that. I didn't know much about extrusions, so I thought it was easy. It was not. And then, of course, the black box itself, and then introducing a novel component into the black box for added complexity. So this has been summed up many times. I summed it up as well, had a little report, yay. But this brings us to this machine now. It's a benchtop microcompounder that I propose as an analytical tool for plant proteins under extrusion-relevant conditions. Extrusion-relevant is going to be a word I'm going to say a lot over the course of this presentation. What can this machine do? So we have a micro twin screw extruder with an inline sensor. It's a torque sensor that can collect rheological data during processing. We have a very small sample size, which is defined by the cavity, roughly 15 milliliters or 10 to 15 grams of protein, depending on how you load it. We have residence time as an independently controlled parameter, meaning that we have an extrusion die that I manually open. Up until then, the product circulates in the cavity, so I can adjust that as well. And we also have processing temperatures up to 400 degrees, which is well above our use case, but this is not what it was defined for. We're just repurposing an existing machine for plant protein rheology and extrusion. Here we go again, extrusion relevant, that's what we look for. What is the aim of this project? We want to study the rheological behavior of dry fractionated fava bean protein. Again, we know what that is now under extrusion relevant conditions using a microcompounder. So how do we do that? We basically split it up into two parts. Initially, we want to take our fava bean protein, we mix it with different moisture contents, and then we extrude it under defined conditions at different temperatures to see the impact of temperature and moisture content on the rheological properties on water holding capacity. Now we kind of have a bed in which we can understand our product better, and then we introduce other components to see their impact on rheology and extrusion. In this context, we used salt. So we had different salt additions, sodium because so commonly used, and then we tried to match that in ionic strength to not actually just establish that, oh, you know, you have 1% of this, 1% of that, they're different. Is it because of the ionic strength or because of the specific functionality of the ion? So we match that and then compare that. We look at rheological data, water holding capacity, protein structure, and then some post-hoc analysis. We did some T2 NMR for water mobility and SEM. This is what we look at in terms of data that comes out of the machine. This is just one of the generic profiles. We put our sample in. It is spun around in the microcompounder. We see viscosity increases over time as we process it. really start to become afraid to say it, but I think we do see protein denaturation in the extruder because we start off with a native protein and we expose it to heat and shear well above the denaturation temperature of the protein. And this is what it looks like. So bottom left, empty shell before I mess it up. Then I put my protein in. It spins around in the cavity. It has the side feed channel where it comes out at the top until I open the extrusion die. Hence, again, independent variable processing time, residence time. I can make these little pasta sausages, like John showed before, spaghetti. I can also dead stop the machine and then just take the sample out, which is the sample extraction method that I chose because I was looking at high moisture extrusion, not at TVP extrusion. So I wanted to avoid to have any flash evaporization. So I actually let the material in the machine to let it cool down enough to avoid that effect when I look at the structure later. What we see in the bottom right I found quite interesting. You can also just spin material around. So this is below denaturation temperature. It just comes out as paste. Looks like pasta, but it's paste. So I put a spoon in it so you can see that. Very uneventful. We just look at a constant temperature and increase our solid content from, or have it the other way around. We will like decrease the moisture content from like 60, 55, 50%, and viscosity increases. So that's not groundbreaking. We just have more solids in our dough, and viscosity increases. We can graph the SME over time as well. It's quite interesting. Some previous work, thankfully not me, calculated how to get specific mechanical energy out of this specific machine. So I can now graph that out and get my data points at different times. Now I change the temperature. It becomes a bit more complex, as per usual with rheology. Down at 100 degrees, when we look at the viscosity, top left, we see it is at 50%, rather low. At 55%, it shoots up, and in 60, it goes down again. So this time, it's not linear. So now it's confusing for me because I just want to have a simple trend, but this is not a simple trend anymore. Same goes for water holding capacity. If we look at the electron microscope structure and we see, like porosity increases with moisture content, what does that actually mean? How is that related to viscosity? It's as always, very, very complex. So as we put these different parameters into the machine, we get a huge load of data. And I, in an initial approach, just took all of that and put it into a PCA. So we see these clusters, and these clusters are based on process parameters. So that's great. And when we look at the left side on the right there, there's like these two that stand out. It's 110, 55, and 60, where we have the highest water holding capacity. And they're at neither end of the spectrum of what we tested. They're not at very high moisture, they're not at very low moisture, they're not at very high temperature, not at very low temperature, they're smack bang in the middle. We can then correlate that with what we tested for. In that case, that is our T2 water mobility NMR and water holding capacity. And now we use that and say, okay, well, that's a condition that seems to at least produce a matrix with increased water holding capacity, and put that into the context of salt. So we take our control, and then we add initially 1% of sodium chloride, and then we have the ionic strength matching amount of potassium chloride and calcium sulfate. And viscosity is impacted by it, but differently. Different ions have different impact on the viscosity in extrusion, and the same goes for water holding capacity. All salts drastically decrease it, but we find that certain salts, in this case calcium sulfate, decreases it more than the other salts. And this is already all this data that we got out of this really cool machine that we just happen to have in our lab. Thank you very much. And that allow us to take these raw materials that we often have in small quantities, and we can process them under a variety of different conditions and subject them to what we're interested in, whether it's a moisture-driven content approach or a temperature approach or a native versus a denatured protein. I know CSIRO, for instance, does work on dry heating their proteins before they put them into the extruder to see the impact of that. But I understand you haven't done that with native proteins, so that would be a really cool thing to look into. And once all of that goes above my head, I would love for someone to have a crazy AI model where they can feed all of this data into. Not my PhD, but maybe someone's. Again, here, we want to understand what is driving the changes. We did a whole band FTIR scan on our samples. Often we just look at the protein secondary structure and say, okay, I'm at band 1, changes, great. We took the whole 400 to 4,000 and then did a PCA on that against the normalized curves. And so, okay, we again have clusterings based on conditions, but also we quite clearly see that the salts are the strong outliers. And we already identified that despite ionic strength match, calcium sulfate is an outlier in both viscosity and water holding capacity, and we also now see it on the FTIR. So there's likely protein secondary configuration and some other configuration that changes with that. That altogether brings us to a point where we can say, okay, dry fractionated fiber bean protein has potential for high moisture extrusion. I personally want to add, there's also other things you can do with these, not just extrusion. There's gels, I prefer them, they're fun to work with, also less complex. But the extrusion part, I think, offers a great platform where we, from the academic perspective, maybe need to deliver the input to incentivize the industrial counterpart to actually work with these materials, because right now it's just too difficult. We now see that salts, for instance, in this instance, can impact our rheology, can impact the product. Again, academia has not a crazy amount of data that I could find on the impact of salt on the extrusion parameters of native proteins. You know, usually academia is 10 years ahead of the industry, or the other way around, one of the two. And most importantly for us, the microcompounder emerges as this valuable tool to analyze extrusion rheology, specifically for us in the context of plant protein. That brings us to the microcompounder plus material analysis as a potential amazing tool to do this analysis and process optimization in rheology. But does it? You know, we often come this far, and then as academics, we're like, great, published, move on. So this is just the last snippet I'm going to add. I was pretty happy with. We presented a bit of this work, and then we had an industrial partner that came to the university and saw that, and they're like, this is amazing, can we come and chat? And they came in and they showed us the problem they have, and they have a baking ingredient that they mix into their dough, and there's a certain functional property that they look for in that ingredient. And in their ingredient production, they extrude. And so the hypothesis was that extrusion parameters actually impact that, but they couldn't quite tell how. And the extrusion operators would tell them, stay away from my machine, we're not going to change anything, it's probably something else. So they came in for a day, they had a little bag of samples, and we could systematically investigate a few different parameters with this machine and saw their impact on the certain functional property that they were so keen on exploring. And they could quite easily show that extrusion parameters heavily impacted that property, which gave them ammunition to come back to the extruded parameter people and actually say, look, there's probably something we need to change. And that was quite an easy test for us. It only took us a day, but we could translate some of our academic findings into an industrial application, which is always fun for a PhD student. That being said, thank you very much.
Thank you, Andrea.
Thank you, and I think my time is very over now. Yeah.
That's okay. One question.
So nice talk. Thank you very much. Two question, comment. Have you considered the wall slip effect in your measurements? Because I believe with the gel formation, it will change depending on what gel synergies of water plus, as well as the possible fragmentation of starch with increasing time. That might explain your results, that, you know, unexpected results, so to say.
Thank you for both of your questions. So like wall slip, I've considered in the context of, could I understand when it occurs? And if so, maybe try to not set my testing regime into those parameters. We found that once we increase water content too much, we cannot texturize the material at all anymore, so we have just no increase of viscosity. And we may thought this could either be due to that, or we just have the lubricating effect of the water, like making the wall slip occur. So when we then look at our graphs, instead of seeing any increase of viscosity, they just stay dead flat. So maybe that is due to the wall slip, and we just then decided to stop our testing at 60% moisture content.
Just for your publication, the wall slip can also happen at very low water content as well. Yeah. Because when you have a very hard gel, it might also just slide, right?
Yeah.
So.
We defined the bottom end of our moisture concentration when the material would stop circulating, which was around 50%. Again, I know this doesn't perfectly answer your wall slip question. These are the two parameters that we set. In terms of starch, we have not specifically looked at the starch distribution in the material, but it is an inherent property of dry fractionated material because the starch content is so much higher than isolate. So maybe this is one of the learnings that we can take from this type of analysis, that we know starch is in there. We can consider it in how we define our experiments. Thank you.
Thank you, Andrea.
Oh, give back.
Next, I will invite Jay from Extrude Tech to give us a talk about extrusion process innovation.
Hello, thank you for inviting me, and glad to be here today representing actually a group of companies. So some of you may be aware the Winger company was purchased about 3 years ago. Extrude Tech has been part of Winger for several years now, since 2000, I guess. But we've been separate brands for over the years. But when Morel purchased us in 2022, we started working a little bit collaboratively together, and innovation is one of those things. And then Source Technology has been part of the Winger Group for over 20 years as well. So recently, Morel, at the beginning of this year, was purchased by JBT. So now we're part of a very, very large organization worldwide. I've been director of innovation for the Extrude Tech business for the last 5 years. Now director of strategic innovation for the Winger Group, and trying to merge all the different processing technologies and offer a great solution for the customers, and trying to work together with the different groups to define what that right solution is for customers. So that's kind of my role. I have a little bit of an odd background. I started in this industry in 1990. Started as an operator, actually a bagging operator, and cleaning equipment, sweeping floors, you know, just whatever needed to be done in 1990. Worked up and got interested in it started out, it was just going to be a temporary part-time job. Became a career. I had no idea I was going to spend these many years in this career, but learned to run an extruder, the dryer, the coating systems, the coolers, all that, and then just got so interested. I went back to college, got a degree in grain science, and so I've learned just enough over the years to be dangerous on the serial chemistry and the physics behind everything, and just kind of grew the career from there. So majority of my time has been in process development. I've done some product development, especially early in my career. After college, was more into the theoretical and scientific side of things. And over time, just nature of what I was most interested in, it started moving more into production and applying what the basic fundamentals to real life production problems and challenges, and fixing problems. And so the total process has really become my passion, not just, just the extrusion. It's the whole process, the batching, the mixing, the grinding, the extrusion, all the way through to packaging. So it's a little understanding of my background, I guess. So going to go through a list of innovation. This is a little different in presentations that I've been listening to for the most part, where most every individual slide will be a different innovation. And I'm going to not focus on one topic. I'm going to talk in general terms of things that have been done to make life easier for operators in production plants, give more flexibility to the process and things like that. Talk just very briefly on preconditioning, and then I'm going to spend a few minutes talking about single and twin screw extruders, and then get into some of the more unique different types of products that our equipment is capable of making. I won't spend much time on meats and alternative proteins. It's been talked a lot about today, so we'll just go through that pretty briefly. By the way, it is coming up on time here for the drinks and everything. This presentation would be a lot more interesting to everybody, I'm sure, if we were already having some cocktails, but Just a suggestion. Okay, so we'll get into preconditioning. You know, there's lots of different types of preconditioners, twin shafts, the high intensity preconditioning. I'm not going to go into the details of that. They're continuous mixers. It's a way to start the cooking step faster and hydrating the ingredients before it hits the extruder barrel. What I'm bringing today, some of the newer things about it is the mixing control. So with automatic control of the shaft speeds, independent speeds on the shafts, and slide gate positions at the discharge of it and things like that, you can, to a certain extent, control the mixing intensity before it ever even gets to the extruder. And then use of this technology, and especially with the slide gate at the discharge of the preconditioner, you can speed up your startup conditions and get everything mixed and hydrated and up to temperature if temperature is part of the preconditioning step before you ever even send material to the extruder. So you minimize your startup waste. Going to a couple of things on single screw extruders. It's well documented. It's been around, this technology has been around for a long, long time. Some of the things that have been done differently is the use of tools and sensors to give operators online adjustment capability. You know, things like shaft speed, being able to vary that on the fly, being able to control valve positions either in the middle of the barrel or at the end of the barrel to control the mechanical energy and spread out that cook throughout the length of the barrel has really done wonders to the flexibility of the process. I will say I agree wholeheartedly with, we need more people in the industry that understand the development cycle and the importance of understanding the process and what's taken place and what the shear rates are and all that. But what we've created here with some of these next few slides is a more flexible system that, you know, with that understanding, we can kind of set a screw configuration and set a die plate configuration, the holes on the end of the extruder, and then give operators adjustments to control the texture and the shear rate, the mechanical energy, to give them a product that matches their quality specs. I think there's a lack of understanding how to marry those fundamental bits and pieces of the development of a process and the quality specification. I've been in hundreds of pet food plants, especially pet food. But I've never seen a quality specification that includes shear rate. It'll include bulk density and things like that. I've never seen shear rate as part of the quality spec that an operator has to check and make sure that they're controlling to. They don't really have a practical way to do that in the middle of a process. So this is an example on the Extrutech side on single screws where we've used a valve in the middle of the barrel and a valve at the end to control the mechanical energy and be able to get to very high levels of meat, almost 1-to-1 ratio of meat to dry mix, and make it a very durable pellet. We've done similar things with sinking aquatic feeds using the same mid-barrel valve to control shear and energy early in the barrel, and then form and cool and densify at the end of the extruder barrel. And missing the picture here. Okay, it was just an add-on. So to make a very small, very dense sinking fish food pellet. Has great water stability and everything. On the winger side, using different types of configurations, and again, a valve at the end of the barrel, the back pressure valve we can use one configuration and be able to adjust on the fly the texture and the energy levels to give a very flexible machine that'll make a lot of different types of products. Similar technology with just different screw configurations and barrel lengths, and whether you warm the barrel or cool the barrel, different die configurations. We can make all kinds of sinking, slow sinking, or floating aquatic feeds of all different types of sizes, down to 0.3 millimeters. Way above 10 millimeters is possible. I mean, I've seen over 25 millimeter pellets. And then the thermal twin process, where we're taking advanced technologies and we're kind of changing up the mechanical energy versus steam energy and giving it to where we're seeing up to 10 or 12 to 1 ratios of thermal energy versus mechanical energy. So kind of a complete different way of cooking the product. But we're able to achieve over 50% meat in proportion to the grain mix this way. And then we go into a convection roaster that kind of sets, this is very soft product. You can imagine being 1-to-1 or better ratio of meat to grain mix. And so it needs some temperature and some time to set that structure, create the shell that'll hold that kibble together through further processing. So we go into a very short retention time roaster to create that, that surface shell. And then into traditional drying process. Pet treats, there's all kinds of different things we can do with co-extrusion to make a wide variety of products. We have crimping systems that can make a filled pillow with a liquid emulsion in the center. We have dies that rotate and that can create a twisted treat coming off the extruder. We have equipment to put on a single screw extruder to be able to make up to 4 colors and 4 different shapes at one time off of one machine. So lots of advanced technologies that are out there commercialized. Regarding textured proteins, we have, of course, single screw extrusion equipment that's been used for TVP for so many years. It's not innovative, and so I'm not even mentioning that on here, but when we've got twin screw systems doing all types of textured meats and alternative proteins these days. The picture here is actually of our source technology power heater, and it's capable of taking a meat emulsion and processing it through anywhere from 1 to 5 tubes and using thermal energy to cook the meat and get laminar flow out of it. And then I don't show wasn't room for the flexi cut system that will chop it into different size pieces. But you can see that from the pictures here, the wide variety of types of products that it's capable of making. So I'd mentioned my career has been around the entire process. So I had to throw in a slide on drying improvements. We've got a lot of new innovation that's designed to help with energy efficiency, with standby controls between production runs, or if there's something that causes equipment to go down, to be shut down downstream. We can control the gas usage and the fan speeds, so we're not just blasting energy out through the roof when there's no product in the dryer. And advanced spreader controls to help with uniform moisture, product moisturing using sensors and smart technology, air controls on the exhaust air so that we optimize the heated air that we're using, that we're creating in the drying process. And then we can, with some new technology, we can recirculate that. We can clean it and recirculate it so we're not putting as much air out through the roof that way. And then electric and hybrid drying is also things that are new that are available these days. And then the last slide here is batch coating and vertical cooling. So we've got technology that can take and pre-weigh the kibbles before the coating process so that we know exactly how big the batch is, and then we can match that with the proper amount of liquids. So every batch is unique, and we can get exactly the right amount of coatings to apply on, and powders as well. And then that goes into a mixing process that gently stirs that. It's a cycle, it's a batch cycle, so we're going from a continuous process up to that point, creating batches, and then dumping directly into our coolers. So there's no extra transfer of product that could break product up and cause degradation. So it's a lot more efficient process that way. Sanitary design with our coolers is very important as well. We've talked about hygienic design on things. There's no moving parts. There's no spreader inside our cooler. There's no grids that have to be cleaned in between production runs. It's essentially a vertical bin, so very easy to be cleaned. So with that, that's the end of my slides. Any questions? Or
thank you very
maybe
much.
We're out of time.
Yeah, if you have any questions, just put in the QR code, and then we'll send it to you. Okay. We don't have time for, sorry about delay. Yes, next is my talk. To be fair, I will put the time.
I'll come and sit up the front, Daniel, and keep you the time. Time's up. Chair, just because you're chair doesn't mean you get away with it.
It's my pleasure to share one piece of our research technology called extrusion, high max extrusion cooling die. As Dennis was saying that there is a big failure in the plant-based meat analog. And we always ask why, how this will happen, and how can we avoid that. And one of the pain points we found is that everyone is working on that different sorts of cooling die for the high moisture extrusion. But one thing we find is that this cooling die, although especially the students like this very much because that the flow is simple. It's easy to use computational modeling to simulate. So the students love it, and also it's simple. But the problem is also generated from this, because this cooling die is rely on the pressure generated by the extruder, the screw, to push the paste out from that long, narrow channel. So therefore, because of this high pressure, and the material or the product produced is very dense. It's much denser than the meat. So that's one issue. Another issue is that because the pressure needed to match, the screw-generated pressure needed to match exactly the cooling die, the back pressure. Therefore, the operation needed to be very accurate. Any changes in formulation or any conditions, and then the balance will be break. And in order to find that balance, and needed to do some more trial and error. That's what we found. So therefore, one of the idea we think that if we can have a die that instead of let the extruder, like the pressure, push the paste through. If we can have a die that's pulling the paste, that's the technology or idea coming from. So the paste generated by the extruder, and then this is the cooling die, and pulling this paste. And we can use that rotating movement to pull the paste. Therefore, any
paste generated from the twin screw can be easily carried away without need to match the pressure, back pressure, and any. So, and also the pressure, you don't have to generate the huge pressure, back pressure, because that only need to have like a nozzle kind of small, very low pressure, and therefore the material can be taken out very easily. So that's the idea from for our this idea. So this we have tested this idea in our pilot plant. And through lab scale extrusion, use different protein, soybean or chickpea lupin. And then we found that the pressure is significantly lower required. And also that the texture is very easily controlled by the varying moisture content or by different extrusion parameters, very easy. Whatever the paste that the screw generate can easily take by that cooling die. And also that and also we can like generate some porous structure, because that if we have a high pressure at slightly higher pressure at distributing nozzle, and then there is a pressure gap, like because the cooling die is basically zero pressure, or it's 1 atmosphere pressure. And then there is a pressure drop, and the pressure steam in the high temperature or pressure steam inside this distributor can like generate a puffing effect. But this puffing effect is controllable. It's not like a blast to everywhere, but this we can control using that cooling die temperature and rotating speed. So with this idea, and we found, okay, this idea is workable, and we've managed to generate some kind of rough idea, like the high max throughput is much higher than conventional, because that, as cholesterol was pointed out, that the bottleneck for the extruder is the cooling die. So, but with this new cooling die, and the bottleneck can be opened up much, remove this bottleneck. And also the pressure is normally less than a quarter of the conventional cooling die required. And also the texture we can control into soft texture, juicier, and more realistic meat-like. If you want to simulate like a beef, pork, or chicken, or the fish, it's all it's possible. So we can produce 100% plant-based analog chicken, beef, fish, pork, or hybrid meat. That's like, it's a slightly different hybrid you're talking about, because this hybrid we are use the animal meat, feed it to animal meat, and have plant protein or flour even, and then extrude it out into like a hybrid meat. So, and there is a lot applications possible, like can put into stir-shred meat or ready meals. So, and we are looking for some kind of collaborations, like joint trials or license or early access commercializations. So, yes, so in quick summary, and high max cooling die is enabled the next generation meat analog to be produced, and great flexibility and efficiency and texture control, and suitable for both plant-based and hybrid meat. Thank you very much. Happy to answer any questions. Otherwise, we will move to next. Yes.
Hi. We also heard this morning, I think Billy present about the lupins that we can't extrude in our traditional extruder. do you think this one works well with lupin and fava as well? It has a lot of back pressure. It can't extrude, say, 100% of fava protein isolate or lupin protein isolate.
Yeah, we have this overcome these back pressure issues, but some of the chemistry, like cross-linking, that's still material dependent. Because if this material unable to form like a fibrous structure and even use this new cooling dye, still won't be able to, because some chemistry, basically you can't change by this mechanical. So if they are inherent, all those ingredients, and then that's still there.
Danyang, the pressure drop in the die is a function of viscosity, flow rate, and geometry. Even if I pull it, it should remain same.
Yeah. So for this one, anything like the viscosity, all things that's before that paste or paste distributor, that's still rely on the material's viscosity and the rheological properties. But the back pressure from the cooling die, there is no back pressure transfer to the extruder. So basically it's decoupled.
On the belts.
That's right. So,
no wonder it works. Okay.
yes, yeah. Yeah. Oh, yeah. Dennis' question is that whether these two moving like surface, there is speed difference. That's right. So for the rotating things, like outside don't have to rotate, and inside is rotating. So there is the shearing velocity difference. And for the moving, like a belt kind of configuration, two belts can drive different speed. So they also generate the differentiated speed.
I wanted to ask, like, does the mycotoxin content in grains decrease when you use extrusion?
That's a slightly different, yes, that's the microtoxins, that's extrusion itself, like has these certain kind of functionality, can reduce the anti-nutrient and maybe microtoxins, yes.
Yeah, one question. You know, the dragging of the material inside the cooling die, depending of the non-stick condition in the rolls. And then what happens when you have material with maybe a little bit high content of fat, when you have a slip, can you drag the material into the cooling die?
Basically that, because that rotating surface could have some slippery, but still will have some kind of frictional dragging force. So for if you have a higher oil loading in the mixture, and there will be have some slippery. Yes, yes. So the surface of the drums can be like a rough surface or treated like heat treated differently. Yeah.